Hi, so my name is Hafiz, and disclaimer, this is not a tutorial video, this is a study video. So this video is all about study, and I'm not a professional, I'm just a university student, and I just want to study like the behind the scene of AI in the computer vision. So please correct me if I'm wrong, and since this is a study video, I hope you will learn a lot from it. And so yeah, that's it. Let's get started into the study section. Okay, so in this part of the segment, I'm going to basically speed run the neural networks, because so the purpose of me making this segment is I want to show you what you are going to study. So that's the goal of this segment, because sometimes you just study a lot, but sometimes you don't know why I would study this subject. Like you find those mindset in a mathematics subject, and especially so in this video I'm also going to go through the mathematics aspect of the neural networks, so to show you what you are going to study, and then getting rid the mindset of why I would study this subject. It does not it would not help me in real life kind of a mindset. So I'm just going to create this speedrun programming part, this speedrun explanation of a neural nets. So I'm just going to basically showing you the finish line before we go into the marathon. Okay, so we are going to create a neural net. Okay, so let's just start it. Because this is a speed run just to show you the finish line. Okay, and of course I'm going to explain everything in a detail in the next segment. Okay, so we are going to create a neural net that has 10 neurons, and in the last neuron I'm going to have 5 neurons, because I'm using my own dataset. So I have my own dataset, and it's going to be an 8x8 images. So it's really small images, like as you can see, like it does not look like images even. So it is an 8x8 images, and I have a handwritten kind of like dataset of an alphabet going from A into E. So I have 5 category. So this is one of the example of A, and this is one of the example for the E. Okay, I don't know if you can see that, but trust me, it is E because it is such a small dataset. It is an 8x8 dataset. Okay, so this is the forward pass. This is the forward propagations, and of course we are going to using this as our kind of like a guideline. Okay, so in the forward propagations, I would have an A is equal to the input times the so the input is basically the 8x8 images times the amount of images that we are going to have. And then in the first layer, which is the input layer, I'm going to have the W, which is the weight, multiplied by the input plus the bias value for each neuron, and I'm going to have the Z value for that. And then in the second layer, which is basically not the second layer I'm sorry, so in the next part, because this is going to be the linear function, so I would perform the non-linearity function to get the non-linearity value from it. So I'm going to use a rectify linear unit non-linearity function. So it's going to be something like this. It will look like this, and in the value, if I have a value that is bigger than 0, I would have that value, and if I would have a 0 value, not 0 but a value that less than 0, I would get a 0 value from it. So that is what the value function is. Of course I'm going to explain it better in the next segment. And then I would have in my second layer, and in my second hidden layer is going to be my output layer. So in this case I would have the weight, and then multiplied by the input from which is the input is basically the output from the first hidden layer plus the bias value, and I'm going to call that z value. And then after that, again, it is going to be a linear function, so we need to have non-linearity to it. And since it is the last layer, which is the output layer, I'm going to have my my probability distributions non-linearity, which is the softmax. And the softmax is going to be something like this. So it's going to be e to the power of the input divided by the sum of the value of e to the power of every input of every value distributions, basically. So that is the forward propagations. And for the back propagations, I would have something like this. So first of all, I'm going to have my data into the one-hot encoding. So the one-hot encoding is basically, like for example, I have 5 categories. So for example, my first image is A, and A is basically in the 0th index. So in the 0th index, I would have the number of 0, or the number of 1. I mean, I would have the number of 1, and the second, the third, the fourth, and then the 5th index is going to be 0. So that is what the one-hot encoding. And again, I'm going to explain that later in the next segment in a more detailed part. And then I would have, so that is basically the true label, and I would have my, the prediction that this softmax activation function outputted, and then I would have, see the loss function, see the loss value. And then for the back propagations, I need to derive all the propagation, and this is how I'm going to do it. So the dw2 is going to be 1 minus m, which is the amount of data, multiplied by the dz, which is this loss value, multiplied by the A transpose, which is the activations. And then I would have the dp of the second layer, and it's going to be 1 divided by the m multiplied by the sum of the dz value, and then the dz is going to equal the w, which is the weight value, transpose multiplied by the dz value times the derived activation function. So in this case, I would derive this ReLU function, and then I would input my z1, and then after that I'm going to find the dw1, and it's going to be 1 divided by m times dz1 times the input transpose, and then finally I have my db my db2 is equal to 1 divided by the m, which is the amount of data that I have, and then multiplied by the sum of the dz1, and then I would have my my parameters getting updated, which is by doing this. So the parameters is going to be w1 will become, so the previous w1, so this is going to be the new w1, and this is going to be the previous w1 before we get into the back propagations, minus the learning rate of alpha times the dw1, and for the new bias value b1 is going to be the previous bias value, which is the b1 minus the learning rate of alpha multiplied by the db1, and then the new w2 is going to be w2 minus learning rate of alpha times the w2, and then finally for the bias value of in the second layer, which is b2, is going to be the new b2 minus, no, the previous b2 minus the learning rate of alpha multiplied by the dp, which is the derivative b that has connection with the loss. Okay, so we are going to do all of this. We're going to do all of this using this kind of this really simple image, okay, and we are going to do a simple image classification. So if I'm if I'm input an image, I hope my AI model is going to give me a prediction of what kind of image it is. Is it the image of a capital of A, or the alphabet of, not capital, but the alphabet of A, or the alphabet of C, or the alphabet of D. So that is the classification problem. Okay, so yeah, that is the explanation. Now let's get into the programming part. Okay, so here's my Python IDE, and I'm going to import some dependency. I'm going to import numpy as np. I'm going to import pickle as pkl, and I'm going to import matplotlib.pyplot as plt. Okay, now I'm going to load the array from the binary file, the array from the file using pickle that I have. So it's going to be with open. I'm going to have my dataset. So I call my dataset class.pkl, and then I'm going to read binary those dataset as file, and the dataset, which is the variable that we are going to use as our dataset, is going to be pkl.load, and I'm going to load the file. Okay. Now for the dataset, I'm going to change the dataset into the np array, not np array but numpy array, and so it's going to be np.array, and it's going to be dataset. Okay, I'm going to make it this bigger. Okay, so maybe like that. So, and then I'm going to have my np.random shuffle to shuffle my data. Oh my god, shuffle is going to be dataset. Okay, and okay, I'm going to get my m and n, which is the dataset dot shape. So I'm going to use this later. So okay, I need to split the dataset. So I'm going to do this data underscore train, and it's going to be dataset, and then 50 until m. So n is the amount of dataset that I have. Okay, and I'm going to transpose this dataset. Now after that, I'm going to have my x train, and it's going to be data underscore train, and it's going to be until -1. Okay, so what's happened here? So basically I'm taking the last value inside of my array, and so basically this last value is basically my dataset, not including the label. Okay, so again I'm going to explain that later in a great detail, but now it's just for the speed run, it's just for to show you the goal of what you're going to do. And then I would have my x train is equal to my x train divided by 255 to normalize the data, and then I would have my y train, and it's going to be the data train, and it's going to be -1, like that. Okay, so this is the data train, which is the amount of data that we are going to use. Now we have a data trend. Now okay, after we get the data train, we need to have the data test, and the data test is going to be data set, but it's going to be in the reverse of this. So instead of 50 until the amount of data set that we have, I'm going to have until 50, not from 50, until 50. Okay, so that is the test data set. That's the test data set, and then I would have my x test is equal to data test until -1 to get the label, and then my x test is also going to be x test divided by 255 to normalize the data, and then I would have y test, oh my god, test, and it's going to be data train is 1 to get the label, not the image. And then okay, so we finished with the data preparation. Now let's get into the neural network. Okay, get into the neural network. So it's going to be, so first of all, you need to initialize the parameters, which is, okay, so the parameters is basically this one, so w1 and then bias value, so which is the weight and the bias. So let's create a function which is defined init params, and it's going to be so oh my god, it's going to be w1, which is np.random.ran, and it's going to be 10 because I want to have 10 neuron, and I would have the same amount of the data that we have. So remember that we have an 8x8 data. So by using 8x8 data, I'm going to have my 16 input. So that is what this n-1 mean, because we are not including the label. So so all the input not including the label. So basically this is what the n-1 mean. Okay, and then I would have my 0.5 to get the random value between -0.5 until 0.5. And then for the p1, I would have np.random.ran, and it's going to be the same, which is 10 neuron, but for each neuron I would have only one bias value. And then for the w2, I'm going to have np.random.ran, and I would have 5 neuron because I would have 5 category, so the output is going to be 5, and the input from this layer is going to be the same amount of the output from the first layer. Okay, and then for the p2 is going to be np.random.ran, and it's going to be just the same, which is 5 and 1, because the bias value only has one value on each neuron, and I would return all of that, which is w1 and then p1 and then w2 and then p2. Okay, so something like that. So that is my initialized parameters. And then I would create my activation function to get the non-linearity value, and the activation function is going to be this value here. Okay, so value, okay, I would define, and I would create my value, and I would have the input of z, and it's going to be return the np.maximum of z and 0. So z like that. So if it's greater than 0, I would have that value, but if it's less than 0, I would have 0. and then after that I'm going to make my softmax activation, and it's going to be also z, and it's going to be a is equal to np dot the exp of the input divided by the sum the sum of np dot exp of the z. Okay, so that's how you create the softmax and return those value. Okay, so that is for the initial parameters. So now for the forward propagation. Okay, I'm not gonna do that. So for the forward propagation, it's going to be, so I'm going to define forward prop, and I need the value of the W1, and then P1, and then W2, and then P2, and then the input value, and it's going to be Z1 is equal to W1 dot of X, which is the input, and then plus the base value, and then I have A1, which is the activation function, and I'm going to call the ReLU function that we've already created, and it's going to be Z1, and then for the Z2 it's going to be equal to W2 dot the dot product of, oh my god, dot A1, and then it's plus P2, like that. And then for the A2 I would have the softmax activation function, it's going to be Z2. Okay, and then I would return the Z1, and then A1, and then Z2, and then A2. Okay, so that is the forward propagations, which is following this equation. Okay, so again, Z is equal to W1 multiplied by the input, which is the data that we have, and then P1, which is you know, the same thing, okay, that we apply. And then I would create, okay, so before we get into the as you can see, before we get into the back propagation, I need to have my one hot Y encoding. And so let's create the one hot encoding. So it's going to be one hot of the Y, which because it's going to be the label, and it's going to be one hot Y. It's going to be np dot zeros, and it's going to be Y dot size, and then Y dot max, like that, and then plus 1. Okay, and then we have one hot Y is equal to, not equal to, but np dot range, and then Y size, and then it's going to be Y is equal to 1. Wait, where's my 1? It's equal to 1, and then my one hot Y is equal to one hot Y dot, we need to transpose that data, and then we return the one hot Y. Okay, so that is the one hot Y encoding. Now for the back propagation, okay, so this is the one hot encoding, and for the back propagation, I would create the define, which is backward prop, and I would need my Z1, and then A1, and then Z2, and then A2, and then W1, and then my W2, and then the input and the label. Okay, now for the one hot Y is equal to one hot of my label, like this. Okay, so this one is we get from this one, and then from this one we get into this one basically. We get into this function was 1 hot. Okay, after that I need my dz2. It's going to be a2 minus the 1 hot y, and then my dw2 is going to be 1 divided by the m amount of data multiplied by the dz2 dot of a1 dot transpose. And then for the db2 it's going to be 1 divided by m multiplied by the np dot sum of my dz2 like that, not sum but sum. Okay, so and then for the dz1 I would have my w2 transpose and then do the dot product with the dz2 and then multiply by the ReLU derivative. Okay, so we're not creating that yet, and it's going to be z1, and then the dw1 is going to equal to 1 divided by the amount of data multiplied by the dz1 the dot product of the input transpose. Okay, and then for the db1 is going to be 1 divided by the m amount of data multiplied by the np dot the sum of the dz1. Okay, so we can return all of those variables, which is dw1 and then db1 and then dw2 and then db2, and also we need to create this ReLU derivative. I'm going to create that here, and then we just define ReLU derivative, and it's going to be the input of z, and we are going to have we're going to return z is bigger than 0. Okay, now, and that's it. So that is the ReLU derivative, and then we just the ReLU derivative is going to give us a value of it's either 0 or 1. So if the value is bigger than basically bigger than 0, I'm going to have 1, and if the value is less than 0, I'm going to have 0. So that is what the ReLU derivative is, and again I'm going to explain all of this in a great detail in the next segment, because for now it is going to be a speedrun segment just to show you what you are going to study. And okay, I'm pretty sure that if you're never doing, you know, neural network from scratch, all of this is going to be very confusing, and that is completely normal, because all of this is basically a mathematical aspect, a mathematical calculations, and we are going to study all of that in the next segment. And then I'm going to continue this just to finish this, and then it's going to be the update part, and the update part is going to be a function of the update parameters, and I would need my w1 and then p1 and then my w2 and then p2 and then my dw1 and then my db1 and then dw2 and then my db2, and then I need the learning rate of alpha. Okay, and so the new w1 is going to be w1 minus alpha multiplied by the w1, and then for the b1 is going to be b1 minus alpha multiplied by the db1, and for the w2 is going to be w2 minus alpha multiplied by the w2, and then finally for the p2, which I'm going to have my p2 minus the learning rate of alpha multiplied by the dp2, like that, and then we can return all of that value. It's going to be w1 and then p1 and then w2 and then p2, like that. Okay, so oh my god, so after we update, we need to create the training part, the training neural networks training. Okay, so first of all, I want to make my gradient descent. Oh my god, descent, and inside this gradient descent I will have my input images, and then my label, and then my learning rate of alpha, and then the amount of iterations. Oh my god. Okay, so for the w1 and then p1 and then w2 and then p2 is going to be init params, so we get the value of the random initialization from the function, and then for I in the range of iteration is going to be z1 and then a1 and then z2 and then a2 is equal to the forward propagation, and we are going to give the forward propagation our w1 and then p1 and then w2 and then our p2 and our input x, not that, but and then so that is the forward propagation, and then now we need to back propagation. Doing the back propagation, it's going to be dw1 and then db1 and then dw2 and then dp2, like that, and we're going to call our back propagation function, and we are going to have our z1 and then a1. It's going to be all of this value basically, like that, and then z2 and then a2, and then we need to have w1, w2, and then x, and then y, which is the label. Why am I? And then finally we update the parameters, and it's going to be w1, p1, and then w2 and then p2, and it's going to be update parameter, and we are going to give this w1 and then p1 and then w2 and then p2, and then all of this value, which is dw1, dp1, and then dw2 and then dp2, and also we need to give the learning rate of alpha. Okay, now if I is okay, I don't know what the English word for it. So basically, if it's divided by 10 and then we get 0, we are going to print the iterations. So I'm going to have my f string and then iteration of I. Okay, so let's just do that, and then I want to get the prediction, and it's equal to get prediction. Okay, and we are going to create that predictions, and okay, so we are going to create that function of get prediction. So define get prediction of a2, and it's going to be return np.argmax, which is this one, argmax of A2 and then between A2 and 02. Okay, and then after the predictions I would have my accuracy. So I'm going to print the get accuracy, and it is going to be a function that involves the predictions and the true label, which is y, and then I would create that function which is get accuracy, and it's going to be oh my god, I'm sorry, it's going to be predictions and the true label. And here we are going to return the np.sum of the predictions is equal to y, then divide by the y.size like that. And then so that is the accuracy, and then we can going out from this for loop and return, oh my god, and then return the w1 and then p1 and then w2 and then p2. Okay, so now to train we need to call the gradient descent function, and it's going to be w1 and then p1 and then w2 and then p2 is equal to gradient descent, oh my god, gradient descent, and we are going to give our x train data and then y train data, and then with this amount of learning rate alpha, and we are going to have 300 iterations. Okay, so now we get in so now we need to create the prediction. Okay, so the prediction is going to be, so we make a function called make prediction, and inside this make prediction we are going to have our input, our parameters, which is w1 and then p1 and then w2 and then p2, and then we are going to have we can ignore all this data, then just get the A2 because it is the basically the prediction, which is the last value of, not the last but the last layer inside of a neural networks, because that's the prediction, because that is where the prediction is coming out. Okay, so for the predictions, for the make prediction is going to be the forward prop, and then the w1 and then p1 and then w2 and then p2, and also the input of x, and we are going to input a single image or maybe a lot of image, we don't know, and then we're going to get the predictions value, which is get predictions, and then pass the a value, which is the prediction value. Okay, and then finally we can print our prediction using the f string, and then prediction is going to be prediction like that, and then we can return the prediction. Okay, so that is the making prediction. Now we need to test the prediction, and to test the prediction we need to have the index, and then w1 and then p1 and then w2 and then p2. Okay, now to create the prediction we need to have the current image, and the current image is going to have be x.test, which is index dot none, not dot none, but and then none, like this. And then we are going to have the prediction is not predictions, but prediction equal to make predictions, and then we are going to have our X test, which is the data test that we have, and then all of this data in the index and then into the none, like this. And then we have W1 and then P1 and then W2 and then P2, like that. So for the label, we are going to have Y underscore test, and then we pass the index, and then let's print the prediction. The prediction, not the prediction, but I'm going to create an F string. So the predictions is equal to prediction, and let's print using the F string the label that coming with that prediction, basically. Okay, and then we can return the label, return the prediction, and also return the current image. Okay, and then finally we can so that's the prediction, and then now this is the test part, and the test part is going to be for I in the range. So I'm going to use 3 random image. So basically I'm going to have my 3 image, and then getting into the forward propagation after we training the forward propagations, and then to see if the the neural network is working or not. And for I in range of 3, which is the 3 image that I want to predict, it's going to be a label and a prediction. I want to get the label, I want to get the prediction, I want to get the current image. Okay, and it's going to be test prediction, and of course I'm going to pass my index and also my W1 and then P1 and then W2 and then P2. And then for my current images, my current image, I want to reshape that image dot reshape into an 8x8 data, and then multiply that data by 255, because previously we normalize the data so that the data becomes between the value of 0 and 1, and then we and so I need to unnormalize that data by multiplying it by with 255, which is the standard value for the data set that has 8-bit value. Okay, and since the in the neural networks you will have your data get flattened out, so my data is actually inside of this so instead of this PKL data, I would have my not 8x8 but 64. Okay, because this 2-dimensional basically data, I flatten those 2-dimensional data into 1-dimensional data, so it's going to be 84 data amount instead of 8x8 dimension data. So, and then I will have my PLT dot gray, and then I would have my labels, and the label is going to be, well, it's going to be the A and then P and then C and then D and then E, oh my god, and then E, which is the category. Now if the label is not the same with the prediction in the index of 0, in the 0th index, mean the result is equal to wrong. Okay, else the result is going to be correct. like that. Now after that, I want to have my title is going to be the f string of so real is going to be the labels of label, which is the index, and then the prediction is going to be prediction in the 0th index, not predictions, but well, it's correct prediction, but the labels, and then it's going to be predictions of 0, and then I would have my result like that. Then I would have my VLT dot title as label is equal to title, and then I will have my plt dot image show to show the image, and it's going to be the current image, and also the interpolation is going to be nearest, and then finally I'm going to show that image using the plt dot show. Okay, and then yes, that's it. Okay, so now let's run this program, and then let's see what do we get. Okay, so also because it is a speed run, I'm not gonna lie, I just, well, basically speed running everything. So there's a couple of mistakes that I made, and I fixed all of those mistakes. And if you want to see the the implementations that I'm using, you can go into the video descriptions to see the correct implementations basically. So okay, so this is what I'm talking about, and this is 8x8 image, and apparently so the real value is E, and the prediction that our neural network has created is also telling us, hey, this is an E image, so the classification is correct. Okay, so remember we have 3 images that we pass into the neural networks, and then so this one is also, so the real value is B, and then the prediction is also B, so it's going to, so this one is also correct, and well, this one is also correct, which is D value. Okay, so that is what you're going to do. We are going to classify an image. Okay, and then that is like the most fundamental part of a computer vision, which is image classifications. And we are going to okay, so I'm going to explain to you about the basic of neural networks, and then including the mathematical aspect of neural networks in the next segment. Okay, so now we get into the recap version of our neural networks. So this is a very simple example of a neural networks. Here you have input layer, and then this is the first hidden layer, and then this is the second hidden layer, which is the activation function here basically, and then you get the input layer, which is the prediction of your neural networks. Alright, now let's get through this one by one. For the input layer, in our case we are using an image data, which is every neuron, every input layer here, which is the x1 and then x2 and then x3, basically represent the pixel that we have. So this is the first pixel, this is the second pixel, and this is the third pixel of one image that we have. So this is the a simple version of the input layer of input data that we have. So let's get into the first hidden layer. Now the hidden layer, we can have as much as neuron that we want. So here I have 4 neuron. So this is the first neuron, this is the second neuron, and then this is the third neuron, and this is the fourth neuron. Now again, this is like a parameters in neural networks, so you can have as much neuron as you want to have. And then we have the second hidden layer, which is, I'm gonna say this is kind of a distribution of a probabilities layer. So I'm going to talk about that later. And this is the output layer, which is the prediction layer for the neural net that we have. Okay, so let's focus into this part. Okay, let's focus into this part, this two first part. So in neural networks, in a fully connected neural networks, you want every input neuron to connect it to every neuron in a hidden layer, in your hidden layer. So the X1 going to connect it to the first neuron, the second neuron, the third neuron, and then the fourth neuron. And then for the second input and then the third input, you want to do the same thing, which is connected to every neuron that you have. So this is a simple one neuron representation. So here I have this, this input, which is x1, x2, x3, which is the same kind of input that we have here. And what happened inside of each neuron is that inside of every neuron is that we are going to apply the dot product between the weight and the input data, and then we add the bias value to it to get the value of z. And then after we get the value of z, we want to apply the non-linear activation function to get the value of a. And then we get, finally here we get, this output layer, this prediction layer. Okay, I want to do this. I want to show you this. Okay, you know what? I want to do this actually. Wait a second. Okay, so this is what happened. So this is the amount of images that we have, which is, this is the first images, this is the second images, and this is the third images. Now this is the image data that we are going to have. So this is a very simple image data. So this is x1, which is x1, this is x2, it is x2, this is x3 and x3. But here I want to have the n amount of a pixel of input data of an input neuron. So this is the images data, this is the input data that we have. Okay, and so in each neuron here, so which one is the neuron? I'm sorry. Okay, so the question, which one is the neuron? Well, the neuron is the row, each row of this matrix. So this is the first neuron, this is the second neuron, this is the third neuron, and then this is the fifth neuron. Okay, so this in a row we have the weight value, and then in the column we have the amount of neuron that we have. So this is the amount of neuron, which is 5. So we have 5 neuron, and then the 5 weight value, and the weight value needs to match out the amount of image pixel, because we want to connect every input with every neuron here. So we need to match the amount of the weight with the amount of a pixel in one images on every single one images. So for example, if I have 64 pixel in one images, which means I'm going to have x1, x2, x3 and x64. Okay, and in the weight value I'm going to have W1, W2, W3 until W64, which is the amount of input that we have, to match out the amount of input that we have. Okay, so why do we do that? Well, again, I want to show you this. Wait a second, give me a second. Okay. Okay, so this, to get the z value here, okay, to get the z value here, I need to perform the dot product between the weight and the input. And to apply the weight and the input, we need to match out, we need to kind of match the dimension, because we are going to apply the matrix multiplications. If you remember the matrix multiplications, we need to match the amount of column and the amount of row. So here I have okay, a quick guess. What is the dimension for this input? So this is the input, which is here x1, x2, x3. So this is the input x1, x2, x3, and this is the amount of neuron that I have, which is 4, which is here f4. So now I have the input, which is 3 by 1. Okay, 3 by 1, and I want to apply the dot product between the 3 by 1 of a shape matrix into the 4th by 3 of an input of a matrix, which is the weight matrix. So again, you need to match the column and the row to perform the matrix multiplications. Again, I have to go back to the example here. Okay. Okay. So we got to apply the matrix multiplication to get the dot product. Here so this is the first image. Okay. Apply the dot product, the first image, to every neuron here. So apply the dot product between the image and then to every neuron here, which is x1 times w1, x2 times w2, and then to get and sums up all of those number, you get s1. Okay. Now you apply the same thing, x1 times w1 on the second neuron, x2 times w2 and the second neuron. You sum up all of those values to get the s value here, which is here that I wrote. So you sum up the element-wise matrix multiplications between the weight and the input of element-wise, and then you apply the b plus b. So here to get the z value, so the p amount needs to match up with the amount of neuron. So we have 5 amount of neuron here, which means you are going to need 5 amount of bias value for each neuron that you are going to have. So let me show wait a second. So this is another example again. To get the z value, which is this z value, we need to apply the dot product between the weight and the input plus the bias value, which is here, and then we get the z value here. And then after we get the z, we need to apply the z value into a non-linear activation functions, which is here. And then we get the a value, which is I wrote here. The a value is the non-linear value of z. We'll get into the non-linear activation function later. Okay. Now, okay, so this is what happened. So this is the formula, and this is the mathematical representation of this. So you have the weight, and then you have the input, and then you have the bias for every neuron that you have, and then you get the z for one images. You can see this is for one images. Okay, and then you apply the activations to get the a value, to get this value. So after you get z, you applied all of the z in your first layer to get this amount of z. So this is the z in the first layer, which is this is the hidden layer, and then you apply the non-linear activation function to all of this layer, which is this. So this is the z1, z2, and z3, and z4. Okay, and then you apply a non-linear activation function to every element in here, which is z1. Okay, and then you get this amount of a1. So a1 here is a activation value in the first layer. Now this one amount is basically the amount of input data that you are going to have. Like for example, if you have 10,000 data, which means you are going to have 10,000 of activation functions amount. So this is the first data in the activation functions. So basically in the mathematical representations, this is what we have. We have z. To get z, you need to apply the w times the input plus the bias to get the z, and then to get the a, you need to apply the non-linear activation functions. Okay, and so this, okay, this 2 is basically the mathematical representation of this 2. Okay, and this is basically just like if you have another hidden layer. So for example, if you have another hidden layer with the amount of maybe 5 neurons, you are going to have this kind of value. So the input is not x anymore. The input become the output of the first neuron, which is the a. Okay, and then you apply the same kind of calculations to get the z for the second layer, and then you can apply the same kind of calculations to get the a for the second hidden layer. Okay, now I mentioned a lot about activation function, but I haven't explained what activation function I need to apply to those values. So in neural network, actually there's a lot of activation functions. So here's the some of the most popular that a lot of people use. So first we have a sigmoid activation function. Basically we are applying a non-linear function into the output of our linear function, because this is just a matrix multiplication, which means we have a linear output. So we need to apply the non-linear activation functions to get the non-linear output. Now we have a sigmoid. So the sigmoid formula is 1 divided by 1 plus e to the power of -2. I'm sorry, to the negative of z. Z here is here, which is the output between the weight and the dot product between the weight and the input plus the bias. Okay, so this is z value, and then you have a 10h value, which is e to the power of z negative to the e to the power of -z divided by e to the power of -z plus e to the power of -z. This is the 10h value, and this is the Rayleigh value, which you are going to get the maximum value between. So it is basic. So in Rayleigh, you are going to get, for example, if you input number 7, I'm sorry, everything that negative number, you are going to get a 0 value, and then for the positive number you get the positive number itself. And then you have leaky value, which is kind of a leaky-ish kind of a value, which if you get a negative number, you multiply those number with 0.01, and then if you get positive number, you are going to get, well, the same number. I'm going to explain more about all of this in a coding part. Okay, now you're probably wondering why non-linear, why we are applying an activation function, why we are using activation functions, why we apply a non-linear activations inside our neural nets. Why we are applying? So this is the basic linear function formula that we get in high school. So this is y equal to mx plus b, which is very similar to neural nets, right? In neural nets, we have the weight and the bias. So here, this is very similar. So this is the input mx plus b. It's very similar. You just need to replace the m with the weight, and then x is the input plus the bias value, while the y value is basically the z value for our neural nets. Okay, why do we using a nonlinear function? Well, the answer is because it's for us to get a universal approximator. Okay, so what do I mean by universal approximator? It is basically we want to have an approximator that can classify any kind of data, any kind of complex data. So when we only have a linear function, we can only do a regression kind of a classifications. So we cannot do very complex kind of classification using only a linear function. Okay, now I want to explain that in a more detail. So remember, wait a minute, give me a minute, give me a second. Okay, so if you remember our here, so here. Okay, now for example, I have two input, which is x1 and x2, and I have the weight, just weight 1 and weight 2, and then apply the bias value, which is this is pi 1 and then pi 2, and then I have the y1 and then y2, which is basically the same kind of calculation. So you can imagine the y1 and the y2 as a z value. Okay, but what we get after we do all of those calculations, so let's break down all of these calculations. Okay, let's focus on here. Okay, I want to do this. Okay, okay, let's find the y1 and then the y2 value. So just like in the neural networks, the W is basically the weight, and this is a random value. Let's say I have a random value of 2, and then the bias is also a random value, and let's say I have 1 here as a random value, and X is the input. So this is the input list that I have, which is -1, 0, 1, and 2. Okay, so for example, if I have a 2 as the random value for the weight, I'm going to just calculate all of this. So for example, for the first input of X, which means I'm going to have 2 times -1 plus 1, and I have -1. And then for the second input, which is 0, I'm going to have 2 times 0 plus 1, and then I have 1. And then for the next input, I'm going to have 1, which is I'm going to have 2 times 1 plus 1, which is I'm going to have 3. And then for the next input, I'm going to have 2 as for my value input, which means I'm going to have 2 times 2 plus 1, which means I have 5 value. And I want to draw the graph of those distributions, which I have this linear function, this linear line. Okay, so this is the linear function that we have for y1, which is this one, this y1. Okay, now what about the y2 here? Well, I'm going to use a different kind of a random value for the w1, and then for the p1 I'm going to use the same value, and for the input value I'm going to have the same kind of input value, which is -1, 0, 1, and then 2, and then do the same kind of a calculations like what we did here, which is if my input is -1, I'm going to have -3. If my input is 0, I'm going to have 1 for the output. If my input is 1, I'm going to have 5 for the output, using this kind of function. And again, I'm going to get a linear functions. So this is the y2 linear function, which is for these functions here. So this y1, this linear line is for here, and then this y2 here is going to be here. Now I want to apply a non-linearity to both of this value, so let's do that. Okay, here I'm going to combine the two value. Give me a minute. Okay, so this is the function that we have, the linear function that we have. Okay, I want to combine those two linear functions, and then I want to get the non-linearity value for those two functions. In this case, I'm going to use a ReLU non-linearity. So in ReLU, if I have a positive number, I'll get this positive number, but if I have a negative number, I'm going to force those negative number into a 0 value. So all of this negative number, I'm going to force all of the negative number into a 0 value. So we have this kind of a distributions right now. Okay, now why do I combine these two nonlinearity? Okay, this is a very simple example that I can give you. So we have two nonlinear line. We have two linear line, for example, and then we apply the nonlinear function and combine it. Now, first of all, if we are using a ReLU function, which means this part is gone, right? This part is gone. And if we combine this part and then this part, we are going to get this kind of a non-linearity. Okay, and again, this is only two non-linear example. We only use two nonlinearity neuron. Okay, imagine you have so many neuron, you have so many non-linear function, you are going to get this kind of function. So this is the first two. So if you have two non-linearity function, you get this kind of a non-linearity. But if you have a lot of non-linearity function, you can get this kind of distribution, which kind of a non-linear, and in neural network it would kind of match your data. Okay, I know what you're thinking. I still don't understand about all of this. Okay, I'm going to show you a very unique example. Okay, so in nonlinear, so you can go to playground.tensorflow.org. Here I have these data distributions. Okay, these data distributions. Now let's classify these data distributions using one hidden layer. So you can play with the hidden layer, the amount of hidden layer, and then you can play with the amount of neuron here. So let's say I have one neuron and one hidden layer. Can it classify this kind of distributions? Okay, so let's start. Okay, this is what you have when you only have one kind of a distributions, one kind of a neuron work, which is I want to show you. Okay, imagine you only has one of these distributions of this function, which is what you get here. And it can classify a very simple data distributions. But the question is, can it classify a more complex data? Like for example, I have this kind of data distributions. Can it classify this kind of a data? Well, let's see. Well, and the answer is, unfortunately, it can't. Because it's too simple. You cannot classify a complex data when you have a very simple kind of a function. So what do we need? Let's stop this simulation. Okay, let's add a neuron. So in our example, we have two neurons, right? We have the y1 here, we have the y1, and then we have the y2, which is, this is one neuron, and then this is the second neuron, the first neuron, the second neuron. Okay, so now let's try to classify this kind of data distributions using the same kind of architecture that we have. So let's start to classify. Okay, so now it is trying to classify in a much better kind of classification, but still it can't really classified in a perfect manner, because we only have two. So this is the first non-linearity and this is the second non-linearity, so it combines those two non-linear function, and then we get this kind of non-linear function, just like what we did in our example here. We combine a linear function, and then we applied a value to get a non-linearity function, and those non-linearity with those two non-linear function, we combine the two non-linear function, but still we have a very simple non-linear function. We want more complex function. So now let's add more non-linearity to it. So let's have 4 neurons. Okay, why do I use 4 neurons? Because remember in our example I have I have 4 non-linearity function here, which is 4 neuron here. So let's use this as an example. We have 4 neurons. So let's classify this. Okay, so it is perfectly classified the data distributions, because it is combining this and this and this and this to create much more complex non-linearity. So that's why we are using a non-linear activation function. When you only combining a linear function, you still have this not a good kind of a function. You need to have a non-linearity to it, so you can get this kind of non-linearity for your architecture. Now let's have much more complex data. So this is more complex data. Let's see if we can classify this data. Okay, so it can classify this data. Now let's use much more complex data. Let's say we still have 4 neurons and then 1 hidden layer. Okay, let's try to simulate this. Well, unfortunately, it looks like we can't classify this kind of data distributions, because the data distribution is too complex for our non-linearity combinations. So we have this function, we have this function, we have this function, and we also have this function. When we combine all of those functions, we still cannot get the perfect kind of a classification that we want. We cannot have the perfect classification approximator that we want. Again, and this is why neural net is a universal approximator, because you have the freedom to add the amount of hidden layer, and then you can have the freedom to add the amount of neuron. So let's go back to our simulation. Let's stop the simulation. In neural networks, you not only able to add the amount of neuron, you also able to add the amount of hidden layer. So let's use 3 hidden layer, and then let's use, I don't know. So in the first layer we have 4 neuron. In the second layer we have 4 neuron, and then in the third layer, hidden layer, we have 3 neurons. So the idea is that we want to have as much of a non-linearity function, and then we want to combine all of those non-linearity functions to get much more complex of a non-linearity functions, which is what I'm talking about here. When we only have two non-linearity functions, we still have a very simple function. But when we have many non-linear functions, we can have a very complex non-linear function. Hence, we can classify a much complex kind of a data distributions like this. So let's try to simulate this, and let's see. Okay, so can it okay, so this is what I'm talking about when in neural net, when I give you this example, you know that the function is kind of a changing of a shape, because it's not just combination of a non-linear function, but it is also the effect. It is also got affected by the amount of the weight value. So let me go back. Okay, let me go back here. Okay. So remember when I have the W1 and then W2 as a random value. So in neural network, these two value is also changing. Hence, it's not going to be output this kind of a distribution all the time. The distribution output is going to change because the W1 and then P1 and then the W2 and P2 is also changing, which means we are going to get much more of a complex linear function. In this case, as we can see, this is a more complex data, and the blue, if you look at the blue, it classified the blue in this circular way. So it classified the blue here. It is not a perfect because we have a very simple kind of a neural network here. And then the orange one, it is also like trying to match with the orange data here. So what's happening here? So we have in the first layer, we have this kind of a distribution in the first neuron. In the second neuron, we have this kind of distribution. In the third neuron, we have this kind of distribution. And then in the fourth neuron, we have this kind of distributions. And then we want to combine all of the distributions. And in the second hidden layer, we have this kind of distributions for this input distributions as an input. And then we have this kind of distributions. We have this kind of distributions. And we also have this kind of distributions. Again, as you can see, this is the simple distribution because it is like a very linear distribution. But when we get into the second layer, it is not a linear distribution again. It became a triangular shape of a distribution. It is not even a triangular shape in this third neuron. And then when we get into the last neuron, it becomes a much more of a complex non-linearity functions. And you can see this kind of distributions, and when we combine this kind of distributions, this distribution and this distributions, and then this kind of distributions, we get this kind of distributions, which is pretty much classify this very complex kind of data distributions. And that's why we are using a non-linear activation function, and that's why a neural network is a universal approximator, because it can classify a very complex dataset. Okay, now I would like to explain about the softmax activation function. Now, the softmax activation function is kind of a different non-linear function compared to the ReLU, leaky ReLU, tanh, and sigmoid, because softmax activation function, the output of the softmax activation function is going to be like a probability distributions. So in a lot of cases for the neural network, softmax activation function is going to get used in the very last hidden layer inside of a neural networks. So this is the softmax activation function for one image. So I have this example. So let's say the neural network predicted the images, and this is the value, the random value that they are outputting. Again, this is a random value just for the sake of intuition, just for the sake of for us to learn to understand about the softmax. Now, for example, I have 5, 2, -1, and 3. So you are going to compare this with the one hot encoding label. So in this case, we are going to have 4 label, 4 kind of category inside of a one label, right? So for example, if the correct category is in the second index, the one hot encoding part will be 0, 1, 0, and 0. So we are going to get the value of the probability distributions, so we can compare this distribution with the one hot encoding label. Now this is the softmax activation functions formula, where you have e to the power of x of each index, and then divided by the sum of the e for every index. So for example, this is the formula that I calculated using this formula. This is the calculations. So for example, in the first index we have 5, so we calculate the e of 5 divided by the sum of e to the power of 5 plus e to the power of 2 plus the e to the power of -1 plus e to the power of 3, and then we get 0.842, and then we do the same thing with the second index, where e to the power of 2 divided by the sum of the e in every on this bracket, in this value. So e to the power of 5 plus e to the power of 2 plus e to the power of -1 plus e to the power of 3. And then we do the same thing with the e to the power of -1 and e to the power of -3, which is the third and then the fourth index. And we get these probability distributions. We have in the first index we have 0.842, and then in the second index we have 0.041, in the third index we have 0.002, and then in the third index we have 0.113. And if you sums up all of this number, okay, you will get 1, which is that's why we are using softmax probability distribution. So it is actually keeping the value, so that is actually kind of a like a really nice distributions, because when you sums up all of those value distributions, you get the value of 1. Okay, now when we have all of these distributions, what we are going to do with it? Okay, what we are going to do with this distribution is that we are going to calculate the loss for each images. Okay, let me arrange this. Give me a minute. Okay, so there are two types of loss function that I want to mention. So first of all, the most simple function or loss function is the MSE, which means mean squared error. So I would like to mention that wait a second. Okay, I would like to mention about the loss function and the cost function. The loss function is basically the value that you get of the error for one images. Now the cost function is actually the value that you get for the entire dataset. So for example, if you have 10,000 dataset, so you are going to have a loss value of a 10,000 value, but you are going to have one cost value, which is the sums up of all of those 10,000 value. Okay, so that is the difference between loss function and the cost function. Okay, now in the mean squared error, which is you just need to subtract the prediction and the label and then the prediction. Now the label is the one hot encoding label subtracted by the prediction by the softmax. So this is the prediction value, which is done by softmax activation function, and this is how you can calculate the loss for your images, for your one single images. And then the result of those subtraction, you squared up those value, and so this is the sum. So n is the amount of data, and then y is the true I is the true label, and then y hat is the prediction, which is the output from the softmax activation function, softmax probability distributions. Another loss function that I would like to mention is the negative log likelihood. So the negative log likelihood is very good loss function that calculate a categorical kind of a problem. So when you have a lot of classification, like for example you have 10 class for one problem, just like what we have in MNIST Dataset, we have 10 class, which is an images from 1 through 10. Using a negative log likelihood, it is much better than using the mean squared error loss. So what happened in the negative log likelihood is that so here we are going to have the probability distribution from the input and from the label, which is the softmax activation function here. Okay, which is from the softmax here. Okay, and we need to find the log of the capital P of m, which is the amount of data. So the capital of P is basically the sum, but instead of addition, it's going to apply the multiplications. Okay, so log P labels in a training set is going to be log capital Pi of m, which is the probability for the label, the true label, and then the input label. So the log of p is basically the loss, okay, the log of this, the probability here is basically this, the negative log of the prediction with the true value. So when you apply this kind of a probability, the log value between these two, you actually going to get a negative value. But as you know, in a loss function, the smaller number that we get means that the better our neural networks works. So we need to inverse the negative value into a positive value, and so to do that we just need to multiply this loss between the prediction and then the true label with the negative value here. And this is why it's called the negative log likelihood, because if you are only using the log likelihood, you are going to get a negative value. So you want to inverse those negative value into a positive value, and so you just need to multiply it with the positive value, and this is what we get. So this is the loss. You can also write it like this with the amount of data. So the negative value of every amount of data, every amount of the loss between the prediction and then the true label. Now all of this is going to make sense when we get to the coding part, which is in the next segment. So if you don't understand it, don't worry about it, because again, this is all going to make sense when we get into the programming part in the next segment. Okay, here I have the cost function version for the negative log likelihood and then the mean square error. Again, the cost function is basically a single value for our entire dataset. So this n is the amount of data. So in order to get one value, you just need to divide all of the value with the amount of data that you have. Okay, I would like to mention in the negative log likelihood. So okay, J is the notation you using when you trying to find the cost function. Okay, so this is A. As you can see, this is A. As for the softmax, and as you can see here, I write it like this. So this is the loss value for one image. So this is one images, right? So this is only one images, and when we get here the entire formula for the cost function, we get the entire dataset. So again, this is the softmax output for the prediction, which is the prediction that we have. Again, this is probably doesn't make any sense, but when we get to the programming part, I hope it's all makes sense. All right, now I would like to explain a little bit about derivative, at least the intuitions behind derivative, because we are going to use this a lot in the neural networks. So imagine I have this kind of a function, which is f of a, function of f of a equal to 3 times a. Okay, So the function f of a is equal to 3 times a. Now if I have a in the coordinates of 2, how much the slope or the derivative in this direction, in this coordinates of 2. So to find the coordinates, to find the derivative value, I have these calculations. So if a is equal to 2, then f of a is equal to 6, because again f of a is 3 times a, which means 3 times 2, which we have 6. Now we cannot calculate a slope of something using only one coordinates. We need at least 2 coordinates, and that's why in a derivative you move just slightly your value. So here I'm moving the value of a, the value of these 2 slightly to the right. I'm moving with the very small number, which is 0.001. It is a very small number. So I'm going to calculate how much a in the coordinates of 2.001. Now a to the power a, when a is equal to 2 to the point of 001, then the function of a is going to be 6 to the power 6.003, because the f of a is equal to 3 times a, which means I'm going to have 3 times 2.001, and we have this, which is 6.003. So to find the slope or the derivative of f of a at the coordinates of a, which is in this case is 2 here, we need to calculate the height divided by the width. So here you can actually draw a triangle here, and by using this triangle, so this is the height and this is the width, which is the width is the amount of how much we are moving the value of a, which is the value of the second coordinates that we have, and the height is the value of how much the new coordinates. So the slope or the derivative of f of a at a equal to 2 is 3, because when you divided the height and the width of this triangle here, you get 3. Okay, so in conclusion, the slope value of this line here is 3, and for this particular line, for this particular function f of a, every coordinates, whether in the 1, whether in the 2, whether in the 3, 4, 1 trillion, 1 bajillion, everything, the slope value is 3. Okay, because this is such a straight line, so the slope value is always the same in every coordinates. Okay, now what happened when we have curve of a function? Now doing the same thing with what we did here, but now the functions became 8 squared. Now do the same calculation. If a is equal to 2, then the f of a is 4, because 2 to the power of 2 is 4. And if I'm going to move slightly to the right, and I would get a equal to 2.001, then the f of a is around 4.004. So the slope of f of a at a equal to 2 is 4. Now the question is, what if I'm moving the direction of my coordinates, like for example here? So instead of 2, what if I have 5? Is it still going to be 4 for the slope value, or is it going to be different? So let's find out. Okay, so this is the same kind of slope, the same kind of a function that I have here. Here is the same function I have here, but instead of using this 2 coordinates, I'm using 5 coordinates. Now, using the same kind of calculation, so f of x is equal to a squared. Okay, so if a is equal to 5, then f of a is equal to 25, because a squared is 25. And again, I'm moving the coordinates slightly to the right. So now I would have, if a is equal to 5.001, then the f of a is equal to 25.010. And so when you divide the width and the height, you will get a different slope. You will get a different derivative. The slope of f of a at a is equal to 5 is actually 10 instead of 4, because when you divided the width and the height between these 2 coordinates, when you have the coordinates of 2, the width and the height of the triangle is actually kind of different. As you can see, this triangle is kind of a more wider, while this triangle is more kind of a taller triangle. So it is a very different triangle. So it is kind of makes sense if the slope is different, which means in terms of this kind of curvy line, in every direction, in every in every coordinates, we are going to have a different kind of a slope value compared to this kind of line. So in this kind of line, in every coordinates, we have the same kind of a value of a slope. But here, because we have different kind of a triangle, okay, we have different kind of a slope value, because the slope of a at a is equal to 2 is 4, while the slope of a at a is equal to 5 is 10, which is a very different which is a very different value. And as you can see, it's more, and as you can see, this is way more makes sense, because this slope is less curvy compared to this slope. And so I would like to also, this is where we get the formula for in a high school mathematical of the derivative. So if you remember in high school math, the derivative of a squared is equal to 2 times a, because this is the formula that they give you, which is if you have a, this is the n of a to the power of n subtracted by 1. So in high school, when you have x to the power of 3, the derivative value of this function is 3 times x to the power of 2, which is you move the 3 to the front, and then you subtract this value of 3 with 1, which is you have 2. And then you also have, the same thing happen with x to the power of 4, which is you are going to get 4 times x to the power of 3. So another example, if for example, like you have, I don't know, 7 times x to the power of 3, for example, the derivative value of that function is 21 times x to the power of 2, right? So that is the high school math that they're teaching you. And the reason why this value is changing is because this on each value, on each coordinates, it has a different kind of slope, and that's why on every coordinates, in every coordinates you have a different kind of slope. And this is why this is where this formula came from. This formula is coming from this kind of a reason. So this is the reason why this high school formula exists for the derivative. So I know that a lot of teachers in high school is not explaining why we get this kind of formula, and so I want to this is why I'm explaining the concept of a derivative here, because a lot of high school teacher is not explaining why we are using this kind of formula. They just giving us, okay, this is the formula to calculate the derivative for for us, but they never explain why we get this kind of a formula, and this kind of formula is coming from this, basically. Okay, in order for us to understand about the backpropagation in neural networks, first of all we need to understand about a concept in calculus called chain rule. And to understand a chain rule, I'll give you a concept, and it is something called computation graph. Now I have an example of a simple computation graph. Here I have a function of j. So a j function is sometimes in neural networks it is also called an error function or a loss function or the cost function of j. So j has a 3 value, which is a, b, and c. Now the function itself is 3 times a plus b times c. Now we can simplify this formula. P times c, we use u to represent p times c, and we are using phi to represent a times u, which is p times c. And this is the entire formula for this function. So u is equal to p plus b multiplied by c, phi is equal to a plus u, and j, the cost itself, is equal to 3 times v. Now this is the graph that I'm talking about. So here, am I talking too fast? I think I'm talking too fast. Okay, so here I have a is equal to 5. Just for the example, this is a random number, and p is equal to 3 and c is equal to 2. Now you can see this as an input, and as you can see, this is like a simple version of a neural net. So this is, you can see it as an input value, and this is just a random value. Okay. Now p times c here is equal to u. So here u is equal to p times c, which is 3 multiplied by 2, and it's 6. Now we have a plus u. Here we have v is equal to a plus u, and it is 5 plus 6, and we have 11. And now finally we have the j value, which is the cost function or the output function for this simple graph, and it is 3 multiplied by v, and here v is 11, so j value is 33. Now, the chain rule in calculus is basically we are going to find the relationship between all of this value. So what is the relationship between j and v, and what is the relationship between v and a? Something similar with v and u, and what is the relationship between u and b, between u and c, etc., etc. So this is the mathematical notation. What is the derivative of j with respect of v? So what does this notation mean? It means that how much j value got affected by the v value, or how much v value affecting the j value here. So let's apply a simple derivative to here. So if j is equal to 33, right, if v is equal to 11 here, then j is 3 times 11, okay, because j is 3 times v here, and we have 33. Now let's move the coordinate of v a little bit, slightly, which is 0.001, and now we have 11.001. Now j is equal to 3 times 11.001, and now we have 33.003. So what does this mean? It means that the slope of j when v is 11 is 3, because if I move v by 1, it affecting 3 times of a value of j. So the derivative of j with respect of v is 3, because this is how much the value of j got affected by the value of v. So the value of v affecting 3 times of the value of j. Now, in neural networks, we want to find the relationship between, wait a second, I'm gonna do this. If you remember, in neural networks, we actually want to find the relationship between the output value and the hidden layer value, because in the hidden layer value you have the weight and the bias, and the weighted bias is a random value, just like what we have in this simple computation graph in A, B, and C. This is a random value that affecting the value of V, affecting the value of U, and it also affecting the output, which is the J value. Similar with a neural net, we have the value of W and the value of P, affecting the value of the output layer, which is the prediction itself. So now we obviously want to find, okay, how much this value got affected by W and P. Now, similar to here, we want to find how much J value, which is the output, got affected by the input value, which is A, B, and C. So for example, we need to find how much J got affected by the value of A, how much J got affected by the value of B, and how much J got affected by the value of C. So those are the three relationships between the output and the input, and this is the chain rule example. this is a simple example of a chain rule where you have how much j value got affected by a. Okay, and to find the value of this, value, we need to find how much j got affected by v, because v got affected by the value of a and v affecting the value of j. So we need to find how much j got affected by v, and then after that we get to find the value, how much the value of a got affected by how much the value of v got affected by the value of a. And that is called the chain rule, where to get how much j got affected the value of a, we need to find how much j got affected by the value of v and how much v got affected by the value of a. And I'm sorry, this is a mistake. This is supposed to be a multiplication, not an equal sign. So this is a simple recap to get the derivative of j with respect of a, which is how much the value of j got affected by a. We need to know that a affecting v and v affecting j. So this is the simple graph for these equations. Now I want to show you another example. Okay. Wait a minute. Okay, I'll find it. Now, here I have another computation graph. Now, this is the input. Okay, so this is the input. I have a with the value of 3, I have b with the value of 1, and I also have c with the value of -2. So this value is a random number, okay, just like what we have when we initialize neural networks to get through the first iteration. Okay, so this is the random value, and I have a d variable which is 2 multiplied by b. So b is 1, so 2 multiplied by 1 is 2, and I'll also have e is equal to d plus a. So now d is 2 and a is 3, so 2 plus 5 is 2 plus 3 is 5. I'm sorry. Okay, so now I have the L value, which is the loss value. So again, this is like a simple neural network. So this is the input and this is the output. So here I have L value, which is the loss value, is equal to C times E. And C times E is -10 because C is -2 and E is 5. So this is the formula, which is the L function, the loss function of ABC is equal to C multiplied by the value of A plus 2 multiplied by B. So now the job is, let's find how much the loss value got affected by the A value, which is the input value. How much the output of L value got affected by the input B. How much the output L got affected by the input C. And this is the notation. The derivative of L with respect of A, which is how much L got affected by A. The derivative of L with respect by B, which is how much L got affected by B, and the derivative of L with respect of C. Here, how much L got affected by the value of C. Okay, I want to mention a little bit about a chain rule. So this is a simple explanation of a chain rule. Here I have the function of f of x, and here I have a u variable. Now u variable affecting the variable of v, and the variable of v affecting the variable of x. So now the chain rules become, if I want to find the derivative of f of x, I need to find the derivative of u with respect of v and the derivative of v with respect of x, because x here and here got affected by the value of v here. So x got affected by the value of v, right? And the value of v got affected by the value of u here. And the value of u is going to affecting the value of f of x. Again, I have another example. The function of f of x is equal to u affecting, I'm gonna reverse the order. I have x got affected by the value of w, and the value of w got affected by the value of v, and the value of v got affected by the value of u. So if I want to find how much f got affected by x, I need to go through how much u got affected by v here. The derivative of u with respect of v multiplied by how much the derivative of v got affected by the w. Here I have the derivative of v with respect of w multiplied by how much w got affected by x. Here I have the derivative of w with respect of x. Now again, let's find this value using the chain rule effect. Wait a second, I want to do this. Okay. Okay, here. Alright, now, so this is the formula that we have here, right? So d is equal to multiplied by b, which is here. D is equal to 2 multiplied by b, and I have e is equal to a plus d, which is e is equal to d plus a, and I have the loss L, which is c got multiplied by e here. L is c multiplied by e. So in order to find the relationship between all of this, is that we need to find how much L got affected by the value of c. Okay, how much L? Okay, let's go from the bottom and moving up. Let's go from the bottom here. So how much the value of L, got affected by c? Well, whatever value e is, which is here, if I have, for example, if I have e is equal to 6, well, the value of c is going to affect the value of L by 6 times amount of c. Again, does that make sense? Again, so you can write the amount of value of L got affected by the value of c is equal to e, because whatever value e is, it will affecting the value of c. The value of c in order to get the value of L. So the value of L is going to get affected by the value of c. Like for example, in this example, 5 times the value of c, because the value of c is -2, right? So if I have L is equal to -10, well, then how much the value of c affecting the value of L? Well, the answer is 5. Does that make sense? So we are not trying to find, okay, how much this value got multiplied by this value, okay, or how much this value got added by this value. No, we are not trying to find those kind of value. We're trying to find how much this value got affected by this value. Okay, see, I want you to really digest what I mean by that. How much L value got affected by E value. So now I can write the formula. So the derivative of L with respect of C is equal to E. And I can also write the derivative of E is equal to C, which is the same thing with this formula. Okay. Now, let's find how much A here, A affecting the value of L here, affecting the value of loss. So using the chain rule, in order to find A, well, A affecting the value of E and E affecting the value of L here. So the chain rule effect is the derivative of L with respect of A is equal to the derivative of L with respect of E, because E affecting the value of L multiplied by the derivative of E with respect of A, because A affecting the value of E and E affecting the value of L. Okay, so now let's find the derivative of L with P, which is the relationship between L and P. How much L got affected by P? Well, here's the chain rule effect. So the derivative of L with respect of P is equal to the derivative of L with respect of E. Okay, why is that? Well, here's I have P here, and P affecting the value of E. I'm sorry, I messed up. So here I have L. L got affected by the value of E. Okay, and the value of E here got affected by the value of D here, and the value of D got affected by the value of P. Similar with here, with this, the value of L got affected by the value of E, and the value of E got affected here, this line here, this tiny line, got affected by the value of D, and the value of D got affected by the value of P. And so this is why the derivative of L with respect of P is the derivative of L with respect of E, because E changed the value of L, multiplied by the derivative of E with respect of D, because D affecting the value of E here, and the derivative of D with respect of P, because D got affected by the value of P. So now here's the formula that we have. So again, the loss here, L is equal to C multiplied by E, becomes the derivative of L with respect of E is equal to C. The same thing with the derivative of L with respect of C is equal to E. Again, it is the same thing, because think about it. The value of L got how much the value of L got affected by the value of C. Well, it's whatever E is. Okay. Similar with how much L got affected by E. Well, it is how much C is. Okay. Now we also have. We also have here E is equal to A plus D here. So the formula become the derivative of E with respect of A is equal to 1. And the derivative of A with respect of D is also equal to 1. Because if you think about it, whatever how much the value of A affecting the value of E, it is how much the value of D is cut multiplied by 1. Like, so for example, if I have the value of A is equal to 10, for example, well, how much the value of E then? Well, it is whatever the value, well, it is the same value. It became the same value. Because, again, it's not that we found how much D affecting E. We try to find how much A affecting L, okay? So let's forget about D. So if I have A is equal to 10, how much E? Well, E is equal to 10 because A is 10. And how much, if I have the value of A is equal to 11, how much the value of E? Well, the value of E is also 11. So A affecting E with one value. So if A changing by 1, A is also changing by 1. Similar with the derivative of E with respect of D. Okay, the same concept is also could apply here. Because let's forget about A here, because we want to find how the relationship between L and D. Let's forget about A for a second. So again, if I have D is equal to 5, how much E? Well, E is also 5. So and if I have D is equal to 6, for example, how much the value of E? Well, the value of E is also going to be 6. So it affecting by one value because it has a similar value regardless. So the value of E got affected by D is 1. Okay. Now for D, D is equal to 2 multiplied by B. Okay. Now we can write the derivative of D with respect of B is equal to 2 here. Okay, because if I have, for example, if I have 6 for B, how much is D? Well, D is 12 because it is because the value of B because the value of D got affected twice amount of B here. It got the value of D got affected twice amount by the value of B here, twice amount the value of B, and that's why the derivative of D with respect of B, which is how much D got affected by B, is equal to 2. Okay, so I redraw this computation graph into here. So this is the chain rule effect. Okay, this is the chain rule effect for this computation graph. Again, we want to find how much L got affected by A, how much the output L, oh my god, okay, how much the output L got affected by the input A here, and how much the output L got affected by the input B here, and how much the output L got affected by the input C. So we need to find the chain rule. Okay, so first of all, in order to find how much L got affected by A, let's apply the chain rule. So again, so how much L got affected by L? First of all, how much L got affected by L? Well, it's 1 because L is equal to L, so it's 1. So the derivative of L with respect of L is 1 here. Okay, now in order for L to go to A, we need to find the relationship between L and E. Okay, so how much E affecting the value of L, or how much L got affected by the value of E, which is how much the derivative of L with respect of E. Well, we have the answer, and the answer is here. The value of E here, and the answer is whatever C value is. Now in our case, C is equal to -2, so the derivative of L with respect of E is equal to -2. Okay, because again, the derivative of L with respect of E is equal to -2, which is C, which is here. The formula here got applied here, and which is the value of -2 is coming from here. It's coming from here. Okay. Now, okay, we find the relationship between L and E. Now let's find the relationship between E and A. So what is the relationship between A and A? How much E got affected by A, or how much A affecting the value of E, or how much the derivative of E with respect of A. Well, the derivative of E with respect of A is equal to 1. So the relationship between these two connection between these two values is equal to 1. Okay, now what is the formula for us to get the derivative of L with respect of A? Well, it is the multiply value between the derivative of L with respect of E multiplied by the derivative of E with respect of A. So how much L and E? Well, this -2. So -2 multiplied by E with respect of A. And how much is that? It's 1. So it's -2 times 1, and we have -2. So the relationship, so A affecting the value of L by -2 amount of a value. Okay, so we found the answer, and the answer for here, this question, is -2. Let's find another question, another example. So let's find, okay, so this one, the obvious answer. Okay, let's find this one. How much L got affected by C? How much the derivative of L with respect of C? Well, the derivative of L with respect of C is equal to E, and in this case E is equal to 5. So the derivative of L with respect of C is equal to 5, and that's the answer for our question here. So here we have the derivative of L with respect of A, which is -2, and we also have found the answer for the derivative of L with respect of C, which is 5. Now the last question is how much L got affected by the value of P. Well, here we need to find the value of the derivative of L with respect of E, and the derivative of E with respect of T, and then we need to find the value of the derivative of T with respect of P. So let's go through those values. Okay, so we already found this value, this relationship value, which is the derivative of L with respect of E, which is -2. So here we have -2. Here this is -2. Okay, how much E got affected by D? Well, how much the derivative of e with respect of t? Well, the answer is here. The derivative of e got affected, the derivative of e with respect of t is equal to 1. So here is 1. So the derivative of e with respect of t is equal to 1. Okay. Now, how much the derivative of t with respect of p, because t got affected by the value of p, and we found those questions here. We found that question answer here. The derivative of t with respect of p is equal to 2. So here I'm writing the derivative of t with respect of p is equal to 2. So the derivative of L with respect of E is equal to -2, and the multiplied by the derivative of E with respect of t, which is 1, multiplied by the derivative of t with respect of p, which is 2. So it became -2 multiplied by 1 multiplied by -2. So we have -4. So p affecting the value of L, the p input affecting by the value of L by a -4 time amounts of p, amount of value, I'm sorry. So this is the complete answer. So here we have the derivative of L is with respect of p is equal to 4. So this is the answer for how much L got affected by A, how much the output of A got affected by the input of how much the output of L got affected by the input of A. The answer is -2. How much the output L got affected by the input P? The answer is -4. And how much the output L got affected by the value of C? The answer is 5. Okay, so that is the chain rule in calculus. Okay, now I have another computation graph, but this is a computation graph for a neural net. Okay, now this is the old simple neural net that we're familiar with. So in neural net, we want to get the value of z, which is the dot product between the w and x, which is the input x, plus the bias value, which is p, and y hat here is the output, which is equal to a, and a here is a non-linear value of z. And sometimes, well, not sometimes, a lot of times we are using softmax activation function, because softmax activation function, it is actually a probability distributions, but we're not gonna talk about that here. But just let's say this is a softmax activation function, which is equal to the prediction that we have, and I have the loss value, and the loss value is of course the a or the y hat, because okay, it is the same thing, y hat is equal to a, it is the same thing. The loss value is the relationship between the output or the prediction with the real label, with the y label, with the true label, which is y here, and I'm using the negative log likelihood loss. Okay, so here I have the input of x, I have the w of 1, I have the input of x2, I have the w2, and I have the bias. So again, if you remember in our simple neural network, the amount of value for the x input needs to be the same with the amount of value with the w. Okay, that's why I have x1 and w1, I have x2 and w2, and I have b. Okay, so all of this value here, all of this value is going to affect the value of z, because we apply the dot product of the w and with the input of x plus b to get the value of z, and to get the value of the prediction here, which is the y hat, I need to apply the non-linear activation function, which means that the prediction value got affected by the z value. And now this value, this y hat value, is going to affect on how much the loss value that we get from our neural networks, because the loss value got affected by the a value, which is the prediction value, or the y hat value here. So let's find the relationship between all of this line, all of this variable. So we need to find the derivative of loss with respect of y hat slash a, which is the prediction. Okay, how much the loss that we get got affected by the prediction value, and how much the prediction value got affected by the z value. Okay, and so the goal is, again, we need to find how much this output got affected by this input. Okay, and that's the entire goal. So this is the goal here that we have, just like the previous example. Here it is very similar with this example. We need to find how much the output got affected by the input. So here I have an output and I have an input. So how much L got affected by W1? How much L got affected by W2? I'm sorry. And how much L got affected by the value of B? Okay. I'm going to write a variable called dA, which stands for the derivative value with respect of A. Okay. Again, the derivative value of L with respect of A. So we need to apply the chain rule here, which is here. Okay, so how much the derivative of L with respect of A? Well, what is L? L is A and W. Okay, I forgot to mention this, but this is called partial derivative, which is you have two value, you have two or more value, you can have two value, you can have three value got affected by one value, which in this case I have two value, which is the prediction and the true label. How much this value got affected by this one value. Okay, so that is a partial derivative. So if you want to if you want to actually really understand about this concept, I suggest you to learn about something called partial derivative. Okay, what is L? What is L? What is this formula? Okay, we know the formula for this part. And the formula for L is the negative log likelihood, which is negative y log of A plus 1 negative by y multiplied by a log of 1 negative A. Okay, so let's divide, so let's split this equation. So let's find how much the derivative of y log of A with respect of A first. Okay, so the derivative of log of A with respect of A is equal to A divided by is equal to 1 divided by A. Okay, I'm sorry, I'm probably going too fast here. Okay, so we found this value here. Okay, again we are splitting this part and this part. Okay, so now we found this value here, which is 1 divided by A. Okay, well, how about this value, which is 1 subtracted by y multiplied by a log of 1 subtracted by A, where here I have the formula. The derivative of 1 subtracted by y multiplied by a log of 1 subtracted by A with respect of A is equal to 1 subtracted by y times the value of the negative value of 1 divided by 1 subtracted by A, and the answer is a negative value of 1 subtracted by y divided by 1 subtracted by A. Okay, and now the derivative of L with respect of A becomes the negative value of y of A, because again here, so okay, so I'm combining the formula that we split here. Okay, I'm combining this with this, so it became, so here I'm moving this to here, and I'm moving here this here to here, and I'm moving this negative value here to here. Okay, does that make sense? So now we get the negative of the value of y subtracted by y divided by A subtracted by the value of 1 subtracted by the value of y divided by 1 negative of A. Okay, and so now so this is the derivative of dA value. So this is the dA value, because now I have the derivative of L with respect of A, which is equal to negative y. Okay, so the negative part multiplied by this part, and the negative part here is also multiplied by this part, and that's why we get this formula, which is negative of y divided by A plus y subtracted by y 1 subtracted by y divided by 1 subtracted by A. So this is the dA, which is the derivative of A with respect I'm sorry, the derivative of L with respect of A, which is here. Okay, so let's move on to, I'm gonna do this. Alright, I'm gonna do this. Okay, so we found this part. Okay, we found this part. Now let's find this part, which is y hat and z. But before that, let's find z, the dz. So what is dz? dz is, I'm sorry, dz is the derivative of L with respect of z, or how much z affecting the value of L, which is here. Okay, I'm sorry, this is wrong. So this line is supposed to go here, not just go here. I'm sorry. Okay, so how much the value of dz? Well, we know the value of L, and the value of L is A, which is the prediction, and then the true label. So apply the partial derivative formula. So the derivative of L of A and Y with respect of A times the derivative of t of of A with respect of Z, because again, in order to find the derivative of L with respect of Z, is we need to find the derivative of L with respect of A here multiplied by the derivative of A with respect of Z, which is here. Okay, and this is the formula that I got, which is, okay, we found this formula. Okay, we found this formula before, which is this formula. We found the value of the derivative of loss with respect of A, which is this. So just write this formula here. Okay, and what about the derivative of t with respect of z? Well, the derivative of t with respect of z is 1 negative t. I'm sorry. Okay, I need the coffee actually. I'm sorry. Okay, what is the partial derivative of t with respect of z? Well, the partial derivative value is 1 equal to a. Oh, is this supposed to be a, not t? I'm such a bad at writing a, I'm not gonna lie. Okay, so basically we get this formula, and then we simplify this formula, and now we have dz, which is the derivative of L with respect of z, which is a negative y, and this is basically the prediction negative by the true label, because a is prediction and y is the true label, right? Okay, finally we get to the W part, which is the input value. So in order to find the input value, the relationship between loss and W, so I'm going to call this dwi. So the derivative of loss with respect of W is, okay, we need to find the derivative of loss with respect of A, which is here, and we also need to find the derivative of Y, which is the prediction, or A, with respect of Z, which is here. And now we can find the derivative of Z here with respect of W. So that is the chain rule effect, because L got affected by A and A got affected by Z, and Z value got affected by the W value. Okay, so we know this value. Okay, we know the derivative of L with respect of A multiplied by the derivative of A with respect of Z, because this is what we get, because this is the basically the same calculation, and that's why we have a negative y here. Okay, so now we need to find, or I'm just going to say that the derivative of L with respect of A multiplied by the derivative of A with respect of Z is basically equal to dz. Okay, it is equal to dz, which is the derivative of L with respect of Z, because we perform the same kind of formula here. So now we knew the value, which is A subtracted by Y. Okay, now we need to find the derivative of Z with respect of W1. Okay, so what is how much Z got affected by W1? Well, the answer is whatever X value is, and that is how much W1 affecting the value of Z. And that's why here the derivative of Z with respect of Wi is equal to the X of I, which is the input of I. So if I have the derivative of Z with respect of W1, the X becomes X1, and if I have the derivative of Z with respect of the W2, here I have X of 2. So now the dW of I is equal to X of I times dz, which is A negative Y, which is here. Okay. Similarly with dB, so how much dB affecting the value of Z? How much B affecting the value of Z here? Well, it is affecting by the value of 1, which is the same value, which is makes the dB value becomes dz value here. Okay, so that is the chain rule in neural networks, and this is very important for us to understand about the back propagation inside of a neural networks. So I hope you understand, and if you're still confused about the chain rule, about the derivative, about the computational graph, you can repeat this video, and I hope you understand about all of this. But I mean, if you don't understand it, don't worry about it, because all of this calculation is happening behind the scene of a neural networks. So yeah, right now I have a list of a derivative of activation function. Now, first of all, you're probably wondering why derive the activation. Okay, I have a simple forward propagation for a neural network for pass of a single layer of a neural networks. So we already very familiar with this formula, which is Z is equal to W times the X of the input plus P, which is the bias. And then after we get Z, we applied non-linearity to this Z, because Z is a linear function. So in order for us to create a universal approximator using neural networks, we need to apply the non-linearity function, such as ReLU, sigmoid, tanh, etc., etc. And because we need to find the relationship between the output and the input, which is the loss value, and how much the loss value got affected by the input value, which is the W. And in order to find how much W affecting the loss value, we need to derive using the chain rule. So the derivative of L with respect of W is equal to the derivative of L with respect of the activation function. Okay, so this is the activation function. It is very similar with it is very similar with this. So we need to find the relationship between the L, which is the output, and the A value, which is the activation value. And we need to also find the derivative of A with respect of Z. Now, this is why we need to derive the activation. It tells us how sensitive the activation A is to changes in Z. Okay? Because here we are changing the linear function into a non-linear function. So that's why we derive the activation function. And then to finish the chain rule effect, we need to know how much the derivative of Z with respect of W. Okay, now because now we know why we need to find the derivative of the activation function, because it is telling us how sensitive A to the changes of Z, because of course we applying non-linear activation function to a linear function of Z here. Here's the example. So this is a simple example, but I want to show you a couple of examples. So now, if we are using a sigmoid function, this is the formula of a activation function, which is 1 divided by 1 plus e to the power of negative z. So the derivative of sigmoid is basically 1 divided by 1 plus e to the power of negative z multiplied by 1 negative 1 to the 1 divided by 1 plus e to the power of negative z, which is, to simplify the equation, is basically the sigmoid function multiplied by the value of 1 negative the sigmoid function. Okay, so that is the derivative of sigmoid function. Now I have a tanh function. So the tanh function is e to the power of z subtracted by e to the power of negative z divided by e to the power of z plus e to the power of negative z. So the derivative of a function of tanh function is this. It is 1 negative the tanh function to the power of 2, which is 1 negative tanh squared. Okay, so that is the derivative. So this is the derivative of tanh. Now what about the ReLU? Oh, here, if we are using ReLU, every positive number, so we want those positive number, but every negative number we want to force those negative number into the value of 0. Okay, now in the derivative of a ReLU, we actually want all of those negative number become 0, and we want all of those positive number becomes 1. Okay, so that is basically what the ReLU derivative is. Okay, now for the leaky ReLU, if the ReLU we get 0 if we have a negative number. In leaky ReLU we have 0.001 if we have a negative value. Okay, so that is the, so this is the formula of a derivative of activation function. After we applying the forward propagation, and then we calculate the loss value, and then we apply the back propagation, we need to update those values. Now those formula or those algorithm is actually called gradient descent, and here I have a very simple gradient descent. This is a one-dimensional gradient descent, and of course in neural networks you are going to have a lot of dimension, but this is for the sake of our intuitions. I'm going to use one dimensional of a gradient descent. So Imagine this function is our cost function, which is the j function, which is the loss function, and the goal of our learning the goal in the training process is to reduce the amount of cost or to reduce the amount of loss, because the lower our loss function value gets means the better our neural networks perform. So we want to get into the lowest value inside of this function, inside of this cost function. Okay, so the lowest value inside of this cost function is called the global minimum, or it's just the value, the lowest value inside of a function is called global minimum. And let's say in the early iteration we have this coordinate, we're going from these coordinates, so we need to find a way to get into from these coordinates into these coordinates, because again the lower our cost function value has, the better our neural network perform. So, and the lowest value is the global minimum, and that's why we need to go into the global minimum value. And of course we can use we can calculate how much the slope of this function. Again, this is the triangle that I'll draw in the where is it? Oh my god, in this example. So this is the triangle. Okay, so in order to find how much this axis of W affecting the value of the loss function, which is how much each neuron inside of a hidden layer how much every weight value and the bias value inside of every neuron in the every hidden layer affecting the loss value or the cost value of our neural networks. So in this case we update the W using this formula, right? So the W is going to be the W negative, which is the previous W, and so this is the new W and this is the previous W, subtracted by the learning rate alpha times the derivative of J, which is the cost function, with respect of the input function, which is the W. So here I have a very simple example of how the gradient descent works. Okay, wait a minute, give me a minute. Now okay, now I have this very simple example of a gradient descent. So let's say this is the y-axis and this is the x-axis, and this function here has this formula, which is y is equal to x plus 5 squared. Now let's say in the 0 iteration, which is in the initialization, you can call it I have x is equal to -3. So I'm actually in these coordinates here. Okay, in this function I'm on these coordinates. So how can I going from here to the lowest value, which is the -5? I want to the global minimum. Okay, I want to go from here to the global minimum, which is the -5. Okay, how can I do that? Now this is how you can do it. So first of all, we need to derive the derivative of y with respect of x. You know, apply the high school derivative. So you move the 2 to the front, and then the 2 here, just subtracted the 2 with one value, which is, it became 1, which it becomes, you know, well, it became 1. So this is a very simple derivative value. So you move the 2 to the front, just like what we did in high school derivatives, just like what we did in high school. So now we have 2 multiplied by x plus 5. Okay, so this is the derivative formula. Now, if I have the learning rate of alpha is 0.01. Now let's apply the first iteration here. So the first iteration is, I want to get the new x of x value, and let's call this new x value is x of 1, and the x of O is the old value, which is what we are using to update the weight in the neural networks here. So now how much the x, or the initialization value, or the starting value? Well, the starting value of x is -3. So the x of O is -3, subtracted by the value of alpha, and the value of learning rate of alpha is 0.001, here 0.001. And what is the derivative of y with respect of x? Well, this is the value, which is 2 times x. And what is x? X is -3. So I have -3 here plus 5. And to the calculations, I have -3.04. Okay. Now I'm going from the x of -3. Actually, I'm going down to the -3.04. So I'm going down to this direction. I'm going down to the global minimum direction. Okay, so I'm going down to the -5. So this is the first iteration. In the second iteration, we did the same calculations. We did the same calculation with this, or with this. So let's call the new x is x of 2, and the previous x is x of 1, subtracted by the learning rate of alpha times the derivative of y with respect of x. So now let's put the number. Okay, so what is the value of x of 1? Well, the value of x of 1 is this, -3.04, which is here. What is the learning rate value of alpha? Well, the 0.01 multiplied by the derivative value of the derivative of y with respect of x. I'm sorry. And this is the formula of the derivative of y with respect of x. So it's 2 times the x value, which is the previous value, which is in this case, in this iteration 2 case, it is x1. So we put -3.04 plus 5, and now we get, okay, I'm sorry, it is supposed to be -3.007. I forgot to write the negative value. Okay, so now we get from -3.04 into -3.079, which is, again, we are going into the global minimum. So we start from -3, and then in the first iteration we going down to the -3.04, and then in the second iteration we going down again to the -3.0 0 to the negative 3.079. So again, we are trying to get to the lowest value of this global minimum. So the global minimum is the lowest value of a function, and in this case the function is the cost value. So by finding the global minimum, or by finding the lowest value inside of this j function, we actually trying to finding the lowest value of a cost function, of the loss function, because again, the whole goal, the whole concept of a neural network is that we are trying to find the lowest value for our loss function, because the lower the cost function gets, it means the better our neural network perform. So using the gradient descent, we can get to the lowest value inside of a loss of the inside of a loss function, or the cost function, or the error function, and we get the global minimum, which is the lowest value of a loss function inside of a neural networks can get. Okay, now I want to introduce you to the kinds of gradient descents. So there are three kinds of gradient descent that is usually used or in machine learning. So first of all, there's something called stochastic gradient descent. What is stochastic gradient descent? It is one random input at a time. So imagine you have a neural networks. Imagine you have 10,000 data set, 10,000 image data. So you perform the gradient descent. So you're performing the forward propagation, you calculate the loss, and then you going to back propagation, and then you update those values using one input, one images only. So if you have 10,000 images, you choose random images going into the gradient descent process, and then you update the value, and then you update the random and then you update the the weight and the bias value, the parameters. And this is the illustration that I can give you. By using one random input at a time, we can get a really noisy oscillations, because if you're using one input out of 10,000, one random input out of 10,000 images, automatically every input is going to be a different data, and every input is going to oscillate, to make this oscillation getting noisy, because because the input data is always changing, because the input data is always changing, and that's why the oscillation in this kind of stochastic gradient descent is very noisy here. Like for example, like this is the first iteration, which is random images, and then you pick random images again, and then see this is the second iteration, and then you pick random images again, and then the third iteration, fourth iteration, fifth iteration, sixth iterations, until you go to the lowest global minimum here, which is here in the middle. Okay, in another example, another kind of gradient descent is called batch gradient descent, or sometimes it's just called gradient descent, which is we are putting our entire data as an input at a time. So imagine you have 10,000 data images. You pick one images, you perform the forward propagation, you calculate the loss, and then you pick the second images, you forward propagation that images, and then you calculate the loss, and then basically you inputting all of the 10,000 dataset inside of this neural networks, and then you calculate all of the loss, and then after you calculate all of the loss, now is the time you back propagate. Okay, so we are using entire dataset. After we forward the entire dataset, we calculate the loss. Now we go back and we update, and this is why in this case, if we are using the entire dataset, we got no oscillation, because if we are using the entire dataset, means that in every iterations we have the same kind of data. Okay, so in the first iteration we are using the entire data. In the second iteration we also use the same data. In the third iteration we also use the same data. And this is why in this batch created descent there is no oscillation here. There's no oscillation. It is a very stable of a algorithm. Now the last kind of gradient that I would like to mention is called mini batch gradient descent. And mini batch gradient descent is basically the combination between stochastic gradient descent and batch gradient descent. If I have 1,000,000 data, I would use 10,000 data as an input at a time. So for example, if you have 1,000,000 data, I would split those data and each into a batch. I would split those 1,000,000 data into a batch, and each batch of those data I would have 100,000 data. So in the first batch I would input the entire data of the first batch, which is 10,000 data, going through forward propagation, calculate the loss, and then go back using back propagation, and then update the value, update the parameters. After I'm using the first batch, I'm using the second batch, which now it has a different kind of data set, because each batch has a different data. And this is why mini batch gradient descent is the combination of batch gradient descent and stochastic gradient descent. Because in stochastic gradient descent part, I'm using each batch for the neural networks to recognize a different kind of data. And I'm using batch gradient descent so that I can put a lot of data and then calculate the data loss, and then go back and then update the parameters using not just one data but a lot of data. But then again, and I'm using a smiley face, and this is why in mini batch gradient descent is not as noisy as stochastic gradient descent, but it is also not as stable as the batch gradient descent. So imagine I have 10 batch, and on each of those 10 batch I have 100,000 images inside of those 10 batch. So in the first iteration I'm using the 10 batch, going through forward propagations, calculate the loss, going back, and then update the parameters. That is the first iteration. Now in the second iterations, I'm using a different batch from the first iterations. So the gradient descent would see a different data set. And this is why and so a lot of people using mini batch gradient descent, especially when they have a really big data set, like a 1,000,000, 2,000,000, because if you are using batch gradient descent, if you're using batch gradient descent for a big amount of data set, it would be very heavy for the computational data, for the computer power, for the computation power. It would take a lot of power, and it would take a lot of time to calculate for just one iteration. If you have a really big data input, like for example, you have 10 million data input, it would very heavy on computation, because you need to wait until all of those 10 millions going into the photo propagations, and then you calculate all of those 10 millions loss, and then you go back, and that is just the first iterations. But if we are using stochastic gradient descent for a really big dataset, the oscillation is going to be very noisy, because if you have 10 million dataset, which means the dataset is going to be very random, so the oscillation would be very big. So the oscillation here is going to be very noisy, and this is why mini batch gradient descent is often used if you have a really big dataset. But again, it is really depend on how much the dataset that you have and what kind of dataset that you have. Like for example, in our first example, in the first segment of this video, we are using the MNIST dataset, and we are using the batch gradient dataset, and we get a very good amount of the loss value here. We get a good loss value, and which means using the batch gradient descent is good for our case. And that's why there's no such thing as the best kind of a optimization, the best kind of a gradient descent, because it really depends on your types of data, and it really depends on the amount of data that you have. Okay, so you can choose stochastic gradient descent, or you can choose batch gradient descent, or you can choose mini batch gradient descent. It is up to you as an engineer to figure it out. So I mentioned a lot about the MNIST dataset, but we never actually used the MNIST dataset itself. So in this part of this segment, we are going to code everything that we learn from the mathematical aspect into like breaking down all of this in the programming part, basically. And we are going to use like the MNIST dataset look alike. So it's not a MNIST dataset, but just for the sake of us understanding the data and the neural net. Okay, so you can go to this collab.research.google.com, and then you will get to this page. This is allowing us to get this kind of a Jupyter Notebook environment, but in Google, so we can have the same kind of environment, and so that you can follow along. So you can just click this plus new notebook, and we are going to get, well, a new notebook. Alright, now okay, first of all, let's call this neural net. Yay. Why not? First of all, of course, let's import numpy snp. So this is a library that allowing us to do the calculus, the matrix calculation, linear function calculation, non-linear function calculation, etc., etc. It is basically a mathematical library, but in a matrix format. Basically, that's what it is. I'm pretty sure that this is what the numpy is. So we can just enter to run this cell, or you can just click Ctrl plus enter. Now, if you don't know what the MNIST dataset look like, because in this case I want to create, okay, so first of all, let's create a new cell, and I want to make an MNIST dataset look alike. MNIST look alike. Now, of course, we want to get the data. We want to have data, and in this case, I want to have image. Now, if you don't know what the MNIST dataset look like, this is what basically MNIST dataset is, which is a bunch of handwriting data. Let me do this. So this is a bunch of handwriting data from 0 through 9, and it has 60,000 amount of images inside of this one single dataset, and each of the image has 28 by 28 pixel. So let's create this kind of a 28 by 28 pixel dataset. So you can do this np.random.ran, and let's use 28 by 28 because this is what the MNIST dataset is. Now again, I'm using this random value, so we're not going to get the exact same kind of this data, but I just want to make sure that the shape, and that you can understand the shape of a data. So this is basically 28 by 28 is basically pixel by pixel, or row by column, because okay, this is what image is actually. So let me image.shape. We can see the shape of this data. We can press Ctrl, press Enter, and this is the shape of the data. And if you want to look at what the data look like, so image, so we can print the image. So this is what the data look like. It's going to have 28 by 28 data. So this is basically the first column, which is the first column, and it has 28 value inside of this column. Basically what happened is that, okay, I'm going to see if there's, alright, now, okay, so you can see that it has this kind of grid, and each of this grid represent one pixel. So here I have a column, right? This is a column, and inside of this column it has 28 data. It has 28 value amount of data. So imagine this is the first column. So okay, this is this first column, this is the first column, and this is the second column, this is the third column. Now in the first column, it has 28 data that represent the amount of row data. So this is in the first row. In the first column we have 28 data here, and in the first column, in the second row, we have also 28 data. Okay, so that basically this is what the MNIST dataset look like, but in this part this is just a random number. Actually, when we are using this okay, I'm not going to clear the output. If we are using the random.ran, it will give us a random value. between 0 through 1. Okay. Okay. And this is why when we predict, this is why we get this, a value between 0 through 1 here. So let's delete this part. Okay, now this image MNIST dataset, it has 60,000 amount of image. Now this is basically one image, one image that has 28 by 28 value. But what about the other images? Okay, so let's say now I want to make, instead of image, I want to make images. Okay, now let's use the same np.random.ren. Now instead of using 60,000, let's say I want to have 23 image. And now what about the amount of pixel? Well, I can do this actually, but instead of doing this, I can do this. So what is 28 by 28? 28 by 28 is 784. Okay, what does this mean? In the MNIST dataset, it has 784 pixels inside of one image. So in this case, instead of using 28 by 28, I want to use just, turn this two-dimensional data into a one-dimensional data. Okay, so we still have every amount of data, we still have every value of our data inside of this image, but we just change the dimension of this image. So from the two-dimensional, which has the row and the column, we want to keep this data into a single row that has 784 value inside of this row. So let's say 784 here, and we can images.shape. Let's press enter, and this is what we get. So we have now 23 amount of data. Okay, I'm going to do this. We have 23 amount of data right now, and 784. Wait, no, amount of images, and 784 amount of data for each image. Now this is what happened. I have 23 amount of data, and I have 784 pixel, which is the amount of data inside of this MNIST dataset. Okay, now let's create the neural net. In this segment, we are going to understand what's happening, behind the neural net, behind the calculation of a simple neural net. Okay, now we have this lookalike data, so we just use the random data. Okay, keep that in mind. We are using a random data. This is not the real data. Okay, let me check. Okay, now let's initialize the parameters. So the parameter is basically the weight and the bias value. So we are, let's say we want the weight one, the W1 is equal to np.random.ran, and I want to have, okay, you know what, let's do this, because we need to know the amount of neuron for the first layer. Okay, how many neuron that we want to make, that we want to have? Okay, we can have 10 neuron. Okay, now let's see amount of random neuron. Okay, so if we're using ran n, instead of getting 0 to 1, we are getting a random value between negative 0.5 to positive 0.5. Okay, so this is what we want. Now I want to have this amount of value, amount of neuron for the first layer. And okay, so this is, well, what is this? This is going to be the amount of the input. So we have 784 amount of input, so we should use this value for the column in the W1. Now the bias value is going to be nb.random.ran n, and okay, how many amount of neuron we have? Well, we have 10 amount of neuron, so we can copy this and we want to have 1 because we want to have a 1. Okay, maybe this is too early for this. Okay, I'm going to delete this for now. Let's find, okay, do you remember the this value? Okay, wait a minute, I want to do this. Not this one. Okay, do you remember this S value? Basically the dot product between the input and the parameters. So let's find the S value first. S value here. So the S value is equal to nb dot dot, to find the dot product, okay, between, okay, between what? Between the image data and the weight value, which is the W1 value. So what is the data that we want to use? We want to use images, and we want to use W1. Oh my god. Okay, now let's see what happened. Well, we get an error. Okay, so why does this happen? First of all, why does this happen? Well, if we read the we got a value of error, shape of 23 by 784 and 10 by 784 not aligned. So it has a different dimension. So here is the key. So the dimension of 784 does not equal to 10. So okay, why does this problem happen? Why does this error happening? So remember that we have 23 by 784 amount of data, and we have okay, I'm going to do this. Okay. I'm going to, let's doing this. Okay, give me a minute. Okay, let's see the shape of the W1. What is W1? Well, W1 has has 10 by 784. So we cannot do the matrix calculations, because in order to do the matrix calculation, let's see in this part, we need to have the same amount of dimension between this, the first column in the first matrix, the column in the first matrix, and the row in the second column. So in this part we have a different, so this is the column in the first matrix, which is the image here. So this is the first matrix, and in the second matrix we have a completely different amount of row, because the row in the W1 is 10, and in order to do the matrix multiplication we need to have the same amount of column in the first matrix needs to have the same value of the row in the second matrix. Okay, so how can we fix this problem without ruin inside of this data, without ruining the value inside of this image data? So we need to have, instead of 723 by 784, we want to have a shape of, okay, in this case we want to have the W1 shape into, we need to change the W1, okay, change W1 from 10 by 784 into, okay, so we keep the data value, everything. We need to keep the data inside of this matrix. So how can we do this? Well, we can just turn this column into a row and this row into a column, so that we can preserve the data value. So we want to have this kind of data. Okay, now how can we do this? How can we change this into this? Well, if you still remember, we have something called transpose in matrix, which is switch row into a column and column into a row. So when we have the W1 shape of 10 by 784, we can apply the transpose, and you can do that by using this dot capital T to change the shape, and let's see, and we get the 784 by 10 now, which is, if we are doing that, let's apply this into here. Can we basically now able to do the calculation, so we are going to get a correct answer. So let's see the S shape. Okay, what's the shape of the S? Okay, so we have 23 by 10. Okay, so what does this mean? It means that we have 23 amount of data, because this is the amount of data, this is the amount of images in our imaginary data set, and this is the amount of neuron that we have. So in every neuron we are going to have every data from the input, from the amount of data, and this is what, okay, I'm not sure where, okay, so no, not this one, okay, so this is what I mean that when we have 10 by m, which is the amount of data, and we have 10 by m, which is the amount of data that we have here. So this is the amount of data, and this is basically the amount of neuron that we have, because here in our example here we also have the same amount of neuron. Okay, so you're probably wondering, why does this has 10 here, has 10 times m, but here we have m, basically the amount of data, times the amount of neuron? Well, if you still wonder, if you still want to, you can just change the shape of this data to get this kind of data, which is the same amount of, again, doing transpose is still keeping your data, so you don't need, okay, so you don't have to worry about the data, as long as you keep the amount of data when you change the shape. Now we got the s value, but what about the bias value? Now let's see if we can do the bias value. So this, let's say I have a p1, so this is the bias value. Okay, what is p1? P1 basically has the same amount of the S data, which is the same amount of neuron. So if we have 10 neuron, each neuron has one bias value. So the amount of bias value need to have the same amount of neuron in the first layer, in our layer. So let's say np.random.ran n, and we get this, and then we're doing this, which is I want to have 10 amount of the bias value, and for each of those bias value I want to have one, because we only need one for each of the neuron. Okay, so let's see the shape of this bias value. Okay, now we get 10 by 1, which is what we want, 10 amount of bias value in each neuron. So now let's do this operation, which is S1, which is the S plus the bias value. So it's going to be the Z value. So the Z value is going to be, okay, Z1, let's say the Z1 value is going to be S value plus P1. Okay, so what is going to happen here? Again, we'll get an error. Okay, so again, we need to match the shape. So we cannot do this kind of calculation because the shape is not matched up. Okay, so this is what I would like to do. Instead of changing the hyperparameters, which is what we are doing, okay, let's just, so this is what we are doing. We are changing the hyperparameter, which is the W and the P. Let's change the data. Let's change the data, because if we're changing the parameters, we are going to change a lot of parameters, and we don't have time for that. Basically, that's what happened, and we are paying, basically, because we are lazy. So let's change, instead of changing these hyperparameters, let's change the shape. So what the shape is, so the shape is 23 by 784. Let's now change images from 784 value 23 by 784 value into 784 by 23. Okay, how can we do this? Well, we can do the same thing, but there's another way to do the transpose. So we can just do this. We can create a variable images, and we can do np transpose. So this is another way to do the transpose, and we use these images. And now let's print images. No, I'm sorry, not print. Why am I printing? Let's see the shape of images. Oh wait, what? Images and b.images. Okay, now we change the shape from 23 by 784, which is the amount of image by the amount of pixel, into the amount of pixel by the amount of image. So right now we so the data look like this. So we have the amount of pixel here, the amount of pixel, and we have the amount of images, like in a you know, row kind of a shape. So right now, can we, okay, so after we transpose the image, let's delete this part because we don't need, because okay, we already have this image as our variable for the new image, because we you know, execute the cell. The question is, can we execute this cell? Well, the answer is no. Because again, we get the error value, the shape of this and this is not aligned, and now we get 23 is not equal with 10. So what is happening is, image has 784 by 23, and the W1 has 10 by 784 shape. What does this mean? It means that in the first matrix, okay, in the first matrix, yes, we have now we have the same amount of, instead of column, we have the same amount of row in the first matrix, and the column in the second matrix. Okay, the column in the second matrix, we don't want this we don't want this shape. What we want is, okay, I'm going to do this. What we want is, in the first layer, in the first matrix, how can I write this? Okay, column of the first matrix needs to be equal to the row of the second matrix. Okay, so how can we debug this problem? Well, just instead of making the W1 the first matrix, the second matrix, let's make the W1 become the first matrix. And now we get the correct calculations. We get the correct shape for the calculation. Okay, let's see the shape. And now the shape become 23 by 10 by 23 data sheet. Okay, now let's apply the bias. And Now instead of transpose the bias, we doesn't need to transpose the bias because we already transpose the data. Okay, and now let's see the shape. We get 10 by 23, which is, if you remember, we have okay, no, not this one. We have the exact same dimension as this part, as in the forward propagation part, which is the z value here. The z here is the amount of neuron, which is here the amount of neuron, by m, which is m is the amount of data input, and in this our imaginary data we have 23 amount of data. So this is the correct answer for this. Okay, so let's putting it all together. So in the first layer, put everything together. Okay, so this is our data is equal to images. Okay, so our data is basically images, and the z value, the z1, which is, okay, I'm going to do this first. Hidden layer has 10 amount of neuron. Oh my god, neuron. So the z1 is basically the weight, the np dot of the weight at the w1 and data plus the bias value, and again we can see the shape of this. Okay, so this is what we have here. Okay, this data is basically here, which is a0, and this is the bias value here, and this is the w value here, which is the w value has 10 by amount of pixel. This is has 10 neuron and has 784 amount of pixel, and here we also have the amount of pixel by the amount of the data. And with the bias we have 10 amount of pixel, and on each pixel it has 10 it has one bias value, so we have 10 by 1, and the result is that 10 by the amount of data, which is this one, 10, which is the amount of neuron, and 23, which is the amount of data. Okay, now, so right now we have z1, and if you remember what z1 is basically where is it? Z1 is basically a linear function. Oh my god. Okay, Z1 is basically a linear function here, and in order to perform neural networks to get the universal approximator, we need to use the nonlinear activation function. So we need to apply this linear function and change this linear function into a nonlinear function. So now we can see Z1 is basically linear function. So in order to get the nonlinear function, we need to apply activation function, and we have sigmoid, we have 10H, we have ReLU, and we have leaky ReLU. Okay, so since this is called activation function, well, let's just make a function out of it. So let's create a function. Okay, I'm going to call this part activation function. Okay, so this is activation function. Let's create a function of it out of this. So first of all, we have a sigmoid, and the input is going to be z, which is the linear function. Okay, and we want to have the activation variable, which is a. And what is the sigmoid? Sigmoid is basically 1 divided by 1 plus e to the power of negative z. So we doing this 1 divided by 1 plus, so np.exp, so we can get the e value. The e value of what? To the power of what? Negative z. So we can just negative z. Okay, so this is the sigmoid function, and we can just return the function. Now let's run this code. Okay, so I want to do this. I want to print the z1. Okay, no. Dot. Okay, let's do this. D1 dot shape. Okay, what is the shape of the z1? It has 10 neuron and then 26 amount of images. What about if I'm doing this? Well, I have the amount of images, but this is not what I want. Okay, I want the amount of neuron instead of the amount of images. So I can just transpose z.c. Let me do this. So I'm going to transpose z and get the amount of neuron now. So okay, why I'm doing this? So let's print this. Okay, now we have all of this value, right? And what are these values? This is the value for each neuron for one single image, because every neuron contains an information from every pixel. So this is what this value means. It has 10 value, which is the 10 amount of neuron from the input image. So this is represent the first image, because this is the zero index here from the first image from the 23 amount of image data. Okay, so let's apply the sigmoid function into this linear value, into this linear function. So I can just doing sigmoid. Okay, and let's see. Well, this is the non-linearity that we get. Okay, I'm going to do this instead of doing that, so we can still see the amount, and we can compare the amount. Okay, so this is the linear data, which is this part, the linear data, and this is the non-linearity data, the non-linear function that we get by applying the sigmoid. Okay, what about the another activation function? Let's create function for 10h. So the input is going to be z, and I'm going to return a as my variable. Return a. Okay, in NumPy they basically have 10h, so we can just doing this. And we get the 10h value from z. So now let's run this cell, and instead of sigmoid, let's see the 10h value. Oh my god. Alright, so this is the 10h value that we get, the non-linearity from the 10h value. Now I want to use ReLU. Let's see. So let's again define now ReLU, and the input is going to be Z. Okay, now what is ReLU? ReLU is basically, if we have a positive number, we want those positive number, but if we have a negative number, we force those negative number into a zero value. So basically what we are going to do is the activation function of ReLU is going to be np.maximum of between 0 and, well, whatever Z is. So let's return A. Okay, so let me doing this. Now I want ReLU. Okay, so what is happening here? So every negative value instead of this instead of Z1 here, in the instead of this neuron for the first image, I'm forcing all of those negative value into a zero value and keeping all of the positive number into a positive number, because what we are doing here is that, okay, we are picking the maximum value between a two value. So for example, in the first index we have basically 8.5, right? Okay, which one is bigger? Which one is the maximum value between 0 and 8.5? Well, it is 8.5, and that's why we have 8.5 here. Another example is that which one is bigger? Which one is the maximum value between 0 and 0.3? Well, the answer is 0.3, and that's why we get 0.3 here. Well, now the question is, which one is the maximum value between 0 and negative 22.9? Well, the answer is obviously 0. 0 is bigger, and that's why we get 0 value here. So this is the ReLU activation function. Okay, now we can apply non-linear function into the linear function, which is the Z function, which is the Z value. So let's take this and oh my god, I want to take this. Oh my god, oh my god. Okay, okay, so this is the linear function. Now let's use A1, stands for activation function, which is the non-linearity function. So this will become non-linear. Okay, so let's apply. Okay, I want to use ReLU, so let's apply ReLU for Z1. Okay, it's supposed to be ReLU here, capital L. And now, well, we get the activation function. We get the non-linear from this linear data for this Z1, and this is basically what we are doing here in this example. We get the Z1 value, okay, the Z value, and then we applied a activation function, which is this sigma activation function for the notation. And if you guys see this, Okay, I don't know if you see this. Okay, let's doing this. This is what we do. Okay, in this part of the code, this is what we do, which is the z1 is equal to the w1 and the dot product of the input and then the w plus the bias, and then we apply the non-linearity into the z value, which is the linear value. Okay, now let's create the second hidden layer, which is z2. So create, let's make the second hidden layer. So basically it's going to be z2, and let's initialize. Okay, before that we need to initialize. Oh my god, I don't want to do that. Let's initialize the hyperparameter. Okay, the parameter for the second layer. So we need to have w2 and p2. Okay, now the w2 is going to be np.random.ran, and okay, now how much neuron that I want to have? Okay, let's say I want to have 5 neuron. Now what about the input value? Is it 784? Well, the answer is no, because right now the input is not the data, but the input is the output of the first layer, which is this is the first layer, and this is the input for the hidden layer, for the second hidden layer. So this is what you see here. Let's see. Okay, so this is basically what you're doing. We have an input. Okay, so this is the input, and this is the first hidden layer that we have. But now in the second hidden layer, the input is basically the output of the first hidden layer. So the value of this part is not the input itself, it's not the input data, but the output amount of the first hidden layer. So what is the output of the hidden layer? Well, it's 10. Okay, because we have 10 amount of neuron, and the same thing is happening with random.ran. How many neuron that we have? Well, we want to have 5 neuron. Well, that's 5, and each neuron only have one bias value. So let's do the dot product, np dot. Let's do the dot product between. Okay, be careful. What is the z value? Okay, not the z value. What is the a value? The a value is a1 dot shape is 10 by 23. So we need to careful here. So it makes, let's make the a1 become the first matrix and the w2 become the second matrix, and then we apply the base value. Okay, so let's run this code. Okay, we get an error. And why is that? Well, apparently the shape of does not align. Okay, so we basically do the same thing with the image here, where we transpose. Okay, where is it? My god. So we transpose the input. So we basically do the same thing. let's do the same thing by doing this. A1, okay. Oh my, A1, so W2, oh my god, what am I doing? Oh my god. Oh my god, what am I doing? I'm sorry. Okay, so this is not our one. W2. It's not P1, it's P2. 10 and then A1, W2. So W2 is A1 is 10. Okay, I can just do this. W2 as for input. Alright, so this is what we're doing. So this is exactly the same for this formula, right? Where right now we have W2 as the first matrix here, A1 as the second matrix, which is the output of the first layer, and we have P2. And this is basically, let me do this, the linear function. So let's apply the non-linearity. Okay, now let's apply the non-linearity to this. So the A2, right, become, okay, what non-linearity that I want to use? Let's use sigmoid, why not? Sigmoid of the Z2, and let's see the shape A2, which is the amount of neuron and the amount of data. It is exactly the exact same thing that we want. Now I would like to use softmax activation functions instead of sigmoid activation functions for the linear function of Z2, because it will create a probability distributions. And what do I mean by that? So first of all, let's see what Z2 is. Print Z2. Why not? Okay, so let's see the first index. Okay, so this is the value that we have, and I would like you to use something called softmax. Okay, hold on a minute. Okay, where is it? Hold on. Wait, I can't find it. Is it this one? No. Okay. Softmax. Now, okay, what is softmax activation function? So it's basically an activation function, but instead of creating a nonlinear, it creates a probability distributions. So it would look like something like this. Okay, I'll give you an example of softmax activation function. Okay, so first of all, let's use an example for this. So I have I don't know, label, might not, but prediction, and inside of this prediction I have 5 and then 2 and then -1 and then 3. Okay, so this is our prediction. Now let's apply the softmax for this. So the softmax activation function is basically again, it is a activation function, so let's create a function out of it. So softmax, and the input is basically the zip, and inside of the softmax I would have a is equal to np dot exp. So this is the formula of so it's e to the power of every index in here divided by the sum of every index of the e value of every index here. So here's what's going to happen: exp dot every index divided by the sum np dot sum of every index value inside every e value inside of a z value. So return a. Alright, so let's try to get the prediction, the probability prediction using the softmax activation function. So softmax of prediction. Okay, so just let's print the result, probability prediction. Is it working? And yeah, it's working, and we get the exact same answer here. Okay, so what is actually happening here? If you sums up the prediction, np dot sum of the prediction, the result is 9. Okay, and in order to get the probability distributions, we need to have the sum of the all of the value inside here. If we sums up all those value, it becomes number 1. It becomes just one value, and that's why let's see if I sum the probability prediction, the sum is going to be 1, right? Because okay, so you can imagine like, okay, this is the probability, right? So what is the maximum output, maximum, not output, but the maximum value of a probability? Well, it's 100%, right? It's 100%, and in this case 100% is getting represented by the value of 1. And so if you see this distribution, like for example, if you see these distributions, we can see it as, okay, so this is the distributions. Let's see. So in the first index we have this value, and because if the 100% is equal to 1, which means we can say that this is also mean 84%, and this means 4%. And etc, etc. Okay, and that's why when we sums up all of these numbers, we get a value of 100%. If that makes sense. Again, like for example, for this value, right? So we have 11% here for this value. And we got in this part we got like 0.2. And if it sums up all of this value, we get 100%, which is 1. So what does this mean? If you remember, in this part, the maximum value that we have in the prediction is, so np.maximum, the maximum value inside of the prediction is 5. np.maximum, np.maximum, oh no, we can't do that. I mean, it's pretty obvious. So let's just delete this. So the maximum value in this, inside of this file, inside of this array, is 5, right? And we need to create a distribution, but we also need to keep the distributions in a probability manner. And that's why in this part, this is the highest value. So we create a probability where the highest value is also the first index, and the second highest value is the last index, which is here, and then here as this, and the lowest value, which is the -1, is this part, which is the lowest value that has 0.2% percentage. And this is what the probability distribution means. We have this probabilities distribution, because if we are using these random distributions, yes, this is the highest value. But what if I have I don't know, something like 5.1 maybe, or maybe there's a lot of 5.1 inside of this array, and it will be so hard to differentiate, and it's not going to be exactly 1, and it's like not going to be exactly the maximum value of probability. So the distributions in a probabilistic manner. Is that make sense? I hope that makes sense. I hope that makes sense. Okay, so let's do the softmax breakdown. So here I have my softmax formula, which is okay. So how does this code work? Because okay, let's write the softmax again. Softmax is equal to the np.exp of whatever value we want to get, and divided by np.sum of the np.exp of whatever value. So let's say I would do the prediction, and I will also have the prediction. Okay, so let's break down this one by one, all of this one by one, right? So first we have np.exp, which is going to create the e to the power of every index inside of this array, inside of this prediction array. So let's see the result. Okay, so e to the power of 5 here. Okay, so e to the power of 5 is this value. E to the power of 2 is this value. Oh my god. And e to the power of -1 is this value, which is 0.3, and e to the power of 3 is 20.08. Okay, so we get all of this value, e to the power of every value inside of this prediction matrix. So now I want to sum up all of this value, np.sum dot exp of the prediction, right? So I'm going to sum up all of this value. Okay, so what is the sum? My god, okay, so what is the sum of 148.41 plus 7.38 plus 0.36 plus 20.08? Okay, so what is the sum of all of this value? It is 176.255, etc, etc. Okay, so we get this value. This is a single value because this is the sum value. And if we apply the division of this array here, I'm going to copy this array divided by this single number here. Okay, I would get the result okay, I can't do this. This is not the correct format. Wait, let me delete this one and let me create. So array is going to be this, and np, and then sum is going to be this, and result going to be array divided by the sum. Okay, so let's see the result value. And we get this probability distribution that we have here. Okay, so how can this value happen? Because if we are doing this division, mathematical divisions, we would apply the rule inside of the matrix rule that has, so this is a single number, so this single number is going to divide all of this number inside of this array, inside of this matrix. So 148.4 is going to be divided by this. This value is also going to be divided by this, and this value is divided by this, and this value is also going to be divided by this. Okay, so that's what happened here, and this is why we get this result by using this single value, because in this case this part, okay, so all of this value is the same, which is this value, and all this value is basically this value here. Oh my god, let me do this. And all of this e5, e to the power of 2, e to the power of -1, e to the power of 3 is basically this. And we divide all of this number with this number by applying the rule inside of the matrix mathematical rule, and it will basically performing the element wise of the calculations for this single number inside of every matrix here, prediction. And that's why we get this value by using this function, this single function here. Okay, I hope that makes sense. Okay, now you're probably wondering, okay, why do we want this kind of a probability value instead of just this kind of a value? You know what, so I hope you understand. Okay, I hope you understand now why do we need to get this value and change it to distribution, the distribution value. Well, the answer is basically this explanation. Okay, so let's apply the softmax into our Z2. Okay, so let's say okay, I want to do this, so I want to print Z2. So let's print Z2 here, and so let's apply the Z2 in this exact index, apply the softmax probability distributions. So apply the softmax of Z, softmax for Z2 basically. Okay, so now we get the probability distribution of this. Oh no, Z2 of 0, not entire Z2. So now we get this value, and let's see if the np.sum is equal to 1. Why not? It is equal to 1. And let's see if this probability of Z2 is equal to 1. Z2. No, it's 0. Well, no, it's basically much worse. We get -1, which is -100%. Like, what does that even mean? So we need to get the probability distribution for our prediction. Oh, okay, one thing, if we are using the softmax probability distributions, which mean that the highest value, okay, the highest value, the highest is the prediction from the neural net. So like, for example, if I have a label, so let's say in the first index I would have, again, let's use the MNIST dataset, which is from 1 to 9, but in this case let's have 0 through 4. So this is the index 0 to 3. So in this case, if we have the prediction and we have the label, in this case the prediction is, okay, I say that the image that you input is the image of 0, because the highest prediction value is in the first index, which is the index for the 0 value. Okay, this is going to make sense in a moment, I promise you that. So yeah, that is basically why we are using the probability distribution of our softmax distributions. Now we get to the loss value. Okay, so now we get to the loss segment part of this video. But before we start to understand the loss function, we need to create a one-hot encoding label. Oh my god, one-hot encoding label for our MNIST lookalike. Okay, and okay, why do we need to do this? Because inside of the loss function we need to have, well, the prediction and this value, which is the true label that we have, and we don't have the true label yet. So let's create just a random label using a random value, just like what we did with the MNIST lookalike. So remember that A2 is equal to 5 neuron output. Okay, so A2 is equal to 5 neuron of an output. Okay, or not A2 but the output layer have 5 neurons as an output. Okay, and which means that inside of these 5 we need to have 5 labels instead of 0 through 9, because in the MNIST dataset, they have basically they have where is it? They have 0 through 9, but in our case we have 5 neurons as an output, which means that we have 0 through 5. We would have 0 through 5 label for our example. So let's create let me delete this. So let's create the label that we want to have. So np.array is going to be just a random number, integer number from 0 through 4. Okay, so why 4? Because again we have 5 neurons and the first value is 0, and that's why we want to have the maximum output of 4. The maximum label is 4. Yeah, so let's get just a bunch of random number from 0 to 0 through 4. So I have this. Okay, how many amount that we want? Well, in our example here we have 23 amount, and that's what the amount that we want. So let's see, and then just a random value, don't care. Okay, how many amount of this? 1 2 3 4 5 6 7 8 9 11 12 13 14 15 16 17 18 19. Okay, I guess this is number 1 label. Let's see how many amount of. Okay, so one more. Okay, now we have 23 amount of label, that and the label is from 0 through 4, which is 5 value, 5 amount of values. So after we're doing this, let's create the one hot encoding label. So let's create a one hot label that has np.zeros from basically from 23 through the amount of we have, which is 5. Okay, so I'm going to explain this part. Okay, instead of this, okay, I'm going to create a numpy array, and instead of this numpy array it would have 0 value. So it's going to be 23 amount of an array, and instead of each array I'm going to have 5 value of a 0 value. So basically this is the label.size, and this is the label.max plus 1. Okay, because the maximum value instead of this label, the maximum value instead of this label is basically 4, and we want 5 value because again we have 5 neuron. That's why we want to have 5 value. We have 5 value, and we have the label size. And so let's see the one hot label in this part. Wait, well, this is the same value. Okay, the exact same thing with this value. Okay, so now let's do the one hot label dot arrange of the one, not the one hot, but the label dot size, and label is equal to 1. Let's do, okay, let's do this. Okay, so what does this code doing? Now if we look at our one hot label, it will look like this. I'm sorry. Okay, so you can see this is what the one hot encoding look like. So if you see, inside of our label array, okay, inside of our label array, in the first index we have the label of 0, and we want to change. Okay, how can I explain this? Okay, so in our array we have 23 value. Okay, we have 23 value. So we want each of this value is an array. So now we have 23 array that represent each label. So in the first label, in the first index, we have 0 label, and this 0 label is going to be represented by this 1 value. So you can see this as a, okay, I'm going to do this. I'm going to take this. Okay, let's edit this part. 0, 0, and 0. So this is basically the positions for each index value. Okay, so we have index from 0 to 4. So this is basically the positions for 0, 1, 2, 3, and 4. And we want to have each position. So like for example, in the first index, okay, I'm just going to explain by this visual. So in the first index we have 0 label. In the first index we have 0 label as number 1, and then in the 1 label, which is 0, in the second label it is also 0, in the third label it is also 0, and then in the fourth label it is also 0. And because we have 0 as a label in the first index, that's why it's only 1 inside of this index. There is 1 value, which is basically, this is telling us, okay, the label is inside of this part of this array. The same thing with the fourth, with the second index, which is the label of 4. In the second index we have 4 as the label. Well, in this index of an array we have in a 4 position of the number 1, which is this one, which is the correct one, the correct positions, right? And then in the second index, well, in the third index we have 2 label. So just the same, this is the 0 label, this is the 0 index, this is the first index, and then this is the second index, which is represented by this part. This represented by this, you know. And this is why, and this is what the one hot label is. It represents the amount of this. It represents the index. Okay, I'm sorry. It represents this array, this label array, so that each index has its own array, and the true label, which is like 0, 4, 2, is going to be 1 here. And this is what the one hot label is. Okay, so this is the one hot MNIST lookalike that we have. Now let's have, okay, let's have the prediction first. Okay, now we have the true label, which is this part, which is the true label. Why? Now we need to have the prediction. Okay, so what is the prediction? The prediction is basically the output of the output parameter, which is, in our case, it is the secondary layer, and we need to z2 value. Okay, and z2 is a linear function, and we need to change this z2 linear function into the probability of sigmoid. And okay, do we have the prediction? So okay, we have the prediction. Do we have the prediction? Softmax the prediction. So this is the thing that we want. Okay, I'm just going to do this, and we dot so okay, we softmax the softmax value, which is the probability distribution value of the z2. Okay, so this is the prediction value. So this is the prediction that we have, and this is the one hot label, which is the true label that we have here. Now, since we have these two values, we can do the loss calculation. So let's doing this loss calculation. Okay, so in our example, we have two kind of loss, which is the MSE, which is mean square error, and negative log likelihood. So let's calculate loss using MSE first. So let's say MSE of loss is equal to, okay, what is this? So the formula is np.sum. Okay, this is the sum of the square, np.square of, okay, so what is y I here? It is the true label subtracted by the prediction. I'm sorry. So what is the true label? Well, the true label is one hot label. The one hot label subtracted by the prediction label, and the prediction label is the probability distribution of the z2. Okay, and we need to divide with the amount of data. And what's the amount of data we have? We have 23 amount of data. Okay, so okay, first of all, what's going to happen? We'll get a loss. So again, this is the value error, and we need to have actually we need to have the transpose of the one hot label so that we can do these calculations. Alright, so now what is the MSE loss value that we have? We have this loss value of 0.98. So this is the loss value that represent the entire dataset. Now, okay, I'm not gonna. Okay, should I? Okay, no, I'm not gonna do that. Okay, so this is the MSE loss calculation. Now we start to create the negative log likelihood. Okay, I don't know if you can see this. I'm going to do this. I don't know if you can see this. Okay, I hope you can see that. Negative log likelihood. Okay. So for the negative log likelihood, let's call this log loss. So the log loss is equal to, okay, what is the formula, it is np.sum, the sum of what? The sum of the one hot. So this is the formula, the sum of one hot, the probability log. So okay, so this is the formula, the one hot label multiplied by np.log value of the prediction value like this, and then we divide by the n amount of data that we have, which is 23 now. And remember, since this is the negative log likelihood, we need to put the negative in front. So, and we get an error because we forgot to transpose the one hot label. Okay, that is the correct transpose. Okay, so by using the negative log likelihood, how much the log value that we get compared to the MSE? The last log value is 83.08, which is a very different kind of value compared to the loss value. So, but then again, you can, either using MSE or the log loss value is it is up to you. You can compare the loss with this loss, and okay, I want to mention this. For the negative log likelihood, they sometimes call this as cross entropy loss. So this is just another name for the negative log likelihood loss, apparently. And yeah, I guess that's it for the last part. Okay, now in this segment of this video, I mentioned a lot about MNIST, obviously, but right now let's use the MNIST dataset itself. So okay, finally we are using MNIST dataset. So let's go to the colab.research.google.com, and we can create a new notebook by pressing this. And okay, if you don't know what the MNIST dataset look like, it look like this. So yeah, I know this is ridiculous, but basically this is the numerical representation of the MNIST dataset, which is again MNIST dataset is going to look like this. And if you see this, okay, I saw the okay, this is a much better example. Okay, so this is obviously what the MNIST dataset look like, which is a bunch of images, a bunch of array that has okay, 28 by 28 pixel. So this is 28 by 28 pixel, and each pixel is represent a single value that represent number in a grayscale format. Okay, so the white is going to be much more a bigger value compared to the black value. So this is what the MNIST dataset look like. And in this part we have this, which is okay, the zero value is obviously the black color, just like this part. So let's working with the MNIST dataset. So let's create let's call this file MNIST from scratch. Okay, yay. Why not? Okay, so first of all, let's connect the notebook the notebook with the Google Drive, because I have the file. I have this file, okay, on my Google Drive. So I'm going to run this cell to connect the Google Colab with my account, with my Google Drive account, to access the MNIST Dataset from my Google Drive. Okay. So okay, let's wait a minute. All right. Now, okay, where is my? Okay, so this is my Google Drive, which is Drive, and in this Drive I have MNIST train.csv, which is this file on my Google Drive, and I can, okay, file is too large to display. Okay, I'm gonna display that. Okay, so first of all, I'm going to copy path this file, and I'm going to import some dependency. Okay, import dependency that we going to need, which is obviously we are going to need the numpy to do the calculations or the matrix calculations. We also need to import pandas as PD. This is so that we can read the CSV value, because this is the CSV value that we have here. And we need to import. Do I need to import this? Okay, I think I'm fine with just this dependencies. Okay, so let's load the data that we have, and it's going to be pd.read CSV to read the CSV file, and we are reading the MNIST, which is here, which is the MNIST that we have here. So let's load and read this dataset. Okay, now I have data, and okay, this is what the data look like inside our Google Colab, which is the exact same data that we have here. Okay. Okay, I want to do this, which is just to see the 0 through 5. Okay, so this is what the MNIST dataset look like. It has 28 by 28 amount of pixel, which is what we expecting from the MNIST dataset that has 28 by 28 pixel. Okay. And we also have 60,000 amount of images, just like this 60,000 amount of images, just to let you know. Okay, so what do we need to do here? Let's change this data into np.array, numpy array format. Okay, and let's print the shape of this data. Okay, now we have 60,000 amount of images and 785 amount of pixel, which is exactly what we create in the previous segment. Now okay, I want to have this m and n. I want to have this value here, so I'm just going to do data. I'm just going. Sorry. Okay, I'm just going to data dot shape like this, and now I have m variable, which is 6,000 integer number, just a number, and then n is 785, which is m is equal to 60,000 and n is 785. Yeah. Okay, now let's shuffle this data first. So to shuffle the data, we need to nb.random shuffle the data. Okay, so data now is became, you know, in a random order. After we shuffle the data, let's create actually I don't know if I want to do this. You know what, just do it. I don't know, just doing it. So I want to have I want to split the data into two kind of data, which is the train and which is basically the def. So the def value is going to be the data from 0 through 1000, which is the first, you know, the first 1000 amount of data that we have, which is the first 10,000, the first 1000 images that we have, and transpose all of that data. And of course I'm going to have y as the label. Y def is equal to the data def in a zero amount, in the zeroth index. Okay, I'm probably needs to show you guys this part. So let's say I have data from 0 through, let's say it's 0 from 3. Okay, let's see the data from 0 to 3. Now type oh my god, what am I doing? This is not what I want to do. So okay, I'm sorry. Non-type data, because obviously we're going to get okay, I'm sorry. Okay, so this is not what I want actually. Okay, I need to okay, something wrong is happening, and get this, and okay, so I want to see the first. Okay, now I'm sorry for the early I want to show you guys this part. So we have the label, which is this part. So this is the label. This is basically the matrix coordinates, not the matrix, it is the pixel coordinates, and this is the label. So in the first image we have you know, 5 label, which mean in this this image is 5, this image is 0 image, this image is 4 image, and this image is 1 image, and this image is 9 image. Basically, okay, so this is already shuffled data, so I don't need to shuffle again. And so this is the label here, and I want to transpose this label, so I can do this. So now every label has its own array. So every label has its own array, and when I'm doing this, I can actually doing this data of 0 till 3 dot transpose of oh my god dot transpose. Let's do it. I can do this. I get just the label. Okay, so this is what I'm doing here. I pick the first 1000 images, and then I transpose all these images so that every label is on the one array, and that is the first array, this is the first index. And I want to take all of this label so that it became the y def of a label. So now the x is obviously the data. The data. Bro, are you serious? Oh my god. Okay, now xdef is the data. We obviously doesn't want the label. We just want this n until 785, which is n, and here, because again n is 785 until n, and x, I want to do this for xdef and xdef. So we need to normalize the data. Okay, I want to see by dividing the data into 255. Okay, you know what? I want to do this actually. So in the data, I want to see that. So the maximum value is 255, which is the widest color, and I want to normalize this data by dividing this data into 255. So that's what happened here. So that every data is a value from 0 to 1. Okay, so that's what happened here. Okay, I'm just gonna write it, making the data from 0 through 1 instead of 0 through 255, because if we train 255, it would, because this is too much data, so we want to have a small data so that the calculations for the neural net can be faster. Okay, so that is the def, and I want to do the same with the data train. Now the data train is from 1000 until 60,000. And what is 60,000? 60,000 is the m amount of data that we have. So okay, so I'm just gonna write it here like this. The first data until 10,000. The first 10,000 data. First 10 data, and this is basically 10,000 until 60,000 data. Okay, so this is what happened here, and I'm going to do the same thing with the train. Okay, so this is the y, because this is the label, right? This is the label, and I want to have data train. Oh my god, train. Okay, I forgot to transpose this part, and then we get the label for every images, and then doing the x train, we get the data from again 1 through n, which is the pixel amount. So this is take the pixel. Okay, I'm just gonna take the pixel data, and this part is basically take the label data. Just the same thing what we are doing here. We just take the label data, and this is also take the pixel data. Alright, I want to normalize the data. so x train is equal to x train divided by 255. So this is normalize the data. Okay, so let's run this cell, and we got the x train and then y train data, which is this is actually what we want, which is the x train and the y train data. So now let's create the neural net. Okay, so this is the neural net part. The neural network part is okay. First of all, we need to initialize the parameters. So okay, I want to have a simple just a simple neural networks. So it is going to be this architecture, which is 10 neuron and then 10 neuron for the output layer. So in the first hidden layer, I have a hidden layer. I would have 10 neuron, and in the second hidden layer, which is the output layer, second hidden layer, which is the output, I want to have, oh my god, what? Also 10 neuron, because we have 10 label of data. 10 labels of category data. Okay, so again, let's initialize the W, which is W1, and the W1 is going to be np.random.ran. Okay, again, this is the amount of neuron, and this is the amount of the input that we have, which is what? What's the amount of input? Well, it's the amount of pixel that we have, which is the n. So this is amount of neuron and input data, and this is the bias value that we have, which is np.random.ran, and we have a ran n. Also 10 neuron, and on each neuron we only have one bias value. Okay, so this is for the first hidden layer, and for the second hidden layer it's going to be W2, and with a random.ran. And okay, so how many amount of neuron that we want to use? 10 amount of neuron, because we have 10 labels, right? And the input is basically the output from the first neuron, from the first hidden layer. I'm sorry, from the first hidden layer. And in the first hidden layer, we have 10 amount of neurons. So we need to take all of those value, and that's why we have 10 here. So it's going to be amount of neuron, and the input is not the input data. Output amount of the previous layer, which is the first layer in this case. Okay, so that is W2, and let's initialize the P2, and it is np.random.ran n, and it's going to be the same with this part. Okay, and again, the and if you forgot the np.random.ran, it's going to give us, oh my god, a random value between between negative 0.5 to positive 0.5. Alright, So let's initialize random. Okay, so this is the initialization. Now we get to the forward pass. In the forward pass, we need to find the z1, just like what we have. Okay, I'm going to close this. Just like what we already break down here. So we need to have z1. Z1 is basically the dot product between the w1 and then the input plus the bias value. So the w1 np dot of the w1 and the input. What is the input? The input is x train, which is here, which is every pixel data, right? Here is every pixel data, x train plus p1. Okay, why does this happen? Oh yeah, we forgot that we actually should take the okay, wait, what? So this is the w1, right? 784 x train. Okay, wait, x dot shape. So that 700 1 2 3 0 to m, that is 0, then the data train. Oh, I'm sorry, this is not data, this is data train. My mistake. Okay, now we have the correct value, and 784 big. Okay, of course. So it is 784 -1, because we also here, when we get the data shape, we haven't we haven't taken off the label that we have, so we need to subtract this by 1, because n amount is pixel plus label, and we only need the pixel amount, so that's why we subtract this value by 1 here. Okay, so this is the z1. We get the z1. Now let's find the a1. Well, the a1 is the activation function, because this is the linear function value, and we're going to need the non-linearity value. So let's create the activation function. Okay, where is the activations? Okay, I want to do this. Okay, let's do this. Activation function. So the first activation function is sigmoid. Let's create every activation function here. Well, not every activation function. I just want to make sigmoid and hn value. Now, in the sigmoid, we have a is equal to 1, divided by 1 plus e to the power of np dot xp to the e to the power of negative z, and return all of those values. And there's the sigmoid function, and the tan h function is going to be a is equal to np dot tan h, and it's going to be z, so return a. And for the last function, I want to have rectify linear unit, which is ReLU, and it's going to be a is equal to the np dot maximum value of, okay, not but a maximum, it is correct, maximum np dot maximum, yeah, it is np dot maximum, np dot maximum of which one is the highest value, is it 0 or is it the z value. Okay, so return a. Now in this case I want to use ReLU, and let's put z1 there. So this is for the first layer, first hidden layer, and this is non-linear function, and this is for the second hidden layer. Okay, and the second hidden layer we are going to have z2, which is here. Here we have I don't know if you can see this, we basically have z2 here. So this is z1, this is a1, and this is z2, and then a2. The z2 is basically the linear function value for the second hidden layer. Okay, and we are doing the same thing basically with the dot product of the w2, and okay, now the input for the z2 is a1 plus b2 value, layer, and a2 is the probability distributions, because this is the output layer. So I want to have the probability distribution, so it's going to be softmax probability distributions of z2. So it's going to be probability distribution. Okay, and we have not created softmax yet. Let's create the softmax. Okay, I'm going to run this again. Define the softmax, and the softmax this. Okay, so what is the softmax? Again, softmax is maybe a, then np dot exp, because e to the power of every index instead of z, divided by the np dot sum. So this is the sum of the e value e to the power of every value, which is np dot exp of z, and return, oh my god, and return a. So let's run all of this and run the for pass. So now we get a1, which is the probability distributions shape, and we have the probability for 10 instead of a 10 neuron, which is for each level. Now we get the probability distributions value. Let's create the loss values. The loss value is basically a single value that represents the entire loss for our dataset. In this case, I want to use the negative log likelihood, which is the log loss. And the negative log likelihood is basically the negative value of np.sum. Okay, so np.sum of one hot while, which is the label, and we have not yet created the label. So first of all, we need to create a label. And I guess, okay, so let's create a label here and train and def. Okay, I'm going to do this. So this is the train data. Okay, so this is the train data, and this is the, let's say this is the one hot label, one hot label data. So it's going to be one hot label is equal to np.zeros, the zeros value of the x train dot size and x, not x train, but the label, which is y train dot size, which is going to be this, which is 59,000, and the y train dot max, which is the maximum value inside of this label, which is it's going to be 9, because we have 0 through 9 label, and because it only going through 9, we need to add 1, because we want to have a array that represent the amount of data that we have, which is going to be 59,000, and inside of this array is going to have 10 value of 0. So this also, that's what this code is doing. And inside of this label, inside of this one hot label, I want to do np.range of the y train dot size and the y train itself. And so this would create the one hot encoding label, and one hot encoding label I want to transpose this data array, this data tensor. Okay, so this is our one hot data label. And now for the sum, so this is the true label, which is the one hot label multiplied by the the log value of a1. Wait, not a1, this is a2. Okay, I'm sorry, I made a mistake here. So it's going to be a2 divided by the amount of data. Okay, because this is the entire data set, and the amount of data is n divided by 1. It's like this. Okay, so since I made a mistake, let's see, let's initialize again. Okay, I made a big mistake, such a big mistake. Okay, so let's see the log the loss value that we have. Okay, this is crazy amount. Okay, what about 59? Okay. I'm so stupid. It's not M, it's N. Okay, so this is the loss value that we have, and this is the entire basically this is the entire forward propagations. So this is the forward propagation, and now after we get the loss value, which is this, using the negative log likelihood, we need to do the back propagations. So this is the back propagations. Alright, so let's do the back propagation quickly. So what do we need? We need the Z2, which is what is dZ2? dZ2 is the how much the derivative of loss with respect of Z2, right? And that is dZ2. So how can we calculate the value of dZ2? Well, it is A2 divided by the one hot label. So basically this is the okay, how much okay, I'm going to do this. Basically what happened is how much the value of Z2 here, the value of Z2 here affecting the value of the loss here, the value of the loss. Well, the answer is just whatever value, just whatever the difference value between whatever the difference values between, oh my god, between the prediction, in this case A2, because A2 is the softmax activation function, which is the probability distributions, and the true label, which is the one hot Y or the Y label, or Y train or the one hot label. Okay, so that is Z2. How much Z2 affecting the loss value here? Well, the answer is whatever the difference value between the prediction and the true label, what that is the Z2. Because if you see here, what is Z2? Okay, how can Z2 affecting the loss? In order for Z2 affecting the loss value, you need to go through the probability distributions, which is why we're including here. And what is the loss one? What is the loss? The loss is just the differences value between the true label and the predictions. Because again, A2 is just the prediction, so A2 is just the prediction, or sometimes they are using Y hat like this. And for the label, sometimes people write it just like this. So this is for the prediction, and this is for the label. You know what? I'm just going to do this. So okay, not here. Well, why not? So Y hat is for the prediction, and Y is for the true label. Okay, I guess that's it. Okay, so we got dz2, which is the derivative of the loss with respect of z2, which is how much z2 affecting the value of loss. Okay, now after we get z2, what do we need? We need to find the w2, how much the w2 and how much p2 affecting the loss value, which is dw2. And what is the w2? Well, it is np dot the dot product between dz2 and the a1 dot transpose. Okay, so what does this mean? Remember, what is dw2? What is w2? W2 is just the dot product between no, not okay, what is z2? Z2 is just the z2 value is the dot product between w2 and a1. So in order to find how much w2 affecting the loss value, we need to we need to know how much w2 affecting the value of z2, and then after we know how much z2 value got affected by w2, we know how much w2 affecting the value of the loss. Because right now we know the value of this part, which is the derivative of the loss with respect of the z2. I'm sorry. So what is the value that how much w2 affecting the value of this part and this part? Okay, so this is basically how much dz. Okay, what is dz2? dz2 is equal to loss got affected by the value of z2, right? So we need to know how much z2 got affected by w2. Well, the answer is this, which is the dot product of the a1. So that's why we do the dot product between the z2 and then a1, because that is how much this value affecting the loss value. Next, we need to find the db2. Okay, and one more thing, actually, we need to divide this by the amount of data that we have. So like this, so that we preserve the amount of data, not the amount of data, but the amount of value that goes through w2. Okay, so what is db2? Which is okay, so this is the first, it's the same thing, but for now it is basically np dot sum of dz2, because again we need to know how much db affecting the value of dz2, because in order for us to know how much bias value affecting the loss, we need to know how much bias value affecting the z2 value, because again we apply the chain rule for this, and I guess that's it. We can run. Okay, I'm going to run this one. Okay, now after we get the dz2 here, so we get the, so now we're going from the loss and then from the A2 here. So we're going from the loss and then A2, and then we're going to DZ2, which is Z2, and then we're going from DZ2 to W2 and P2, which is here and here. Now we want to find how much the Z1 value. Again, we need to go back all the way to the start. So what is DZ2? Well, in order to find the value of how much, wait, not DC2 but DC1, in order to know how much Z1 affecting the, oh my god, the value of the loss, we need to know how much, okay, what is coming before the Z1. Well, we have the nonlinear activation function, so we need to know how much this value affecting Z1 value, and here we have a ReLU, nonlinear activation function, so we need to know how much A1 affecting the value of Z1, or that's of Z1. That's it. That's one. Okay, so what is Z1? Z1 is where is it? Not that one. Okay, so what is Z1? Z1 is the ReLU activation. So what is the ReLU? Where is ReLU? Okay, so if you see what ReLU is, we need to derive. We need to know how much ReLU affecting Z, and to know that we need to derive the ReLU, just like what we did in the nonlinear activation function. Okay, so if you see this graph of ReLU, okay, let's do the little logic of calculus. So what is this line? It's just a straight line. It's just a linear line, right? So if we input a data here and we have the output here, and we want to compare the data from here and to here, the value, the difference value, like the slope of the value, is always B1, right? Because this is just a linear line, which means in every coordinates it has the same kind of slope, so it's just 1, and so it's just 1, right? And in this part, everything is basically 0. So this is 1 for the positive value. The difference is not as big. The slope is basically 1, and for the positive value, right? Okay, the slope is 1 for the positive value because this is just a linear line, while in the negative value, all of the slope, all of the value becomes 0 for the negative value. So we need to return Z is greater than 0. So what's going to happen here? Okay. Okay, I'm going to do this. So what is going on here? If Z is greater than 0, means that this is true, right? Is equal to true. So this is kind of like a Boolean data type, and if Z is less than 0, then this is false. This equation is false, right? Like for example, if I have Z is equal to 0.2, is this correct? Is this true? Well, it is true. But if I have negative 0.2 is greater than 2. Is it true or false? Well, it is false, and that's why we want this z value. And in Boolean, if we convert Boolean into integer, 0 is false, oh my god, and 1 is true, which is the value that we want. Okay, so we need to run this program. Okay, so now we know how much a affecting the value of z, which is the derivative of this value is. Oh my god, I'm sorry. So we need to operate np dot the dot product of, oh my god, the dot product of w2 and the z2 multiplied by the value derivative. Okay, because z1, what is z1? The value of z1 depends on the value of w2. Okay, and the value of z1 is also depend on the value of the dz2 here. So again, we going back. So we have the loss, and then we have the a here. We have z2 here, and then we have, okay, so this is basically I'm sorry. Okay, I'm going okay, what am I saying? So we have z2 here, and then we going back, we got w2, and then we got the p1 and p2 here, and then we go back, we get the z1, and z1 is the z1 value really depends on the a1 value. So this is basically the a1, this part is the a1, and this is the dz1, because we need to know how much all of this value affecting this way. Okay, I think I have the example here for this particular, for this particular okay, so no, for this particular part, okay, now what is the value before this part? So the loss with the weight, not the loss with the weight. So basically this derivative value is basically this: how much a got how much z affecting the value of a. Okay, and that's the derivative value, the value of loss. So that is dz1. So let's run this. Why not? Oh, what is happening? Of the derivative value of z one. Okay, now we need to find the w1 and db1. So what is the value of this part and basically this part? How much this affecting the loss value, and how much this affecting the loss value? So we need to divide by the amount of data first, and then we also divide this amount of data first, and basically we do the same thing. We do the NP dot product between the DZ1 with xtrain dot transpose, because again whatever, okay, so how much did the W1 affecting the loss? Well, it is depend on how much this one and this one, no, this one and this one. So this is how much, okay, how much this value affecting this. Well, it depends on this value and this value, and throughout this value we're going to go for him for here, here, and then here, here, and then here, and then here, and then going here. So this is what the how much W1 value affecting the loss value, and for the MRE dot sum of DZ1 basically. Okay, the P1 value affecting the loss value. So let's run this now. Oh my god, what is happening? It's not, oh my god, sum. Okay, so we get this all of the value. We get know how much all of this affecting. Okay, now we get how much all of the learnable parameters, learnable there's affecting the loss value, and the learnable parameters is basically every parameters that we initialize, which is V1, W1, P1, W2, and P2. Okay, so what happened now is we need to update the learnable parameters. Okay, so to do the update of the learnable parameters, we basically, okay, we update W1, we updating the value of P1, we updating the value of W2, and we updating the value of P2, right? So what is W1? Well, W1 is the previous W1. Okay, so this is basically okay, I forgot where it is. Okay, so this is, okay, remember this is the gradient descent formula. Okay, so this is the gradient descent formula. We basically following this formula here. So it's going to be the previous value, which is W1, which is in our case it is the random value, which is the initialized value, subtracted by the learning rate. Oh my god, learning rate multiplied by the W1. Okay, so we need to define the learning rate. Learning okay, let's see 0.1. Why not? Okay, what is the learning rate? Learning rate is basically how much faster our gradient descent, not our neural net, learn. So the bigger the learning rate, the faster our neural net learning. But then of course, the bigger it is, the less accurate the bigger value also mean the less accurate the prediction. Not the prediction, it is the less accurate to the global minimum, which is, in our case, it is basically the lowest value for the loss, value. So yeah, so that is the learning rate of W1, and basically everything is also the same. So it's going to be learning rate multiplied by dp2, dp1, and then b1, no, b1, oh my god, W2, and then learning rate multiplied by W2, and then P2 is going to be learning rate multiplied by dW2, dW2, oh my god. So okay, what does this mean? It means that the new parameters is equal to the previous parameters subtracted by how much we can learn based on how much the previous parameters affecting the loss value. Does this make sense? I hope it makes sense. So let's start. Okay, so now we complete the gradient descent process. Okay, so basically I'm making this demo of gradient descent and applying, initialize the weighted bias, and then for propagation probability distributions, which is the softmax probability distributions here, and we get the loss with the mean squared error loss. We get the dz2, we get the in-type backpropagation to get the dw, db, and then dw1, and then db1, and then update the parameters here. So first of all, let's initialize this part, and then going forward, and then let's see the loss. Well, we get this loss, okay, and then we going backward, update the parameters, update all of these parameters, and then we going for propagation again. And now let's see, is the loss value is going to be decreased, and the answer is yes, the value is decreasing. So we go back, we update the parameters, and then we going forward again, and then we get the reducing amount of loss. Okay, now let's see, let's code the entire, let's put it all together. So basically it's going to have this initialization of the weighted bias, which is W1. It's going to be np.random.ran of the n and the amount of pixel. Then p1 is going to be np.random.ran n of 10 neuron, and each neuron is going to be have one bias value. It's going to be w2 and then np.random .ran n, and it's going to be 10 neuron, and then whatever the amount of input from the previous layer, then it has p2 of the np.random.ran n, and it's going to be the same. Okay, and then we have forward propagations, but this time, oh my god, what am I doing? Alright, but this time we put a for loop for the amount of iterations, for amount of iterations. So for I in range of iteration, so let's see, let's have iteration of I don't know, 30. So we're going back and forth 30 times basically. So we are going to forward oh my god, forward prop, and it's going to be z1 is equal to the np.dot product between the w1 and then the x train plus the bias one, and then we are going to have a1, which is the value, the np.maximum here, np.maximum of z1 and 0, and then we're going to have z2, which is going to be np the dot product between the w2 and the dot product between w and a1, not plus the p2, and then we are going to have a2, and then a2 is going to be the softmax here, which is the e to the power of value divided by the sum of all of those e to the power of value in every index. And then we get a loss, we are going to use MSE loss, which is np.sum so loss dot sum dot np dot square the square of where is it, one hot label, and then the prediction that we have, one hot label, where is one hot label, and the prediction, which is a2, divided by the amount of data that we have, and then print the loss. Okay, now that is the loss, and then we go to back prop, and back prop is going to be dz2 is equal to a2 and one hot one hot label. Now we are going to have dw2, and it is the dot product of the z2 and then a1 dot transpose, and then np dot the dot product of the z2 and then a1 dot transpose. Oh my god. And then we are going to have dw2, and dw2 is going to be a m dot np dot the sum of dz2. We are going to have dz1, and dz1 is the derivative value, the np dot dot product of the dz1 of the w2 and then dz2 dz2, and then the ReLU, the derivative of ReLU, and the derivative of ReLU is basic ReLU derivative. So the ReLU derivative is basically whatever the true is the Boolean value of either 1 or 0 between z1 greater than 0. So wait, this is not okay. That is dz1. Now dw1 is going to be 1 divided by m multiplied by and p dot the dot product between dz1 and then x3. The dot product is c1 and x3 dot transpose, which is the input, and then db2 is going to be 1 m and p dot sum of dz1. I hope all of this is correct. Now update the parameters. And it's going to be w1 is equal to w1, right? It is capital, right? Yeah, w1 learning rate. Let's put the learning rate here. It's going to be 0.1. Okay, learning rate multiplied by the dw1. Okay, and then p1 is going to be p1 separated by the learning rate multiplied by db1, and then for the w2 is going to be w2 learning rate, oh my god, multiplied by the dw2 dw1. Okay, and then for the p2 is going to be p2 divided by the learning rate of the dw2 capital pw2. Okay, so let's try to run this. I know it's going to be an error. Okay, m np dot sum. Oh my, it is. Okay, so let's run this and see. Okay, so as we can see, the loss value is getting reduced, which is from 1.69, and after 30 iterations here we get to the 0.89, which is we're getting the value basically going to the global minimum. We're reducing the loss value, which is the exact same, the exact same thing that we want, which is just like the gradient descent process here. We going down to the, so we're going down like this, and all this value is also going down to like this, and and this is what we want inside our gradient descent. So I guess this is the correct implementation. Okay, now let's put this neural net. Okay, so this is the neural net, and this is the entire process of the neural networks that has 10 neurons in the first hidden layer, and then it also have 10 neurons in the second hidden layer or the output layer. and we got this value, the loss value, the reduced amount of the loss value using the MNIST dataset. Okay. So yeah, this is the correct implementation, and we are using, for this case, we are using the mean squared error loss. And so yeah, this is what you get. Hi. So basically, we've done everything that we've already applied in the first segment, like in the early segment, like which is something from the forward propagations and the backward propagation, the loss value, and then the entire gradient descent process. We already break down everything that we already know. So in this segment, I want to introduce you to something called optimizations. Now, in these optimizations, we are going to study 3 types of optimizations. So the first optimizations will be the momentum, and the second optimization will be the RMS prop, and the third optimization, which is the most famous optimizations, is called Adam. So if you wondering why do we need to apply the optimizations, so here I have you can see this as the gradient descent, but in the you see it from above compared to like this. This is the example of the gradient descent that we have, and this is the global minimum, and this is also the example of gradient descent that we have. And so this is similar with this kind of example. So the thing in the middle is the global minimum, which is something that we want to reach in the gradient descent process. And in the gradient descent process, we actually have this kind of a oscillation. We want to have the oscillation of this going up in the positive vertical direction and then going down in the minus vertical direction, and then we slowly going into the middle here, which is the lowest value, which is the lowest value of the gradient descent, the global minimum. And obviously, if we see this kind of a shape, this kind of a image, we want to have this vertical axis movement. So we want to slow the vertical axis movement, because in this first part, in this early part of the movement, of the vertical movement, we have such a big move in the vertical movement, right? So we want to slow down, and we want to reduce the amount of vertical movement. Like we are going to reduce the amount of vertical movement, and we want to get faster in the horizontal movement. So instead of having such a big number for the vertical movement, we want to have a big number in the horizontal movement, and we want to have a low number in the vertical movement, and then we want to have again a big number in the horizontal movement. So this is the momentum formula. So in the momentum, you compute the dW and then the dB, which is going from the back propagation on current mini patch or the current patch. So if you are using, like for example, patch gradient descent, where you have the entire data as an input, you can still perform these optimizations. Okay, so we are going to have a new variable called VDW, which equal to beta times VDW plus 1 minus beta times dW, which is the the variable that we get from the backpropagations. And then we also want to compute VDP, and it's going to be beta times VDP plus 1 minus beta times dP. And when we want to update the weight and the bias, which is the W and then the P value, so the new W value is going to be W negative the learning rate times VDW, and the bias is going to be P is equal to P minus alpha times VDW. So obviously the alpha is the learning rate value that we have. So instead of going from this kind of movement, from this wasteful kind of movement, we are going to get this very efficient movement where we have, slowing down the vertical movement, and then we have a faster movement in the horizontal axis. So in this kind of a movement, we get to the global minimum much faster and much efficient compared to this kind of movement. Okay, so this is the momentum optimization, and if you want to read the momentum paper, they introduced the momentum in this paper called on the importance of initialization and momentum in deep learning by Ilya. So if you don't know who Ilya is, he's basically like the brain behind the OpenAI. He's basically the brain behind the ChatGPT. And we have James Martins, George Dahl, and Geoffrey Hinton. So if you want to have more deep understanding of the momentum optimizations, you can go to this paper. And we are going to code all of this formula in the programming part, so you don't have to worry if you still doesn't understand all of this. Okay, so that is the momentum optimization. Next we have the RMS Prop momentum, RMS Prop optimizations. So again, we have the similar case of the gradient descent, where we want to make the vertical movement going slower, and we want to make the horizontal movement going faster to get into the global minimum. So RMS stands for root mean square. So okay, I don't know if you see this. Okay, so in order to use the RMS prop, we need to compute dW and dB, which is the value that we get from the backpropagations, and we are going to need a variable called SDW and SDB. So in the SDW is going to be beta times SDW plus 1 minus beta times dW squared. And while in the SDB is going to be beta times SDB plus 1 minus beta times dB squared. And in the updated version of the W and the bias, we are going to have W minus learning rate of alpha times dW. Now we want to divide this dW value with the square of SDW plus epsilon. While with B we are going to have W. Wait, this is not W. Okay, I made a mistake here. This should be P. This should be P minus learning rate of alpha times dW divided by the root of SDB plus epsilon. Okay, so I forgot to mention, actually, in this momentum the value of beta is 0.9 positive. It's going to be 0.9 positive value. And in this part of this optimization in the RMS prop, the beta is also 0.9 value. So we are going to have 0.9 times SDW plus 1 minus 0.9 times DW squared. Okay, just remember the beta value is 0.9 value. Okay, so here's the intuitions behind the RMS prop. We want to have the small number of DW. Okay, we want to have the small number of the DW, and we want to have a high number for the DB. Okay, so here's the intuitions. You can imagine if we have a big number here, if we have a small number in the SDW, we get a big number, a big value for this learning rate alpha, right? And when we have a high number learning rate of alpha, you can imagine like this horizontal movement is getting represented by the W. So if we increase the amount of the learning rate alpha, we want to have the faster movement in the horizontal part, and this is getting represented by the learning rate of alpha, while in the DW we want to have a big value for the SDW. So if we have a big value of the SDW, we are going to have a small number of the learning rate alpha, and it would slow down the movement in the horizontal axis. So you can see like the movement of the learning rate alpha on the W part is going faster, and the W part is getting represented by the horizontal part, and the learning rate of the B is getting represented in the vertical part, in the vertical axis. And if we have this SDW as a big number, we are going to have alpha a small number, which is something that we want. We want to slow down the value in the vertical movement. And so, oh yeah, the epsilon value is just to keep this value so that we doesn't get the value of 0. So you can use a very small number for epsilon because it's just to keep the mathematical like formula, so that we don't have to divide this this dw with 0. So again, by making this vertical axis going slower, and by making this horizontal axis going faster, we get this kind of movement inside our gradient descent, which is the same kind of movement that we have in the momentum. We want to have this smaller movement in the vertical, but we want to have a big movement in the horizontal, and this is the RMS prop optimization is doing. Now if you want to read the paper for the RMS prop, I don't think they are having the RMS prop in an actual paper, like in getting introduced in a paper. I believe the first introduction of the RMS prop is in a lecture, in a neural network for machine learning lecture by Geoffrey Hinton with Nitish Srivastava and Kevin Swirsky, and this is the first introduction of the RMS prop. You can go down, where is it? I guess this is it. So this is like the first introduction for the RMS prop. It's getting introduced by Geoffrey Hinton, which is the name that also contribute in this momentum optimizations. And the first usage of the RMS prop optimization is in this paper called Generating Sequences with Recurrent Neural Networks by Alex Grave from the Department of Computer Science, University of Toronto. So this is the first usage of RMS prop in a paper, while this is the first introduction of the RMS prop. So if you want to get a deep understanding of RMS prop, I'm suggesting you to read this lecture and to read this paper. Okay, so that is the RMS prop and the momentum. Now we finally get to the most I would say this is the most famous optimization compared to the RMS prop and momentum. So this is the ADAM optimization, right? So the ADAM optimization. So ADAM stands for Adaptive Moment Estimations. And here's how you can use the ADAM optimization. So first of all, we are going to have VDW and SDW for the ADAM parameters, and we also want to have VDB and SDB. So on iteration of t, we compute the dw and db using the current mini batch or the batch. So we don't have to use the mini batch. We can just use the batch gradient descent. First, we want to calculate VDW. Okay, so the ADAM optimization is basically the combination of RMS prop and momentum. So ADAM is basically just like, okay, we have a really good optimization, like why not combining them in one kind of optimization, and it's called ADAM. So first of all, you compute the VDW, and it's going to be beta 1 times VDW plus 1 minus B1 times DW. And we are going to compute okay, this should be VDB. Okay, this is my mistake. This should be VDB is equal to beta 1 times VDB plus 1 minus beta 1 times dB. And again, the dW and then the dB is going to be the value that we get from the back propagations, and then the beta value is going to be, okay, so we have to kind of a beta value. The first beta value is for the VD, and then the second beta value is for the SDW, and for the SDW and then the SDB. So in the first beta value, we are going to have 0.9 value, and in the beta 2 value, we are going to have 0.999 value. Okay. Now, if you feel like you are familiar with this, of course you are familiar with this, because this is basically the momentum algorithm. So this is the VDW and then VDB, and we compute the momentum formula here in the VDW and then VDB, and we also compute the formula of the RMS prop SDW and SDB here. So the SDW is just the RMS prop formula, which is beta 2. So you can see the beta 1 value is for the momentum value, and beta 2 is for the RMS prop value. So it's going to be beta 2 times SDW plus 1 minus beta 2 times dW squared, and in the SDW we are going to have beta 2 times SdP plus 1 minus beta 2 times dP. Okay, this is also should be dP squared. Okay, I made a lot of mistake. I can't believe I made a lot of mistakes. So okay, after we get the momentum and the RMS prop formula for the VDW, VDP, and SDW and SDP, we want to have this VDW corrected. So corrected mean after the bias correction. Okay, so VDW corrected is going to be VDW divided by 1 minus beta 1 to the power of t, and we want to have VDW corrected is equal to VDW divided by 1 minus beta 1 to t. And we also want, so this is the momentum, and this is for the RMS prop, which is SDW corrected is equal to SDW divided by 1 minus beta 2 to t. And similarly, we also going to compute SDW corrected is equal to SdP divided by 1 minus beta 2 to t. Now this is the updated version for the W. So the W is going to be W minus the learning rate alpha, minus the learning rate alpha times VDW corrected. So if we are using the momentum, we are going to stop here, but because we are combining the momentum and the RMS prop, we also need to divide this VDW corrected value with the SDW plus the square value of the SDW corrected plus the epsilon value. And now the epsilon value is just going to be a very small number, just to keep this value not going into zero value. We can have 10 to the power of 8, and this is also the value that the creator of the paper for Adam optimization recommended. So that is the W update. Now for the bias update, we have P minus learning rate of alpha times VDP corrected divided by the square value of SDP corrected plus the epsilon value. Okay, so this is the optimization for Adam. And if you want to read the Adam optimization paper, you can go in here. This paper, it's called Adam, a method for stochastic optimizations. This is created by Hendrik P. Kingma from the University of Amsterdam and Jimmy Leipa from the University of Toronto. So yeah, this is the Adam paper. This is the RMS prop first usage paper, and this is the lecture for the RMS prop, and this is the paper for the momentum, and these are the formula for the momentum, for the RMS prop, and for the Adam. So in the next part of this video, we are going to implement all of this optimization from the momentum, and then RMS prop, and then finally we get to Adam. So yeah, let's go to the coding part. Okay, so now let's create the optimization for the MNIST from scratch here. So first of all, let's create the hyperparameter. So it's going to be the learning rate, of course, I want 0.01, and we need beta 1. It's going to be 0.9. So this is basically this part, this hyperparameter here. Okay, so we are going to have beta 2 is going to be 0.999, and epsilon is going to be 1e negative 8, I believe. Alright, so this is beta value for our momentum, and this is our beta value for the RMS prop, and this is small value to prevent division by 0. Okay, so let's run this. Now let's create the momentum optimizations. Okay, so if we look at again, we need to create VW and VDB. Okay, so let's create VW and VDB. So VW1 and VB1 is equal to np.zeros underscore like W1 and np.zeros like B1. Okay, so here we have two hidden layers, which is the W1 B1, which is the first layer, and then W2 and B2 as the second layer. So we need to create VW1 and VW2. VB2 is equal to np.zeros of like of W2, W2 and np.zeros like of B2. Okay, this is the, I guess this is like the parameters, I don't know. So this is like the parameters, so let's just run this. Okay, so it's going to create an NP array that look like W1 for the VW1 and B1 for the VB1. So that's basically what happened. Then we need to write this part, this formula of the momentum. So okay, can I do this? Okay, so what is VW1? So let's VW1 is equal to beta 1, okay, beta times VW1 plus, okay, what is this nonsense, 1 minus beta 1 times dW1. And we do the same thing with the VB1. It's going to be beta 1 times VB1 plus 1 minus beta 1 times VB1. We do the same thing with the VW2, which is going to be beta 1 times VW2 plus 1 minus beta 1, oh my god, times VW2. Okay, and for the VP2 it's going to be beta 1 times VP2 plus 1 minus beta 1 plus multiplied by VP2. Okay, so this is the formula for the momentum. So let's run this to see if it's correct. It looks like it's correct. Now we need to write the parameter update. So it's going to be parameters update for momentum, and it's going to be W1 is equal to the learning rate. Okay, I can just do this actually. Minus equal to the learning rate times VW1. Okay, so for the P1 is going to be the same, is equal to the learning rate times VP1. For the W2 is going to be learning rate multiplied by the VW2, and for the B2 it's going to be learning rate times VP2. Okay, so let's see if the calculation is correct and I think the calculation is correct. So now let's put the optimization for the momentum inside our neural net. So we can just copy this cell and we are going to, so it's going to be let's see, gradient descent with momentum. So let's doing this. Okay, so first of all, again we can just copy and paste. So this is the parameters. Okay, let's just use it here, and for this one we are going to change the learning rate so that it match up with this one, and we are going to copy this one and we are going to place it here. So it's going to be here. Okay, so let's call this momentum formula here. So we are doing it after the back propagation but before the update. Now we need to change something because apparently in my gradient descent I'm using capital B instead of small p. So let's change that for the bias value, and it's going to be like this, and for this one it's also going to be like this. Okay, and for the update we can just copy and paste this one. Alright, okay, now let's run the gradient descent process. Okay, so it turns out I made a mistake around this part, so this part should be correct. So okay, so my mistake is this should be the value, which is something that we get from the from the back propagations. Okay, so now we can run this and see. Okay, so the loss is getting decreased, which means that the implementation of the optimization for the momentum is correct. So now let's move to the second optimization, which is the RMS Prop. Okay, so let's see. Okay, so here I'm going to have RMS Prop. Oh my god. Okay, so let's do just the same thing, which is the formula itself for the RMS Prop. It's going to be, say, DI record, yeah, and it's going to be this one. Okay, I want to do this. Okay. So first of all, let's create the SDW and SDB. So it's going to be SDW1, no, SW1, and SB1 is going to be np.zeros like W1 and np.zeros underscore like P1, and for the SW2 and SP2 is going to be np.zeros underscore like W2 and np.zeros underscore like P2. Okay, so this is the parameters for the RMS Prop. So let's run this. Now we get to the formula for the RMS Prop, and it's going to be this one. So it's going to be SW1 is equal to beta 2 times SW1 plus, oh my god, plus 1 minus beta 2 times dW2. So this dW2 is something that we get from the back propagations, and the beta 2 here and here is the value for our RMS Prop here. Beta 2, beta value for RMS Prop. Okay, so this is the SW1. So here is the SB1, which is the same thing. It's going to be oh yeah, I forgot the NP. So it's going to be NP dot square of W1, not W2, W1. Okay, there's a lot of things that could be mistake here. So I need to be very careful. It's going to be beta 2 times NP dot square of dP1 with capital P. So it's going to be SW2, going to be beta 2 times SW2 plus 1 minus beta 2. Okay, what is this nonsense? Okay, so beta 2 times NP dot square of it's the dW2. Okay, so for SP2 is going to be beta 2 times sp2 plus 1 minus beta 2 times np dot square of db2 db2. So let's run this. Let's see if it's correct. So this is the correct implementation. So let's write the parameter update for RMS prop, and it's going to be this one. So the W1 has become W1 minus the learning rate of alpha times W divided by the square root, the root value of SDW plus the epsilon. So it's going to be W1. It's going to be W1 minus learning rate of alpha times the W1. Okay, so the W1 divided by the NP dot square root. Oh my god, what am I doing? NP dot square root of S W1 SW1 plus okay, I should be doing like this, plus epsilon. Should be do like this. Okay. Alright, so we are going to prevent the division by 0 for the dw1 by adding the epsilon value. Okay, so that is for the w1. So for the p1, it's going to be pretty much the same, which is learning rate times the p1 divided by the np dot square root of of s p1, oh my god, plus the epsilon value. So for the w2 is going to be w2 minus learning rate value multiplied by the value of the w2 divided by the value of np dot square root of sw2 plus the epsilon value. And for the p2 is going to be p2 learning rate alpha and dp2 divided by the value of np dot square root of sp2, yeah, sp2 plus epsilon learning rate plus epsilon. Okay, I guess this is correct. So let's try to run this. Alright, so now let's put all of this RMS prop optimization inside our gradient descent. So it's going to be gradient descent with RMS prop. Alright, so again, let's copy the code of the gradient descent here and let's put it here. Now let's copy this parameter for the RMS prop and put it here. Why not? And let's copy the formula for the RMS prop and put it after the back propagation and before the update. Okay, now we are using this update for the RMS prop. So let's copy this and put it here. Okay, so well, let's run this. All right. So we also reduce the amount of the loss. We go from 1.73 to 0.7, which is a good value. Now we apply the gradient descent with RMS prop, and we apply the gradient descent for with also the momentum optimizations. So now let's apply the last optimization, which is the Adam optimization, which is basically just the combinations between the momentum and the RMS prop formula for its optimizations, and it's going to be a lot. So okay, so let's make Adam. Okay, how do I doing this? Okay, I'm just going to do this. So it's going to be Adam optimizations. So first of all, we are going to initialize the value of momentum. So initialize momentum and RMS prop values first. Alright, so let's create the M1. And okay, so let's just create the v w1 and v b1 is equal to np.zeros like of w1 and np.zeros of like of p2 ap1. It's going to be the same thing with v w2 and v p2. It's going to be np.zeros underscore like of w2 and np.zeros underscore like p2. So this is the momentum. So now we create for the RMS prop, and it's going to be SW1 and SB1. It's going to be np.zeros underscore like of W1 and np.zeros underscore like of B1. And for the SW2 and SP2 is going to be the same thing, which is np.zeros underscore like of W2 and np.zeros underscore like of P2. Okay, so let's run this. Okay, and now, so this is the formula. Oh my god, for Adam. So first of all, we need something called T, and T is going to be 0. Okay, so you know what, let's put T is equal to 0 here. So this is going to be the parameters for the Adam actually, and in Adam we are going to add the value of T by 1 each iterations. Okay, so first of all let's apply the momentum parameters first. So it's going to be v w1 is equal to beta 1. Okay, so remember this is the momentum of a formula. So it's going to be beta 1 here times VW1 plus 1 minus beta 1 times dW1, which is, this is what we get from the back propagations, and we are going to get VW2, and it's going to be beta 1 times VB2 plus 1 minus beta 1 times dB2. And similarly, I'm going to get, we have VW2 is going to be beta 1 times VW2 plus 1 minus beta 1 times dW2, and last value is going to be VB2. Okay, so what is going on here is B1, not, oh my god, I made a mistake. Okay, so it's equal to beta 1 times VB2 oh my god, what is this nonsense? 1 minus beta 1 times dB2. Okay, so this is for the momentum. Okay, so this is for the first moment estimate of atom, and then we apply the RMS prop. So it's going to be RMS prop, which is going to be the second moment estimate inside of this atom optimization. So it's going to be SW1 equal to beta 2. Okay, so remember this is beta 2 times SW1 plus 1 minus beta 2 divided by we are doing sorry, so it's going to be NP dot square of the dW1 yes, dW1. Okay, so we do the same thing. So it's going to be SP1 is equal to beta 2 times SP1 plus 1 minus, okay, I don't know if you can see this. Okay, so beta is going to be beta 2 multiplied by the NP dot square of S is going to be dB1. Yeah, it's dB1. Oh my god. And we do the same thing with SW2 is equal to beta 2 times SW2 plus the value of 1 negative beta 2 times the np dot square of the w2. It's not it's p1. Okay, so so for the s p2 is going to be beta 2 times s p2 plus 1 minus beta 2 times np dot square of dp2. Okay, so now we get to the bias correction, something called the bias correction inside of the Adam optimizations. It's going to be the bias corrections. So it's just going to be phi w1 underscore corrected is equal to is equal to phi w1 divided by 1 minus beta 1 to the power of t, which is this value. Okay, so we are doing this for all of the momentum value. So corrected is going to be not p2, it's p1 phi p1 divided by 1 minus beta 1 to the power of t, and then it's going to be phi w2 corrected is equal to phi w2 divided by 1 minus beta 2 to the power of t, and we have phi p2 corrected is equal to phi p2 divided by 1 minus beta, not beta 2 to the power of t, so it's going to be beta 1. Alright, and we also do the same thing with the RMS prop value for the bias correction, and it's going to be, just the same as w1 corrected is equal to as w1 divided by 1 minus beta 2. Remember, this is for the RMS prop to the power of t, and for the sp1 corrected it's going to be sp1 divided by 1 minus beta 2 to the power of t. Let's do the same thing with the corrected, and it's going to be sw2 divided by 1 minus beta 2 to the power of t. Then for the sp2 corrected, it's going to be sp2 divided by 1 minus beta 2 to the power of t. Okay, now that is the formula. Now we get to the so let's run this. Okay, I know it. Okay, so there's no yeah. Okay, so let's run this, and then let's run this. Okay, now it looks like it's correct, so why not? Now we write this part, which is the parameter update of the Adam. So it's going to be parameters update for Adam, and it's going to be w1 is equal to w1 minus the learning rate of alpha times it's going to be vw1 corrected divided by vw1 corrected divided by this part. So it's going to be np dot square root of the s w1 corrected plus the epsilon value. So okay, I'm gonna do this. Okay, so that is for the w1. So let's go for the p1. P1 is just the same thing. It's going to be p1 learning rate times the vp1 corrected divided by the value of the np dot square root of sp1 corrected plus the epsilon value to prevent the zero division. For the w2 it's going to be the same thing. It's going to be w2 learning rate of alpha learning rate times vw2 corrected divided by the value of np dot square root of sw2 corrected. Wait, this is not. Oh yeah. Oh yeah. It's correct. Epsilon. And then it's going to be p2. It's going to be p2 learning rate multiplied by the vp2 corrected and divided by the np dot square root value of the sp2 corrected plus the epsilon value. Alright, sp2 corrected. So let's see if it's correct, and I guess it's correct. So you know what, okay, so let's put everything. So it's going to be gradient descent, just like what we did earlier. So it's going to be gradient descent with Adam optimization. Alright, so let's copy the gradient descent. Where is it? Okay, so let's copy this gradient descent. Let's put it here. And now let's put everything here. So we initialize everything. Let's put it here, why not? And let's put the formula for the Adam after the back propagation and before the update parameters. And it's going to be like this. dp1 dp2, I hope it's correct. And this is the parameter update for Adam. Okay, I'm not gonna lie, I don't know if it's going to be correct or not because there's so many the same variable, so it's kind of a little confusing, you know. But you know what, let's see if it's correct. And it turns out, hell yeah, it's correct. So we reduce the learning rate from 1.74 to 1.73, I mean, we did get, this 1.67 for the lowest point in our generation. And okay, this is just my guess. I feel like we are facing some issue by applying the Adam, because right now I feel like the dataset is too simple and the gradation is too complex for our simple dataset, and I feel like that's why we get this kind of a not optimum optimizations. And it is very surprising that the best optimizations that we are using is the RMS prop, turns out. So when we are using two layers, when we are using the MNIST dataset, and when we are using two layers, so the first layer has 10 neurons and the second layer has 10 neurons, it is the best. So the best optimization that you can use is, turns out, the RMS prop. Okay, so I feel like that's it for the optimizations, and I hope you understand. So yeah. Okay, so we've been using the MNIST dataset. Now there is a problem. When we are using the MNIST dataset, again, the MNIST dataset only has 28 by 28 pixels. And it's such a small dataset. Like, there's no way. This is not like a normal images, what normal images look like. What images? Okay, I'm gonna do this. So this is what the normal images look like. It has color in it. So compared to the MNIST dataset, the MNIST dataset is such a small and simple data for us. So okay, I'm going to do this to see how much the MNIST dataset compared to the actual image. So okay, let's call this. Okay, I'm just gonna leave it there, leave the name there like that. So what is 28 by 28? Just okay, why is it so slow? What is happening? Okay, this is how much the MNIST dataset data. So this is 784 is the amount of data that the MNIST dataset has. Now the MNIST dataset, okay, so this is the interesting part. The MNIST dataset is a grayscale image format image. So what does that mean? It means that it only has, which means it only has 3 channels for one image. For one image. Okay. Alright, so the MNIST dataset only has, so for one image of the MNIST dataset, this is the exact amount of data that they have. Now compared to the real image, so let's see. So this is what the real image look like. It has color in it. So okay, so what do I mean by only has? Oh no, it is only has one channel. It only has one channel for one image. So the MNIST dataset only has a value for either it's white or black. That's it. Okay, so this is what the MNIST dataset look like. Okay, because there's no color in the MNIST dataset, and in a regular image we have color. So what the color image actually okay, so what is the color image data look like? So I have an example here. So this is such a big image. As you can see, it has the width of 2455 and 54, sorry, and the height is 1227 pixel. Okay, so how much is this value? This is basically just like what the MNIST dataset. It's just the amount of pixel that it has. Okay, so let's see how much the amount of pixel that it has. Okay, so it has what is this? 300,000. It has 300, 1,000. Wait, now. Oh no, it is actually. It has 3,011,058 amount of pixel. Now, here's the problem. In order to get a color image, you need to have 3 channels for one image. Okay, so in order to have a colored image, you need to have 3 channels. And each channel represent a color. And in a lot of image, this 3 channel is red, green, and blue. Okay, so you can see that this value is actually only for one channel of an image. So you can see like this image can have a layer, so and each layer represent a color. In the first layer you have a representative for the red value, and then the second layer you have the representative for the blue value, and then in the third channel you have the representative of the green value. Does that make sense? So here you can say that this value is only for one channel. Like for example, okay, I'm going to give you an example. Okay, that's not what I'm meant to do. Okay, so right, red channel has this value, blue channel has this value, and the green channel has also this value. So now the questions become how much this image how much data this image has, right? So we can just calculate by doing this value got multiplied by 3, because 3 represent the channel, right? The RGB channel. So let's run this and see how much this channel has. So it has 9 million. It has 9 million okay, 300 and no, it has 1 million 330. Wait, is it 1 million? Is it 9 million? So it has 9,033,174 amount of data inside of one image. Compared to the MNIST dataset that only has 784, this amount of data is insanely big. It has 9 million plus value in it, in one single image. Now, if you go back to the our, where is it? So there's no way that we are going to use such a simple neural networks to calculate this amount. Where is it? This amount of data, and this is only one image. Like the MNIST dataset has 60,000 amount of data, and in this part it has only one image. So you can imagine, like, we have for example, we have 10 dataset, and then we have 100 dataset, and then we have 1,000 dataset. Like, there's so many amount of data that we are going to calculate, and the problem is it will damage. The problem become the large amount of dataset can cause a expensive computational calculation, and the more expensive the computational calculation we get, the longer our neural network is going to train. Especially when we have this kind of a simple neural networks. There's no way that this simple neural network is going to learn properly. Like, you can imagine, like, it has 9 million as an input, and then in the next layer you only has 10 neuron. There's too much data for it. So it's not just that it is expensive for the calculation. The problem is also okay, I'm gonna do this. Okay, the problem is, if we are using a simple neural networks, there's going to be a lot of important data get lost, and maybe, and or not maybe, and there's a lot of less important data get calculated. So this is the point. We need to separate the important data and the less important data. So what do I mean by that? Okay, in this particular image, let's say we only care about the bridge. So the important data is the bridge, right? So this is the important data, the bridge. So the less important data is the sky, is the ocean, is the land, is the landscape, like it's the the hill, the beach, everything. So we only care about the bridge. We don't care about the background, such as the sky. We don't care about the cloud. We don't care about the ocean. We probably don't care about the shadow of the bridge itself. We don't care about the land. We don't care about the mountain here. So also the same thing, like, okay, I have another image. Let's say we only care about the cat. So we don't care about the wood here, we don't care about the background here, we don't care about whatever this is, we only care about the cat. So we need to reduce the less important data and we need to highlight the important data. So I'm going to do this. Okay, the goal become, okay, we have a goal, and the goal is highlight the important data and ignore the less, oh my god, important data. Okay, so how can we do this? How can we ignore the sky? How can we ignore the ocean and only focus on the bridge? Just the same thing with this image again. How can we ignore the background and only focus on the subject that we want to classify, that we want to process, that we want to calculate, which is the cat? Now there is something called where is it? I forgot where is it. So there's something called convolutional. So here I have an example. Let's say I have this matrix, and this matrix has 6 by 6 amount of data. So I'm going to apply something called filter or a kernel. And okay, so the purpose of applying this filter is to reduce the amount of data that this matrix has. Okay, so how can we calculate this, this formula? So okay, I have 6 by 6 of an image, or you can say it is a matrix, and I'm going to apply a filter or kernel that has the size of 3 by 3. Okay, and in this filter I have 1, 1, 1, and then 0, 0, 0, and then negative 1, negative 1, and then negative 1 as a value. So I'm going to get the, okay, so I'm going to multiply this filter with this amount, with this, with this 3 by 3 matrix here. So I'm going to multiply this filter, which is here, with 3, 1, 2, and then 0, and then 5, and then 7, and then 1, and then 8, and then 2. Okay, so I'm going to multiply all of this, and then I'm going to get, and then I'm going to sums up all of this value, and then I'm going to get, negative 5. So again, I'm going to calculate. So it is like a, matrix multiplications. So it is going to be a matrix multiplications. So we have, well, it is not actually a matrix multiplication. It is more like a element-wise matrix multiplication. So here I'm going to have 3 multiplied by 1, and then 1 multiplied by 1, and then 2 multiplied by 2. So this is not a matrix multiplication. So this is an element-wise matrix multiplications. And then I'm going to have 0 multiplied by 0, and then 0 multiplied by 5, and then 0 multiplied by 7, and then negative 1 multiplied by 1, and negative 1 multiplied by 0, and then multiply, and then negative 1 multiplied by 2. And then I'm going to sums up all of those numbers, and I'm going to get 5. And this 5 value is going to be in the first new matrix, the first index of this new matrix. Okay, so after I calculate this part here, okay, you know what, can I actually I don't know. Okay, can I use like something like this? I'm actually curious. Can I? Okay, so this is the first calculation, right? So, and this is basically this, right? Okay, can I zoom in? I don't know if I can zoom in. I cannot zoom in. You know what, whatever. And then after I calculate this part, which is here, next I'm going to move here. So I'm going to calculate this part with this part. So it's going to be 1, it's going to be 0, 5, 7, and then 1, and then 8, and then 2, and then 2, and then 9, and then 5 gets multiplied by this filter. Just the same thing with what's happened here. And then after I done, and okay, I'm going to calculate, get the element-wise multiplications value, and then sums up all of those number, and then I get -4 for this image, for this matrix. And then I'm going to move again. So now I'm going to calculate this, okay, this with the filter that I have. So now I'm going to have 1, 8, and then 2, and then 2, 9, 5, and 7, 3, 1 of a matrix. Calculate with this filter, and then of course I'm going to move again here. I'm going to move again, and then just do the same calculation, and then I got 0 and 8. Okay, so after I calculate all of this, I'm going down instead of going going right. Instead of going in a x x direction, I'm going to the y direction. So now I'm going to calculate this part. So it's going to be 1, 2, 0. Okay, okay, it is wrong. It is wrong. Okay, should be like this. Alright. Okay, now so I'm going to calculate 1, and then 2, and then 0, and then 5, 7, 1, and then I have 8, 2, and 3. It get multiplied by this filter or a kernel, and then I get just the same kind of calculation, and then I get -10. So again, just do the same thing, and then we just do the same thing. We go into the x direction, and then after we done with the x direction, we going down to the y direction. So okay, I'm going to do this. Okay, can I go back? Alright, so now I would have this value, and we go from 6 by 6 of an image, and then we apply, not image, but well, you can see this as an image, but you can see this matrix, 6 by 6 matrix, and then I apply the filter of a kernel of a 3 by 3 matrix, and then here I get a 4 by 4 matrix, and the value become -5, -4, 0, 8, -10, -2, and then 2, and then 3, and then 0, and then -2, -4, -7, and then -3, -2, -3, and then a -16. So we not just change the size of this matrix, we also change the value inside of this matrix. Okay, now we're going from 6 by 6 by applying 3 by 3 filter. and then we get 4x4 filter. We actually can calculate the dimension of the output. So here I have the calculations. Okay, I don't know if you can see it. I hope you can see it now. And the formula is n minus f plus 1. So n stands for the dimension or input. So here in our case the input dimension is 6, and then we have f. F is the filter dimension. In this case we have 3, so we are going to have 6 minus 3 plus 1, and then we get 4. And then you can do the same thing with the this second part, which is we are going to get 4x4 dimension. Okay, now you're probably wondering, okay, I have this kind of filter, but can I have another kind of filter? So this is has 1 1 1 and then 0 0 0 and then negative 1 negative 1. So can I have another filter? Well, yes, you can. In fact, there's a lot of filter that we can use. So for example, okay, this is probably not very intuitive right now, but when we get to the programming part, we are going to apply all of these filters in a real image. So you are going to see why we need this filter. So first we have the pre-width filters, and the pre-width filters we have the horizontal and the vertical. So in the horizontal one we have negative 1, negative 1, negative 1, and then 0 0 0, and then 1 and 1 and 1. And this is the so what do I mean by horizontal and vertical? So when I said horizontal, it is going to filter the horizontal value inside of an image. And when I say vertical, well, just what it said, I'm going to filter out every vertical value in one image. Again, I'm going to show you what's going to happen in a real image when we get to the coding part. But for now, let's go through all of these filters. So in the vertical filters we have 1 and then 0 and then negative 1. We have 1, negative 0, negative 1, and then we have 1, 0, and negative 1, which is just the the flip version of the horizontal part. It just kind of makes sense. Now we have Sobel filter. For the horizontal part in the Sobel filter we have negative 1 and then negative 2 and then negative 1, and then we have 0 0 0, and then we have 1 2 and 1, and this is going to filter out the horizontal value of an image. And then we have the vertical value for the Sobel filter. It has 1 and then 0 and then negative 1, and then we have 2 0 negative 2, and we have 1 0 and negative 1. It is going to filter out the vertical the vertical value inside of an image. I kind of realized that when I say horizontal, I'm doing this where I should be doing this. Okay, so next we have Laplacian filter. So we are going to have negative 1 and then negative 1 negative 1 and then negative 1, and then we have 8 and then negative 1 negative 1 negative 1 negative 1. So the whole concept of this Laplacian filter is that we are going to put such a big number in the middle and such a small number in the other part of this matrix. And we want okay, so the goal is we want to focus out what's going on in the middle of an image inside of a 3 by 3 part of the image. Again, this is not very intuitive right now, but when we get to the coding part, it is going to be kind of makes sense. And then we have Robinson compass mask, and we have a lot of Robinson compass mask. We have Northwest that has negative 2 negative 1 and then 0 and then negative 1 0 and 1 and then 0 1 and then plus 2. So this is going to be filter out the northwest of an image. And then we have the north, the northeast, the east, the southeast, and then the south. Okay. So okay. Next so in the Robinson compass mesh we also have, you know, the southeast and the west. Now similarly with the Robinson compass mesh we have Kirch's compass mesh. So so the direction is like a compass. If you still don't get it. So we are going to have northwest, north, and then northeast, and then we're going to have east, southeast, southwest, and then west, and then we have south direction. Okay, I guess so that we are not going to, you know, get confused by why do I explain all of this, why do I need to explain all the filter part. Let's go to the coding part and let's see why we are going to apply all of this filter. Right, so now we are going to apply the filters into an image. Now first of all, basically visualize everything that we learn, you know, visualize the theory, basically the theory. So first of all, let's import some dependencies. Import dependencies. Okay, again, the main goal is to visualize the theory. So I'm going to import NumPy SNP. I'm going to import CV2. So this is a library for computer vision, basically. A library for computer vision. And we are going to get, you know, deep into CV2 in the next segment. Not in the next segment, but in the, you know, later segment. We are going to import matplotlib .pyplot SPLT. We are going to import torch, and we're also going to import torch.nn.functional sf. We're also going to import I think that's it. Okay, so let's run this. You know what, let's call this file filter image. Alright, now let's create the function for the filter. Create function for the filter. So we are going to define convolve. Let's name this convolve, and I'm going to take image file path, and I'm going to take the filter. So what is going to be the filter? Like, for example, I can say that, okay, I want an image and then I want to apply the pre-weight filters, or I want to apply the Sobel filters. So this is the image and this is what filters that I want. And I'm going to take the title as a default because we are going to visualize the image and the filters. Okay, so first of all, let's read the image. So in order to read the image, we need to create a variable called image, and in image we are going to read the image using the cv2.imread, and this is obviously is going to be the image image file path here. And okay, I want to change this image into a grayscale image. Read underscore grayscale. So I'm going to change the original image into a grayscale image. So it's going to be like the RGB image into the grayscale image, which is only has one kind of a one dimensional of an image, just like what I explained earlier. And then we are going to define the filter size. So it's going to be, if in our example, it's going to be the kernel size. In this case, it is 3x3, right? So let's define the size, and it's going to be convolve is equal to np.zeros of, so it's going to be image.shape 0 minus filter.size, and it's going to be plus 1. Is this, I hope it makes sense. Filter size, no, okay, first we need to define the filter. No, okay, I'm sorry. So we need to define the filter size, and it's going to be filter dot size of 0. Not size, shape of 0. So what this is going to do? Filter, not filter. Filter. Yeah. Okay, I'm going to explain this later because I'm not yet creating the filter yet. So it's going to be make sense later. Okay, so now let's create an array to store the result, basically. The result of the filter. So basically, okay, the size of this array is going to be this one, which is n minus f plus 1. So it's going to be x minus m plus 1 and y plus m plus 1. It's minus n it's mn. Okay. Alright. Next, we are going to create a variable. Let's name this convolve, and it's going to be np.zeros of image.shape minus filter underscore size plus 1. And it is the same thing, which is image.shape of 0, not 0, of 1 minus the filter size plus 1. Filter size, I'm going to do this, plus 1. np.zeros. Okay, wait. Filter size. Wait, this one is closing this. This one is closing that. Okay, now let's create, well, the filters performing the filters. So it's going to be for I in range of image dot shape is equal to, and then for j in range of image dot shape of 1 is going to be, okay, so what's going on here? Basically we are going to, going in a horizontal direction first, which is in the j, well, not in the horizontal direction, we are going to get into the vertical direction. So, and this is represented by I, and the image, okay, so the image dot shape is basically the output of the image dot shape is the horizontal axis, and the image dot shape in the second disk, which is this part in the first index, is going to be the vertical. Wait, no, no, I can be confused. Vertical axis and then the horizontal axis. So when we go into the vertical axis, which is going up and down, first we are going to calculate in the first vertical, and in the first vertical axis we are going to perform everything inside of this vertical axis in the horizontal axis, and then after we done with this horizontal axis, we going down and then performing the horizontal part. We going down the vertical part, and then we going down, and then we going in the horizontal part. Does that make sense? So okay, let's try convolve of I and j. So we are going to replace everything inside of this index and this index with image of I until I until dot I plus filter size and then we are going to get j until j plus filter size times filter, and then we sums up all of this number. Filter size. We basically performing okay, this calculation here. We sums up all of those number. Okay, I'm going to explain it later, so that it's more clear when everything is already in place, basically. Okay, we try that, and then accept. Okay, I'm going to accept exception. Yep, that's correct. I'm going to do pass. Okay. Now, be careful. We need to still inside of this. We need to go outside of this for loop. Okay, we need to go outside of this for loop after we complete the for loop. So it's going to be convolve torch.tensor. So it's going to convert this number into not this number, this array into a tensor. is going to be the convol. And then let's apply the activation. So I want to use convolve is equal to the f.relu, and it's going to be convolve. Okay. And now let's visualize. Visualize the image. Now let's create the figure, and the axis is going to be bld.subplot. It's going to be 1, 2, and then the dpi is equal to 120. So bld.subtitle is going to be title, which is something that we get from here. It's going to be title, and the axis of 0 dot show of image, and the C map is equal to gray. Okay, and the axis of 0 dot axis is going to be off, and the axis of axis 0 set title is going to be the original image. So we're going to compare the original image and the filtered image. Original. Okay, and in the axis of 1 we do the same thing and show. So instead of image, we are going to show in the convolve, which is the filtered image that we've create. Convolve, and the C map is going to be gray. Axis of 1 is dot axis, it's going to be off, and then axis of 1 dot set title is going to be filter. So we have the original and we have the filter one, and we are going to pass, and basically that's it. I hope that's it. So let's try to run this. Is there any mistake? Okay, now let's create a filter. Create the filters. Okay, I mean we can choose the filters that we want. So for example, okay, I want to do this. Okay, I want to, just for the sake of trying, I don't know if this part is correct, so let's just create one filters. Let's use the Sobel filter, why not? Sobel filter, and it's going to be the Sobel horizontal, and it's going to be np.array. So we're creating array, and inside of this array is going to be -1, 0, and 1, and then wait, this is why. Oh my god. Okay, it's going to be negative 1, 0, and 1, and then negative 1, 0, and then 1. Okay, so that's our filter. Now let's testing the filter. I hope it's worked out. So let's call the convolve function, and okay, we need to import image. So I'm going to import the image from my Google Drive. Okay, I'm importing this image from my Google Drive. You can use any image actually. Okay, I get the image. Now I want to get the filter. So now let's try to filter out the image. Okay, so here's what the Sobel horizontal filter does. Now that we successfully filter out the original into this part, okay, I want to explain everything that happened inside of this function. So first of all, we read the image in a grayscale image. So okay, if you want to see the actual original image, can I open the image? Okay, so this is the original image. So this is the original image, and then I convert this RGB image, basically convert the RGB image into the grayscale format. So basically what happened is it goes from an image that has three-dimensional kind of color, from three-dimensional color into one-dimensional color, because it has RGB, which is from the red and then green and then blue part, and then I just convert into one single dimensional color. So we already reduce a lot of the data inside of this image. So instead of using the original image that has a lot of data, so we filter out those data into just one kind of a dimensional data. And then for the filter size, so this is our filter. If we see the Sobel horizontal dot size, not size, shape, oh my, dot shape, going to be 3 by 3. Okay, now I just want to take the first number, because okay, filters is always, you know, you need to use, okay, I'm going to do this. I don't think you can use in filter or kernel size. You need to use the same, you know, width and height. So for example, you cannot use you know, 4 by 3 kind of filter, or you cannot use, you know, 3 by 1 kind of filter. Well, I don't know about that. 3 by 2 filters. The filters is always the same value for width and height. So it's going to be, it's either 3 by 3 or 4 by 4, you know. So I'm going to take this size, which is, it's going to be 3, right? So this value, filter size in this part, is going to be 3, because I'm only taking this 3 by 3 of an array in the first index of the shape kind of a function, and which is 3. Okay, so it's going to be 3. Okay, now to store the result in the filter. Okay, so the x and y is basically this image. Because we don't know the, you know, the dimension of the image, right? We don't know. It could be a random image, so we cannot predict the output for the filters. So we don't know if it's going to be 4 by 4 like this, or is it going to be I don't know what it is. So we need to, you know, prepare the filter output of a shape based on the image itself. So what is the image shape? The image shape could be I don't know, like for example, MNIST Dataset. Again, I'm going to be using a lot of MNIST Dataset. So the MNIST Dataset is 28 by 28. But MNIST Dataset is such a simple image, and we don't know how big this image is. So we just, you know, take this number, and it is different from the MNIST Dataset. The width and the height in the, you know, in a casual image is not the same. It's not always be the same. It could be 28 by 50. It could be, you know, 120 by 50. It could be 120 and 300. It could be anything. So we don't know the output of this filter. So we need to create the output based on the image. So this is why we apply the image.shape, which is also, this part is the horizontal, and this part is the vertical, which is the width and the height. So, you know, we are applying this formula here. So the width minus the filter size, which is 3 plus 1, by the height minus the filter size, which is 3 plus 1. And now let's performing the filter. Okay, so first of all, we are going to get through. Okay, how can I want to do this, and I'm going to close this image. Okay, so the convolve part is just so that we can track the dimension. So it's going to be, np.zeros is going to be a 0 number inside of this convolve array currently. So we need to change, or we need to replace all of this number by all of these filters. So it's going to be I, and I is going to be going from up and down, and for the j is going to be from left and right. So so first of all, we need to change in the index of the I, in the index of the horizontal part, in the vertical part. So everything in the vertical part, and then we are going to change everything in the horizontal part with image. So I until the filter size. So what is I? Again, I is the the vertical part. So I plus filter size. So it's going to be this one, which is in this case it is going to be 3 by 3. So okay, this 3 by 3. So this 3, and then the j part. The j is going to be this 3. Okay, this 3, right? And then we apply the filter by multiply by the filter, which is here. The filter. What is the filter that we use? It's the Sobel filter. So it's going to be, because we are using this kind of notation inside of a Python, is going to apply the element-wise multiplications. So it's going to be 1 multiplied by this. I already explained that. And then we are going to sum up all of those numbers, and we get 5. And this 5 is going to be getting inside of this particular index inside of the convolve variable. So if you still confused, what happened is, for I, which is the 0th index, and it's going to be this 0th in the vertical directions. So it's going to be, calculate everything inside of this domain, and then we are going to move the j, and the j is always moving. Okay, so the j is always moving. So we're going from this part into this part, into this, and then we're going from this part into this part. So the j is always moving. And when we finish with this j, we are going down. When we are finished with the the horizontal part, we are going down to the vertical part, going down and then perform the horizontal part again. Basically, everything that I already explained is getting performed in this part. Okay, now the one thing I have not yet shown you is that what is the difference between the horizontal filter and then the vertical filter, etc. So let's create another filter, and why not? So we've created the Sobel horizontal. Let's create the Sobel vertical, and the Sobel vertical is going to be np.array, same thing, and it's going to be what is it, 1, 2, and 1, It's going to be 0 0, oh no, 0 0 and 0, and then -1, oh my god, -1, -2, and -1. And you know what, I want to create another filter. Let's create the pre-weight filter. So it's going to be pre-weight horizontal, and it's going to be np.array of -1. Oh wait, wait, I'm not. Okay, so I made a mistake. So this should be okay. I made a big mistake. So this should be the pre-weight, and okay, the Sobel filter, -1, and then this should supposed to be -2, and then this okay, should be like this, right? Okay, so that is the horizontal part. So let's create the vertical, vertical, and it's going to be 1 1 1 and 0 0 0 and -1. Oh my god, -1 and negative, oh my god, and -1. So that is okay. So let's create the Laplacian filter, and let's take some of the compass mask. So it's going to be the Laplacian filter. It's going to be Laplacian. Okay, np.array. Oh my god, I forgot np.array, and it's going to be, what is it, -1 and -1, and then -1, and then a high value in the middle, and then -1, and then -1. So okay, now let's use, I don't know, the northeast maybe good. Okay, Robinson compass mass, and I want to use the northeast, Robinson northeast, and it's going to be np.array of 0 and -1, -2, and then 1, and then 0, and then -1, and then 2, and then 1, and then 0. So there is the compass mass for the Robinson. Okay, I want to let's create the southeast for the Kirsch compass mass. Kirsch compass, oh my god, Kirsch compass mass, and it's going to be Kirsch, let's pick one. Let's use the southeast. The southeast filter. So it's going to be np.array of -3, -3, and -3. There's going to be 5 0 -3, and it's going to be 5 5 and -3. I made a mistake. That's it. I made another mistake. Okay, I hope it's correct. So let's try this. Okay, you know what? I made a mistake, so let's fix that mistake. Okay, now I have my filters. So let's apply and see what each filter does. So I have the Sobel, not just horizontal, I have the vertical one. I also have pre-width. So it's going to be pre-width horizontal. Oh my god. And then I also have pre-width vertical, and then I also have a Laplacian. So it's going to be Laplacian. Wait, what did I name it? Yes, Laplacian. And then basically applying all of this filter and see the difference result for a single image. And then this. Oh my god, I made a mistake. Okay, I'm gonna do this. Alright. Okay, so let's run this one, run this one, basically run everything. All right, so this is what I mean by filtering the vertical part, filtering the horizontal part. So let's compare the Sobel first. So we have the horizontal and the vertical. So as you can see, in this filter, in this horizontal filter, we are not seeing the vertical part inside of this image. We only filtering the horizontal part, which is the right and left, which is the the width of an image. And in the vertical part, it's like we see this, we filtering every vertical aspect of this image. It's like, you can imagine this like you have a flashlight. So it's either you use the flashlight in the horizontal direction or in the vertical directions. If you are using your flashlight in the vertical directions, everything in the horizontal part is not really matter, because that's the part, because in the horizontal part is the only part that gets the light, from your from your flashlight. And so this is the pre-width horizontal. So difference from the okay, let's see the difference. I don't see much of a difference, I'm not gonna lie. I'm not see much of a difference from the pre-width and the Sobel part. But the Laplacian, there's something really interesting happening. It's like detecting the edge of the original image. So this is what happened when you put a big number in the middle of your array, of your 3x3 array. So it's going to be filtering out, it's almost like a filtering out everything, but not everything, if that makes sense. it's like you are using the flashlight in a z-axis, in a front and back axis, instead of left, right, up and down. And oh, this is very different in the northeast, so it's going to be like in this direction, right? This direction, from here going to here, while this part is almost the same, southeast and the northeast. So okay, so this is what filtering an image. We are extracting from the original image. We are extracting everything that important inside of this image. So for okay, can I where is the image? Okay, let's say that I want to focus on the subject, which is the dog here, and let's, I don't care about the background, I don't care about this grass, I don't care about this tree, I don't care about the background. Basically, I just care about the dog. So we can filter the image. We basically want to reduce this data, so we change it into the grayscale image. So instead of the RGB image, instead of we are having the three-dimensional image, we now have one-dimensional image. And inside of this one-dimensional image, again, we only care about the subject, which is the dog, and we're filtering out everything that we care. So now we have this dog right here. So this is why we are using the filter. So we reduce the amount of data. So that the calculation or the computations is not very heavy when we perform the neural networks for a big image of a data. Okay, now the reason why I'm explaining a lot about the filter is because of this. There's something called convolutional neural networks, and basically we are going to apply a lot of filters for one images. So here I have another example for convolutional. So this is convolution over volume. Now so in this example I'm using where is it? I'm using the gray images, and then I apply the filter. But now what if I have the RGB image? Well, here I have an example. So this is a 6 by 6 by 3, this is a 6 by 6 image that has 3 channels, which is the RGB dimension for the red, green, and blue. So if I want to apply a filter for this image, I also need to apply the same amount of dimension. So in this example, I need to apply a 3 by 3 filter. I want to apply a 3 by 3 filter, and I need to have also the same amount of a filter for the dimension that I have. So here I have the RGB, which is 3-dimensional. So, and in the filter part, I also need to have the 3-dimensional filter. So the first filter, the first dimension is going to be filtering the red part, and then the second filter is going to be filtering the green part, and then the third filter is going to be filtering the blue part. Okay, and so after I get all of those number, the filtering value, I just need to sum up all of those number. So in the first in the first dimension, in the first axis, I just need to sum up in the red filtering part and the green filtering part, and then in the blue filtering part. This just the sum of combined dimension, and I'm going to still got 4x4 kind of a output for the filters. Does that make sense? So I'm going to, you know, sums up this one, this one, and this one, and then I get this one. I'm going to sums up this one and this one and this one to get this one, and then I do it, and I'm doing all of those into every dimension. So okay, now what if I want to apply a multiple filter? So again, I have this, a similar example with this part, but now I want to apply two filters, which is the vertical edge detection and then horizontal edge detection. So still I have a 4x4 by 1, because this is sums up of this, all of this filtering, right? So I get 4x4 from here, and then I got 4x4 from here, and then I just, you know, stack all of those filter, and then I get 4x4 by 2. So 2 is the amount of filter applied. So I'm applying 2 filter, and the output is 4x4 by 2, and this 2 represent the amount of filter I applied. Okay, does that make sense? So okay, now I want you to look at this so that you really understand what filtering is actually doing. So I have input of 6x6, okay, and I have the kernel size, which is the filter size in this part, which is you know, this filter size, basically this filter size, all of this, and I have 3x3, and the output is going to be 4x4, right? So we already learned all of this. Now there is something I want to mention. In filtering images or convolutional images, we actually reducing the amount of dimension. So we have input of 6x6, and then we have the output of 4x4, which is reducing the amount of shape of an image, right? So now the questions become, what if I want to keep the amount of dimension? So I have the input of 6x6, and then I still want the input of 6x6. Well, we can use something called padding. So what padding did is basically, so it adds a new dimension. So we have a 6x6 input, and then we add the padding into the input, and now the inputs become 8x8. So it's just a random value around an image, okay? It's a random value around the image, so that we preserve the value output from the input. So we have the input of 6x6, and then we still have the value of 6x6. Okay, now you're probably wondering, why do I need to, okay, why do I want to apply the padding? Well, in a convolutional neural networks, what if you want to apply a lot of convolutional? Again, the main reason why we are using the convolutional neural networks is we want to reduce the amount of value. And yes, it is getting reduced, but what if the value becomes too small? What if the value becomes too small, right? Because sometimes you're not just going to apply one kind of a filtering, one kind of a convolutional. You're also going to add another convolutional. So you can imagine something like, okay, this is the first, okay, I have the example here. So you have the input image, and then you apply convolutional here. So in this example, they have 36 by 36 image, and then the convolutional is going to be 9 by 9. Okay, and then they're not just doing one convolutional, they're doing 3 convolutional. They're doing convolutional with the kernel of 5 by 5, and then they're doing convolutional again. So when we're doing the convolutional, we're not just going to apply one time. So you can imagine, like, this is the first, so this is the first convolutional. So you can imagine, like, this one, okay, is this particular part. Okay, this is the hidden layer one, and then we obviously got the output of 4 by 4, right? So now we have the output of 4 by 4 like this, right? So if I want to apply another convolutional, the output that I get is 2 by 2, which is if it's an image, it's going to be the data is going to be too tiny. The data is going to be too small. So this is why we are using padding. So that we want to reduce the value of data, but not the dimension amount of the data. So we preserve the amount of dimension. Okay, and there's one thing that I want to mention about filtering, and that is something called stride. So, in a traditional way of filtering an image, we just need to move from one by one of a pixel, right? But there's something called stride, which is you jump like with the amount of stride that you have. So in this example, I have the stride of 2, so I'm jumping 2 pixels instead of 1. So if you see, I'm jumping 2 pixels, so I should be like here, right? So do you see my cursor? I hope you see it. So I should be here in the next part in the horizontal axis if I'm moving the horizontal axis, but I'm skipping this part because I have the stride of 2, so I'm skipping 2 pixels at a time, and this is happening in the vertical axis. I'm jumping 2 times 2 pixels, right? So okay, so stride, I'm not using stride very much. I don't know, I don't feel like applying stride is that important, but it's worth to mention, I guess. Okay, so back to the filter. We see this example, right? So I'm applying a multiple filter into one images, just like what we did here. So I'm applying Sobel filter vertical, the pre-width vertical filter, the pre-width horizontal filter for one single images, and this is what's called the convolutional neural networks. So back to this image. This is the example of a convolutional neural networks where you apply so many filters for one single image, and that's it. Actually, that's it. That is what convolutional part of in a convolutional neural networks. So okay, in order to apply a convolutional neural networks, in order to apply a convolutional into neural networks, instead of having this kind of a value, we need to change this value into a learnable parameters Now okay, I'm going to write it. In order to apply convolutional or filter into neural networks, okay, in order to apply convolutional or filter into neural networks, the value for the filters or convolutional, okay, I'm just gonna call it convolutional, needs to be learnable parameters. Okay, so instead of having this kind of a parameters, right, this number, we want, for example, I will have convolutional 1, let's say, and the value is going to be np.array of w1, w2, w3, and then another w4, w5, w6, and then w7, w7, and then w8, and w9. So this is going to be a random number in the first initialization in our neural networks, but then it will learn to match the value. So this is a learnable parameter. So this is the exact same thing that we've learned in a in a neural networks. Wow, where is it? Okay, so you can imagine like you applying all of these learnable parameters inside of a filter. So this is what the convolutional neural network is. So here it's not going to be a Robinson filter. It's not going to be a Laplacian filter. It's not going to be Sobel filter, but it's going to be a random number. And all of this random number here, all of this random number is going to learn within the process of a gradient descent in the neural networks process. Now this is what I'm talking about. So I have an example of a layer, of a convolutional layer. So this is 6 by 6 by 3 image. So you can imagine like this is the input, right? So we have the input, and then we apply the filter, just the same thing like what we did here. But because it's a neural networks, we also going to apply the activation function. So here we applying value, and we also need to apply the bias value. Again, if you remember, z is equal to w times x, which is the input, and plus b. So this is the x. So this is the input, and you can see this is as the w, and this is as the bias value. And now, and you can see the this as the output of the value of or the activation function, the nonlinear activation functions, and then we get this z. So you can see this now as a z. So we're applying two filter, and this two filter is basically w, which is the weight value, and then apply the nonlinearity function, and then add the bias value, and you get the z value. Just this is, we already learned this. Now, if you have 10 filters that are 3 by 3 by 3 in one layer of a neural networks, how many parameters does that layer have? So if I have 3 by 3 by 3, I would have 27 parameters, right? I would have 27 amount of a W, because this is a 3 by 3 filter that's going to be filtering an RGB image. So it's going to be in a 3 channel, because each channel is going to be filtering out each channel in a RGB image, right? So I'm going to have 27 parameters, which is the W plus the bias, and now I have 28 parameters. Now if I want to apply, okay, so this is only one filter, right? So this is only one filter, and we see this amount of filter, which is 2 amount of filter. We see also this is 2 amount of filter, vertical edge and horizontal edge. Now if I want to apply, for example, 10 filters, then I'm going to have 280 parameters. So for one, so in a, you can see this image, right? Wait, is it? I lost it. Okay. So you can imagine, like, this is my filter. This is my 3 by 3 filter. And then I want to apply 10 filters. So how much parameters, how much W that I have? Well, the answer is 280. So you can see this, where is it? So instead of just having, where is it? So instead of just having, you know, a little amount of W, just some couple of W, now we have 280 W as a parameters, right? So this is the summary of a notation for the convolutional. So F is the filter size in a layer. Okay, so S is filter size, and you have P as a padding size, and we already discussed about the padding part, which is you know, this one, to preserve the amount of dimension. And then you have the stride, and then you have the input, and you have the output. And so to get the output dimension, here's the formula. You have the N plus 2P plus F. So N is the dimension input, and then P is the amount of padding, the padding size, and then the F is the filter size, plus 1, divided by the S, the stride amount, and then plus 1. So this is going to be the next dimension for your output. Okay. So if you are kind of wants to guess, okay, if I have an image of a 6 by 6 image, 6 by 6 by 3 image, and then I apply this filter, 3 by 3 filter, and then maybe I want to apply, you know, 2 paddings, and then I want to apply 2 strides. Okay, so what is the output dimension that I have? So you can calculate the dimension that you are going to get with this formula. Okay, so this is the formula for the output dimension. Okay, now I have another example of a ConvNet, of a convolutional neural networks. So now imagine, again, this is just the another example, so that you really understand what I mean by this. For example, if I have 39 by 39 of an image, and it's going to be RGB image, so how much? So I want to apply a filter, I want to have a convolutional, and the filter size, the f here, again f is the filter size, is going to be 3 by 3, and the stride is going to be 1, and I'm not going to apply any padding, and I want to apply 10 filter. Okay, so this is the input image, which is 39 by 39 by 3, which is the RGB image. That's why we have 3 here, the amount of channel. Now by applying this formula here, this equation here, I get this. Now I get 37 by 37 by 10 because I'm applying 10 filters. Okay, so now, okay, so here I'm applying the formula that we get, which is n plus 2p plus f divided by s plus 1 is going to be 39, because this is the amount of pixel, and 0 is going to be the amount of padding, and then 3 is the amount of the filter size, divided by 1 is going to be the stride, and plus 1, and I'm going to get 37 for the output dimension. Okay, now I want to apply another filter for this particular output, so this output become an input, just like what we did in neural networks. So in the neural networks, if you remember, the input for the first hidden layer is the input. So the input of the first hidden layer is the original input, but the input for the second hidden layer is the output from the first hidden layer, right? So I want to apply a filter into this output, into this I don't know what you call it, into this convolutional part, right? Now I want to apply a 5 by 5. Okay, see, this is supposed to be 5, not 3. Okay, I want to apply a filter with the size of 5 by 5 and the stride of 2 and the padding of 0, and I want to apply 20 amount of filters. So just, you know, apply this formula, and then I get this kind of a dimension output. I have 17 by 17 by 20 because I have 20 filters. And now I want to apply another filter. So this filter is going to be 5 by 5 filter, and the stride is 2. And now I want to apply 40 filters. Okay, and if you look at the result, I'm going to have 7 by 7 by 40 because that's the amount of filter that I have. So if you see the result, it's going to be getting smaller and smaller and smaller, but the amount of dimension is going to get longer because the amount of dimension getting is just basic the amount of filter that we apply, and we apply a lot of filters. So in the first, in the first example, we apply 10 filters, and then we apply 20 filters, and then we apply 40 filters. So it's going to get longer in a channel dimension, in a channel direction. Okay, if we go back to this part, okay, if you see this part, so this is basically, so we're covering this part, right? This part right now, in this part, okay, in this particular part. They actually, so after we reducing the amount of data, now is the time that we apply the fully connected layer, which is just the regular layer that we apply in a regular neural networks. So this is going to be the input. So this is going to be our input, the output filter. So we have 7 by 7 by 40, right? 7 by 7 pixel that has 40 amount, and we have 40 amount of this 7 by 7 image, basically. So we are going to have this amount of input. So we can just multiply. So this is the width times the height times the amount of channel. So 7 by 7, which is 49. 49 times 40 is 1960. So this is going to be our input. So we have x1, x2 until x 1960 into a neuron, just like what we did in in the very first example. Where is it? So this is it's just a neuron. So but now we have 1960 amount of input. So we're reducing the data. Okay, so we reduce the data and we get this value. Oh wait, so we get this value, and now we apply the regular convolutional the regular fully connected layer with the amount of neuron, etc., etc. Okay, now I want to mention one more thing, which is something called pooling layer. So in the neural networks, in the convolutional neural networks, they always apply pooling layer after the convolutional layer. So what is pooling layer? It is basically, so I have this example. So I have 4 by 4 of an example, right? So this 4 by 4 is basically, I'm taking it from here. So you can see like I'm applying this one and then this one, I get 4 by 4, and then you can imagine like this is the continuation of it. So I have 4 by 4. Now again, I'm going to have a kernel, but inside of this kernel is going to be a value that represent. So okay, so in the pooling layer, there's two type of pooling layer, which is the max pooling layer and then the average pooling layer. So in the max pooling layer, I'm going to apply a kernel. So the kernel or the filter size that I'm going to apply is, in this case, 2 by 2 and the stride of 2. Okay, so this is the part of 2 by 2, right? This is the 2 by 2 in the first iteration, right? So I'm just gonna take the maximum value and then put it here, and then I'm going to move 2 pixels because I have the stride of 2. So just take another maximum value and then this particular part, and then I take 2, and then put it here, and then I'm just doing the same thing with this part. Okay, so what is the highest value here? What is the maximum value inside of this part? It's going to be 6, right? So I take this part and then take the highest value in this part, and then I take 3. So okay, so in an average pooling, you can just find the average value between those between all of these values. So what is the average between 1, 3, 2, and 9, and then put it here, and that is average pooling. I mean, it is a pretty simple. I don't think I need to explain it in a deeper kind of a explanation. But then again, okay, so if you still doesn't understand anything that's going on, it is completely fine. It is completely all right, because it is such a I wouldn't say it is a hard thing to understand, but it's just a lot. If that makes sense, it's just a lot. So if you're not understand all of this in one go, it is completely fine. And okay, so in the next segment we are going to apply all of this in a programming part. So I hope you going to be understand more about all of this when we actually applying all of this concept into the coding part. So yeah, okay, now let's create convolutional neural networks. I'm just going to do this from scratch. Okay, so we are basically going to apply all of this. Now, first of all, let's create the input. So the input is going to be okay, you know what, we need the numpy, so import numpy as nb. So let's run that. Alright, so the input is going to be nb.array, not array, random.ran, and it's going to be 10 by 1 by 28. It's 28. So what is it? So it's going to be it basically 10 filters for one channel. So this is a grayscale. I'm just gonna say it, grayscale of 28 by 28 pixel. Okay, does this make sense? Does this make sense? So okay, I'm just gonna run this. Now we are going to need okay, I don't know if I need the label. Okay, I'm not gonna need the label. So let's make the convolutional part. Okay, so first of all, we need to track the amount of M, the amount of channel. So M is the amount of image. So in this case, it's going to be 10 image, and the amount of channel, so it's going to be the grayscale channel. Okay, channel, and then the amount of the age of the previous, and then the amount of the width of the previous, and it's going to be input.shape. Okay, so this value is going to be M, so M is going to be 10, the number of channel is going to be 1, the amount, okay, so okay, no, it's going to, it should be like this. I don't want to get you confused. So 10 images that has one channel. Okay, so maybe this more made more sense. Okay, so this is the amount of image, this is the amount of channel, this is the age, which is the height, and then this is the W, which is the width. Okay, so M is going to be 1, N is going to be M is going to be 10, N is going to be 1, and H is going to be 28, and W is going to be 28. Okay, so let's print. It's going to be N to see if it's correct. Previous, and W previous. So let's see. Yes, it's correct. So okay, let's create. Okay, so we need to create the output dimension. Okay, so what is the output dimension? Okay, I'm just gonna it's not that good. Okay, so what is the output dimension? So we're just going to follow this formula. Okay, we are going to follow this formula. Now it's going to be new number channel, which is basically the filter. So it's going to be filter size, filter amount. Okay, okay, I need to so let's create the parameters. I forgot about the parameters. So we are going to have filter amount, right? So how many filters that we want? Like, okay, I'm just gonna use this as an example so that you can imagine. So let's say I want to have this kind for the example. So let's apply 10 filters. 10 filters, and then I'm going to have padding. So what is the padding? It's 0, and then the stride is 1. 0, and then the stride is 1, and then what else? So the filter size, filter amount, and filter size is going to be 3. Okay, so the channel is the amount of filter, because okay, so this is basically this one. So the new channel, which is the new dimension, is going to be the filter, right? So I apply 10 filters, so the new dimension is going to be 10. If I apply 20 filters, so the new dimension is going to be 20. So the new number channel is going to be the filter amount. That's why. Now what about the new height? So it's going to be let's say the integer value of n of height of the previous one times 2 times the padding minus the filter size divided by the stride plus 1. Okay. It should be filter size. So so again we applying this formula, right? So n plus 2 times p minus f plus divided by the stride or the s plus 1. Okay, so that is going to be the new height. And what about the new weight? So it's going to be the integer value of the n of the w or the previous. It's going to be 2 times the padding minus the filter size, and then it's divided by the amount of stride plus 1. Okay, now for the output or the convolutional, it's going to be nb dot zeros of m, which is the amount of images, and it's going to be the new number channel, it's going to be the new height and the new weight. The new weight, wait a second. Okay. Okay, I'm not what I don't want to do. Right. So now let's run this part. Filter amount is not defined, so I need to run this part first and then run this part. Okay, so let's see what we have. So let's just going to print the out convolutional dot shape. So what is the shape? Now we get 10 by 10 by 26 by 26. Okay, so how can we get this number? So this is the input that we have. We have 28 by 28, and it's getting reduced because we are applying the convolutional, and that's why this is getting reduced into 26 by 26. And 10, so what is 10? 10 is the new number channel because we applying 10 filter amount here, and because we have 10 images, so we have 10 images for the input, and that's why we have 10 here. So it's going to be 10 images that has 10 dimension, and each image is going to be 26 by 26 pixel. Okay, does that make sense? So I hope that makes sense. Now, since this is going to be a neural net, we need to apply the forward convolution. So the convolutional part for the forward propagations. So let's create the forward for the convolutional, and it's going to be, again, we are basically applying this. So this is the forward propagation in a convolutional neural networks, right? So we are going to apply all of this in a code. So it's going to be, so for every images that we have in range of the amount of images, or for every images, for every channel in range of the new number channel. So for every image, for every channel, and then we are going to apply basically this. We need to calculate the vertical axis and then the horizontal axis for each image. So it's going to be height in range of a new height, right? And it's going to be height start. Okay, I'm just gonna read for start. It's going to be the height times the stripe. Okay, and then the height n is going to be the height start plus filter size. So basically we are creating this part, right? So after we do that, we are going to create the for the width the weight. Okay, should I call it width or weight? Okay, I'll call it weight. For weight in range of the new weight. So it's going to be the same. It's going to be weight or start is equal to the weight times the stride, and wait, what? And then the weight, and it's going to be the weight start 8. It's going to be the weight start plus filter size. Okay, so now we are going to replace this. So for each images, for each channel, okay, and in every height and weight, so this part is basically the same as this part, but now we, instead of just the the vertical and then the horizontal, we also need to add the amount of channel and the amount of images. So this is what we are doing, and it's going to be np.sum of the input images, input of, so it's going to be like this, images. What is this nonsense? Input images and it's going to be, so for every channel we are going to doing this height start until height n, okay, and then weight start until the weight n, multiplied by w channel for every dimension, and then plus the bias of channel. Did it make sense? So we have not created bias in the W. So okay, so the bias in the W should be nb.random uniform okay, I'm going to do this. So we need to have a boundary of 1 divided by, so import the math. Okay, so 1 divided by the math dot square root of filter size is going to be filter size multiplied by filter size. Okay, uniform minus bound until bound, and it could be the size is going to be filter amount. So we basically making this filter this filter, but in a learnable parameters, which is the weight parameters. So instead of using this kind of value, we need to change it into this kind of value. And also we need to tracking the amount of filter that we are using. So this is what we are doing. So that is what we are doing here. So this is the amount of filter. Okay, so I'm just gonna finish this part. Filter amount and then channel amount. Size. np.random uniform size is equal to then the channel amount and then filter size. So and then we are going to have filter size again. Okay, so I have not yet have the channel amount, or do I? So I have the filter amount and I don't have channel amount. So what is the channel amount? The channel amount is going to be 1, because that is so yeah, this end channel, which is 1, okay, which is NC here. So this is channel amount, if that makes sense. So channel amount is 1, filter amount, so filter amount is going to be 10, channel amount is going to be 1, filter size is going to be 3, and then the output of the W is going to be np.zeros of filter amount and then the channel amount and then the filter size and the filter size. Okay, so that is the W. Let's create the bias, and it's going to be np.random uniform, and just the same is going to be bound, the bound, and it's going to be size of filter amount. Alright, and then we are going to have the bias output np.zeros of filter amount. Alright, okay, I hope this is correct. So again, we are creating the W. So the W needs to match out with the input, because we are going to perform these calculations, right? And we know what happened if we doesn't have the correct kind of a shape, which is what we learned previously about this one. So we need to be careful about the amount of the W and the bias, because we need to match out with this input here. So in this input we have where is it? Okay, so this is the input, right, basically. So this is the input shape. So this is the information that we have. It has 10 images, it has 1 channel and 28 by 28. So this is the filter amount, this is channel amount, this is filter size and filter size. Okay, okay, uniform. So what is uniform? So this is basically create, so the filter size is okay, how can I explain this? It creates like a boundary between of a okay, I'm just gonna nb.uniform. So it's going to be a distribution of a value, if I'm not mistaken. Okay, so it's going to be create a distribution like this, but in a uniform format, where you have this kind of a uniform format. I don't know how to explain it actually, but okay, so the goal is we need to have the correct amount of dimension, if that makes sense. Now if I run this part, okay, channel amount is not defined. Footer amount, channel amount. Okay, so I'm not okay. Channel amount. Okay, so let's run this. Oh my god, and why? Oh man. Okay, cut. Run this. Okay. Now let's see the output for the convolutional. So if it's if the calculation is correct, okay, so where is it? So we have this part for the input, right? No. So okay, so this is the input dimension. Okay, I'm just gonna copy this. Okay, I'm just gonna do this, and I'm just gonna do this, and I'm just gonna do this input dot shape. So this is what we want. So this is what we want. So previously we have 10 images that has one channel, and it has 28 by 28 pixels. So after we are doing the convolutional, the forward pass convolutional, we are getting 10 images, and each image has 10 channels because we have 10 filters basically, and we are reducing the amount of dimension, which is 26 by 26, and this is what we get. This is exactly what we get. Where is it? When we applying the correct formula. So again, this is going to be the learnable parameters. It's going to be W1, W2, WT, and then we are applying the bias value. Well, we are not yet applying the Rayleigh value, but it's going to be later on. But okay, I want to mention this. The main goal is so I'm going to make this. The main goal is to get the correct dimension, basically. Because okay, as you can see, it is very hard to keep tracking the amount of dimension, and this is why we have you know, where is it? This is why we have these equations, because we need to track the amount of dimensions for the output. So we have the input and then we have the output. So the output needs to be the correct amount of dimension, and the dimension is going to be based on the output on the input, right? And this is what the challenging part in the making convolutional neural network from scratch. You need to keep track the amount of dimension based dimensional output based on the dimensional input, and then you have to and not just that, you need to doing the correct kind of calculations. So the reason why we are using this is because we are going to apply what's it called, the multiplications for each index, the element wise multiplications, right? And okay, if you are confused what is this, so remember that we have a multiple dimension, so we are going to apply these calculations across every dimensions. So this is basically what these three dots mean. Okay. Okay, so the last thing I want to apply. Okay, so you know what? Let's finish. Where is it? Okay, so you know what? Let's finish this. So here we are using ReLU. But okay, so let's add the activation function. For this activation for convolutional. And okay, I'm going to do this. Alright, so after we apply the W and then the bias, of course we need to apply the convolutional, the non-linearity to it, which is the activations. So I'm just gonna use 10H. Why not? Because in NumPy they are having just a very simple 10H function that I can apply. So convolutional. So this is very similar with the regular neural network that we already did. So let's run this and we get the nonlinear value. Now let's apply the forward maximum pooling. Okay, let's see if I want average or maximum. You know what? Let's apply the average pooling. It's going to look like this. So in my example, I'm using, okay, where is it? Okay, so I have the max pooling for the this simple example. Now after we apply the convolutional, let's apply the pooling layer, and in my case I want to apply average pooling layer. So it's going to be average pooling layer, and again we need to track the amount of images, the amount of channel, the amount of height, and the amount of the weight of W previous. And it's going to be, instead of the input, it's going to be the out of convolutional. Okay, so if it's this part, so this is the input, because so this is convolutional and the input is basically the input image, but in the pooling layer the input is basically the output of the convolutional part. So it's going to be out convolutional dot shape. Okay, and the new number of channel, so we are basically doing the same thing. It's going to be filter amount, and then the new height is going to be the integer of an age previously plus 2 plus the padding minus the filter size divided by the stride amount plus 1. We are doing the same thing with the weight, and so this should be W. Okay, and let's create the output of the pool. So it's going to be np.zeros. So basically this is going to be the dimension that we are going to get, m, and then which is the amount of images and the amount of the new number channel, and then the width and the height, and the weight, new weight. It's going to be new weight. Okay, so for each images in range of m, for each channel C, no, it's going to be new number channel. For each images, for each channel, for each height, which is the vertical part in range of new height, we are going to apply the same thing that we did earlier. So height start is going to be height times stride, and then the height n is going to be height start plus the filter size, and then for the weight it's the same range of the new weight. It's going to be the weight start is equal to the weight times the stride, and then the weight n is going to be the weight start, weight start plus filter size. Okay, so for the output going to be for each images, for each channel, then for each height, and then the weight is going to be np dot. So because this is the average pooling layer, let's take the average of the each value. So it's going to be np.min out of convolutional on every images and every channel, and the height start until the end. Oh my god. And then the weight start until the weight end. Okay. And I guess that's it. Let's try to run this. And let's see if so let's print the output dot shape, and it's going to be okay. It reduced the amount of the input. So we have the input, which is this one. Okay, I'm going to. So the input that's going through the pooling layer is this one, right? So again, the main idea for the pooling layer is basically to reduce the amount of dimension itself. So we have the same filter, the same amount of filter, the same amount of images, but the dimension of the image, we're going from 26 by 26 into 24 by 24, and that is what the pooling layer did. It reduced the amount of dimension of an image. So okay, I'm probably gonna explain it too fast, but okay, so this entire part is basically the filtering part. Okay. If that makes sense. So this is the weight start. Okay, then this is the weight start, and this is the weight end in this particular part. Weight start, and this is the weight end. Okay. And this is the height start, and then this is the height end, and that's why we get this kind of, because plus the filter size. So you have the and the stride is 1. I don't know. I guess you need to, you know, write it down in the paper for your own, so that you actually understand. But it is actually quite simple. So this is basically doing this kind of a movement here, if that makes sense. And then in this part, you just, you know, replacing the 0 with the amount of value that you are inputting. If that makes sense. So yeah, I guess that's it for this part. So yeah. Okay, everybody. So we are going to continue with the convolutional neural network from scratch. So we get the forward propagation for the convolutional, and we get the activations, and then we get the forward average pooling for the convolutional. Now what happened after the, you know, convolutional and the pooling is the fully connected layer, which is just a regular neural networks architecture. So let's build the fully connected forward fully connected layer. Okay, So let's create I and C and the width and the height. So I is the amount of image, C is the amount of channel, height, and then the width and the height, and then width and the height. Okay, so it should be like this, and it's going to be output. So we are going to take this 10, 10, 24, and 24 value. So the I is going to be 10, the C is going to be 10, the width and the height is going to be 10. Okay. Now the width is going to be the width multiplied by the height and then multiply by the C. Okay, and then the height itself is going to be 4. Okay, so why do I do this? Well, because in a neural networks you need to flatten out the data that you have. Basically flatten the data. So the width and the height, so we're going from two-dimensional. Okay, it's like the MNIST Dataset. We have 28 by 28, right? 28 by 28 pixel, and I want to make this 28 by 28 pixel with one dimension into one dimensional array. So I just going to multiply 28 times 28 times 1. So this is what I'm doing. Again, this is for the input of the convolutional for the fully connected layer. Okay, I'm just going to see the where is it? I guess this is the one. Okay, so I'm just gonna flatten. So I'm just doing this 7 by 7 by 40. I'm just doing this to get the input. So each data can become an input. Okay. Now what I want to do is, okay, so the height is basically wait, what is the height? The height basically is just the amount of example that we have. So okay, I'm going to start to write the bound part. Again, just the same thing. So it's going to be nb dot square root of the width itself, and then the weight for the fully connected layer is going to be np dot random dot uniform, and it's going to be the low part is going to be minus the bound, and the height is going to be the bound itself, and the size is going to be the height and the width. Okay, so the bias for the fully connected layer is going to be nb dot random dot uniform, and the low part is going to be the minus the bound, and the high part is going to be the boundary high, and the size is going to be 1 minus, not 1 minus 1 with the width, because we only need one bias value for each neuron. Now for the out of the pool flat, if that makes sense, it's going to be out pool dot reshape of 10 and -1. So I want to keep the dimension basically, so that's what happened here. -1 just to keep the dimension, and A, which is for the execution of the fully connected layer, is going to be np dot of. So this is, so you know, np dot is, we're familiar with it, so we just, again, this is just a, you know, a normal neural networks calculations or formula dot flat, and then W, and then fully connected W, and plus the bias of the fully connected. Okay, and I hope this makes sense. So let's try to run this. Alright, the width np dot square the width, the height, for expected for, okay, what, but not for, but what do we have? Output shape, it's gonna be 1. IC width height output that, oh my god, that shape should be 4. I have this amount of value and this amount of value, so it is not matched out. What would I have? 10. Okay, this is not working because there's too many. Oh my god. Oh my god. I'm gonna do a shape of output that reshape output flat. Height and width. 1 width. It's not width, it should be the height, if that makes sense. Okay. Okay, so now, well, we get a that fully connected shape. So what is the shape now? The shape is 10 and 4. So it's going to be, so we have basically okay, so this one is the amount of neuron, basically, of neuron. That's it. So that is the 4 value. Now, okay, we need to create. So we've done this. So this is basically the fully connected part, and now let's create the probability distributions. So we're basically doing this, right, with this, which is the fully connected layer, which is just the regular neural networks architecture. So now let's create the probability distributions, which is it's just the softmax expression function, and for the softmax it's going to be np.exponent. I hope you remember what softmax is. It's going to be this and divided by np.sum of the exponent, np.exponent value for the fully connected layer, and we got the softmax value. So let's see softmax dot shape. So what is the shape? Softmax, it should be the same like this one. Okay, now in order to calculate the error, so let's calculate the error, or error. And in order to calculate the error, we need to create the one-hot encoding first. So let's create the one-hot encoding. So it's going to be label. Okay, I'm not gonna make it here. I'm just gonna make it. Where is it? After the input, basically. So I'm just gonna make it. So the one-hot encoding label. Okay. So the label is going to be np.array, and just going to be a random number 1 3 1 2 2 3 1 1 3 1. So how much was that? I don't know. 1. So it's going to be one hot. np.zeros. It's going to be label.size and the label.max plus 1. So I'll explain this already, and it's going to be one hot of np.arrange and the label.size and the label itself. So it's going to be, so the correct label is going to be 1 and one hot transpose is going to be one hot dot t and one hot dot transpose one hot. Just going to see 100 transpose and one hot underscore, not 100 transpose underscore transpose. Okay, so we have 4, just like what we did here. This is why I chose 4. We have 4 neuron, so we need to create a one hot encoding that the maximum value is 3, right? Because we count 0 value, we also count the 0 value, and that's why we create so this is basically 0 to 3, so you can add 0 in this part. Okay, now let's calculate the loss. Okay, again, if you still okay, if you doesn't understand so this is the goal that we did, the main goal, to get the correct dimension. So we are not getting, you know, actually a prediction out of this. So we just trying to tracking the dimension for the convolutional neural networks that we create from scratch, if that makes sense. So the loss is going to be, okay, let's create the patch size, and it's going to be softmax underscore shape of 1. So this is where you should pay attention. We need to keep track something called delta loss, and the delta loss is basically the softmax minus, so this is basically the loss, right? So this is derivative value of the loss, and the loss itself is going to be np.sum of the one hot, so the one hot encode times the np.log. So we are going to use the negative log likelihood. That's why we are having the log and the negative in the front. So this is going to be the negative log likelihood to get one value that represents the entire data set. So it's going to be softmax divided by the patch size, which is the amount of data that we have. So it's going to be negative log likelihood. Oh my god. Okay, so let's try to run this and see the loss value. I mean, we don't care about the loss value since we are not trying to predict anything, because we are using, you know, a random dataset and a random label. So okay, now for the big boy, which is the back propagation of the convolutional neural networks. Okay, all right, so we start from here, right? So we need to find the fully connected layer back propagations. So we need to go back, and it's going to be, so the gradient is going to be the gradient. So we need to keeping the track of the gradient for the W and the bias. So it's going to be the gradient for the fully connected layer for the weight, and it's going to be 1 minus 1 divided by the amount of value times the np.dot times delta L, which is the loss, dot T output flat. Okay, so I don't know if I can find the example, but we've gone through this already basically. So we are doing this basically, but I don't know if I can find the correct example. Wait, let me find the example. Okay, so the delta L is basically DZ, right? That's why we just, you know, find the value of the prediction minus the not the prediction, yeah, the prediction and the label. And now we're going back, and we basically doing the dot product of the loss and what happened before the loss. Basically that's what happened here. And what happened before the loss, well, it is the output of flat. So, and it's going to be So that's for the W, and this is for the bias of the fully connected layer. It's the same 1m np dot sum of the delta L and with the axis of 0. Okay, so the new delta L is going to be np dot dot of the delta L and okay, and the weight of the fully connected layer. So this is the backpropagation for the fully connected layer in the convolutional neural networks. And let's see the shape of the new delta L. Shape. So what's going to be? Okay. Now, so it's just the amount of neuron and the amount of data that we have, right? Now, amount of data that in a one-dimensional aspect on each neuron, basically. Now we get to the, so this is the gradient for the fully connected layer. Okay, I'm just doing this, not doing that. Gradient, fully connected layer gradient, and now we get to the average pool backprop. Okay, so it should be backprop. All right, now backpropagations. So we get this value of the delta shape, right? Now we need to create the out, and it's going to be np dot reshape of the new delta L, and it's going to be 10. Okay, so what is the output value for the delta shape? Six 24 24. So it's going to be the convolutional shape. So what is the convolutional shape? Because, okay, remember, so here's the intuitions. We have this max pooling layer, so the output of the max pooling layer should be the output of the pooling layer in a backpropagation should be the output shape of the convolutional layer. So what's the convolutional layer output? So conv dot shape. So what is the shape? So okay, so it should be like this, right? We should be use that shape. So it's going to be out the convolutional dot shape. So because this is going to be the output dimension for the pooling backprop, so it's going to be the same as the output for I don't know if you can say it. So it's going to be the output for the convolutional in forward, if that makes sense. Okay, so that is the out dot shape. So let's run this. Okay, so I'm not gonna lie, I'm basically making some mistakes and spending hours to fix it, but I'm not finding it, so I'm just starting over. And right now I have the filter amount of 6, and that's what I change. So basically everything is the same, but I have the but now I have the filter amount of 6 now. So we have the delta value, right, which is the loss value. So the loss value needs to be get reshaped. So the loss value shape needs to be the same with the pulling out of the output of the pooling layer, of the pooling layer. Okay, so this is what we did here, and let's try to run this. Okay, now that's why. Okay, so let's track the amount of images, the amount of channel, the amount of the height, and the amount of the width, and it's gonna be the out.shape. Okay, shape. And let's run this. Now okay, so after that we need to get the gradient value for the weight. Not the gradient value, but okay, so we need to calculate delta of the out, and it's going to be np dot reshape. No, we already done that. The delta out. Okay, so it's going to be the so the derivative of x, which is the derivative of input, so it's going to be np dot zeros of 10 and 6 and 26, which is the outer convolutional network. So it's just so I can do this actually out of the convolutional shape. So okay, for every images in range of the m, which is what we got from, which is the m value that we got from here, which is the amount of data that we have, the amount of image for every channel in range of the amount of channel for every height in range of the amount of height is going to be a height start, just like what we did earlier, and it's going to be height multiplied by the stride value. Okay, and then the height n is going to be height start plus the filter size. Okay, now for the weight in range of the n of the w is going to be the same, which is the weight start is equal to weight times the stride multiplied by the stride, and the weight n is going to be the weight start plus the filter size. And so this is the So we are using average pooling layer. So it's going to be average is equal to the delta of the output, right, for the image or the D out, not delta, but D out. So the D out is going to be image, and for each image and for each channel, image, and weight is going to be filter size multiplied by the filter size. Now for the filter average, it's going to be nv.full of the filter size and the filter size and the average. Now for the dx is going to be for each image, every channel, the height start until height n, and then the width start and then until the width, not the width. I should use the width, not the height. The width, not the weight, but whatever. So it's going to be the weight n, and we add the field average. Okay, if this is correct, I'm going to be so very surprised. So okay, what is it? Filter average and v.full filter size and filter size. (326) image channel start and with start weight and okay, now thank God I found that mistake. So now the dx is going to be let's see the shape. So it was 10.6. Okay, yeah, and the delta out, that shape should be not the delta out but D out, which is the delta out. I'm not wrong. Yeah, it should be like that. Okay, so we found the value for this, and after we finish the pooling layer, we actually need to derive the activations. So where is it? So after we done with the pooling layer, we actually need to, when we go back, there's the activation function that we need to derive also. So let's do that. So it's going to be 10h derivative, and it's just going to be a simple, so the back of 10h going to be 1 minus np dot 10h of the output convolutional squared. So that's it. So this is the formula for the back propagation for 10h, which is what we've already. So where is it? So yeah, this is the formula for the 10h, which is 1 minus 10h, and the input of, and then the square, and then you add the square. Now for the finally for the convolutional back prop. So first of all, we need to create the M, and so we need to keeping the track of the H, and then the width, and it's going to be input dot shape. Okay, so it's going to be input dot shape, and this should be 10 and then 28, then 28, right? And for the M and of C of D out, and then N of the H of the D out, and N of the W of the D out should be the D out dot shape after 10h. So it should be the shape after 10h, which is basically the same shape after 10h. It should be 10 and then 6 and then 26, right? Now, so this is basically the input, and this is basically the output shape of after forward convolutional. Okay, because we apply 6 filter, and then since we applying convolutional, we get 26 by 26, which is reduce the amount of input dimension. So the dx is going to be np dot zeros of the input dot shape. Now the gradient is going to be, the w gradient is going to be np dot zeros, the filter amount, and then channel amount, and then the filter size, and the bias gradient should be np dot zeros, that filter amount. Okay, so first of all, we need, so this is basically like this part. Okay, so the filter amount is channel amount, and filter size. Okay, let's compute the derivative of the W, the dw, which is the derivative of the W, and for image, so for every images in the range of M, oh my god, wait, clear output. So for every images for every channel in range of n, of the out, for the height in range of and of the d out should be the height start is equal to the height start, the stride, and then the height n is equal to the height start plus the filter size. And for the width in range of the n of the w of the d out should be the width start, it should be the width, not the should be the width times the stride and then the width, and is equal to the width start plus filter size. Now, so the W gradient is going to be like this. It's going to be delta, so the out of the for every images, for image and for every channel, for every width times the input of every images across all of the channel, and the height of start until the height n, and the width start until the width n. And so okay, so we need to calculate the gradient for the dx, and it's going to be dx of the for every images across all dimension, and it's going to be the height start until height n, and the width start until the width n. Until the width n. And it's going to be the out of every images, and for every channel and every height, and the width times the gradient, not the gradient but the W of channel across every dimension, and that is for the W. And for the so now compute, so we need to compute. So for the dB itself is going to be for every filter in the range of filter amount is going to be the gradient filter across every dimension is going to be np.sum of the out, delta out of filter like this, and let's see the gradient. dot shape. It should be 6. It should be 6. Okay. And if I'm correct, the W gradient dot shape should be 6, 1, and 3, 3. Yes, 6, 1, and 3, 3. And then for the dx dot shape, it should be 10, 1, 3. Wait. Okay. Okay, so we get the correct implementation here. So this is the original. So okay, now dx is equal to the original input dimension, which means we are dimension shape, which means we get the correct dimension. Okay, the goal is to get, so remember the goal is to get the main goal is to get the correct dimension, and we get the correct dimension across the pair propagations. So this is the final dimension that we have, that we get from the convolutional neural networks pair propagations. So this is the correct implementation for the pair propagations. So now we are finished to actually, running the step-by-step of the convolutional neural networks. We are going from, writing the forward convolutional networks, and then the pooling of the layer of the forward process, and then we are, writing the forward fully connected layer, which is just the regular neural networks. And we also did the back propagations, starting from the fully connected layer and then going to average pool, pooling back prop, and then we finally get to the convolutional back propagations. Now let's put everything together. Okay, so it's going to be MNIST implementation of CNN from scratch. Okay, now, okay, you're probably wondering why I'm using the MNIST dataset. So, okay, I already explained that the reason why we are using the convolutional neural networks is to reduce the amount of data, so that we can use a regular image, right? So that we can use an image like this. But why we are using the MNIST implementation again, and why implement this dataset in a CNN? So there's two reasons. Okay, I'm just gonna write it. Why implementing MNIST dataset for CNN? So there's two reasons. Okay, I'm just gonna do this. So the first reason is that for us to understand okay, I don't know if you can see it. Okay, the intuition behind the CNN or the convolutional neural networks. Okay, And the second reason is there's going to be an error, not an error but a big problem. Problem that we are going to have at the end of this particular program, at this particular MNIST implementation, and I'm going to show you at the end, because the problem is at the end of the implementations, so you'll understand the second part for the reason why we are using the MNIST dataset. Okay, so now a big problem at the end. Okay, I'm just gonna write it at the end of this particular program, which is the MNIST implementation for CNN. And you'll see why I'm not just straight up using, a data like this. Okay, so let's start it. First of all, let's import some dependencies, and it's going to be import, of course we are going to use numpy as np. We are going to use pandas. I'm not going to use pandas. I'm not going to see the data. I mean, we've all know what the data look like. We are going to use import mathematical part, and I guess that's it. So no, I'm actually need panda, import pandas as pd, because the file, okay, where is it? Because it's going to be in a CSV dataset, CSV data format, so I need the panda to load the CSV format for me. So it's going to be data, and it's going to be read, oh my god, pd.read underscore CSV, and it's going to be my MNIST CSV, and it's going to be data is equal to np.array. So we change the data into an array format, numpy array, data, and we are going to need image and n, which is the data shape. Okay, and m is going to be I don't know, let's say 1200. And so let's do nv.random.shuffle to shuffle the data. Okay, now we need to split the data, so it's going to be data def is equal to data, so we took the first 1000 data, not data, oh my god, we took the first 1000 data and then transpose this data, then take the label from the data, so it's going to be def, it's going to be data def, oh my god, data def is going to be 0 because the label is on the first column, which is the 0th index, and it's going to be x def, it's going to be data of 1 until n, okay, which is the amount of data, and it's going to be x def is equal to, oh my god, x def is equal to the x def divided by 255 to normalize the data, normalize the data. Okay, And for okay, so that is the data depth. So now we need to create a data train, and the data train is going to be from 1000 up to m, which is the amount of data. So n, okay, if you remember, so this is the amount of data that we are going to use, and this is the, so n is going to be the amount of pixel. Okay, okay, I'm gonna write it here. M is equal to data we are using, and amount of data that we are using, and the n is the amount of pixel, which is again 28 by 28 for the MNIST dataset. So again, we are going to create the x, not x, but y train, which is the label, and it's going to be the same, which is the data train, and it's going to be in the zeroth index. It's going to be x train, and it's going to be data train, and we're going to take 1 until n, because this is the amount, so because this is the amount of pixel. Okay, and we are going to normalize the data. X train is equal to x train divided by 255. Okay, now we are going to take the amount of train from the x train. Oh my god, that shape. Just for the in case we are needed. Now that is the data split. Now let's create the one hot encoding for the label, and it's going to be y train, so of course, and we are going to take the y train until let's say 32. Y train. So okay, I'm gonna treat this data as a batches. Okay, so I'm going to take the 32 as, you know, 32 batches. So size of batch, basically. Now it's going to be one hot y is equal to np dot zeros of the y train dot size and the y train dot maximum plus 1, and it's going to be one hot y, one hot y np dot arrange the y train dot size and the y train, and it's going to be equal to 1. Okay, so one hot is going to be one hot y dot transpose. Okay, so we've already going through all of this actually in the previous segment, so if you still kind of confused, you can go back to the previous segment. Okay, now the batch size, okay, I'm gonna instead of just gonna put it here, so I'm going to have batch size is going to be 32, and instead of like this, I'm going to do something like this. Okay, and the batch size, so it's going to be x train reshape, and it's going to be x train dot t dot reshape is going to be -1 and then 1 and then 28 by 28. Okay, so now we need to split the reshape data into patches of size 32. So patches is going to be xtrain reshape, and it's going to be I until I plus batch size for I in range of 0 and x train underscore reshape dot shape of 0 and the batch size. Okay, I don't know if you can see it. Okay, so this is going to be just a regular for loop, but we are doing it inside of just a singular line inside of a patch. So this is how you do for loop. So you just going the same kind of rule with the for loop basically. Okay, now if this is correct, we are going to have 32 by 1 by 28 and 28, which is going to be stands for patch size, or the amount of data inside one patch size, and then the dimension of the image and the pixel, the width and the height. So the width and the height. Okay, so let's see if this is correct. So I'm going to print the patches of 0 in the 0 index dot shape. And let's see if yes, we get the 32 images and one dimension and then 28 by 28 pixel. Okay, now we are going to create the simple CNN model. Okay, now okay, so first of all let's create the variables. So the hyperparameter is going to be filter amount. Okay, I want 6 filter amount. I want the channel amount is going to be 1. I want the filter size is going to be 3 by 3 is going to be 3. I want the stride of 1. I want the padding 0. I want the iteration probably just 10, and the learning rate is going to be 0.01. Let's do that, why not? And the input is going to be patches of 0, which is we are going to have 32 images that we are going to process. Now let's create a learnable parameters, and it's going to be, we need to set the boundaries of 1 divided by the math square root of the filter size times the filter size, which is 3 by 3, and we are going to have w as np.random.uniform, and it's going to be minus bound, and then the bound, and then the size of, wait, what's going on, and then the size is going to be equal to filter amount and the channel amount, and then the filter size, and then the filter size. Okay, so this is going to be the, so the filter amount is 6, so it's going to be 6 by the channel amount by 1 by 3 by 3. Okay, and the bias value is going to be np.random.uniform, and it's going to be minus bound and bound, and the size is going to be the filter amount. Okay, because each filter needs its own bias, needs only one bias, right? So this is the learnable parameters for the convolutional part. Okay, let's write the learnable parameters for the fully connected one, connected layer. I don't know if you can see it. Okay, I'm going, okay, so it's going to be the width, it's going to be 6 times 6 times 26 times 26. Okay, and the height is going to be 32 because we have 32 patches. So we should set the bound of 1 divided by np dot square root of the width. Okay, and w for the fully connected layer is going to be np.random.uniform, and it's going to be the low is going to be, my god, minus the bound, and the high is going to be the bound itself, and the size is going to be the height and the width. And for the bias in the fully connected layer is going to be np.random.uniform, and it's going to be the same for the low, is just the minus bound, and the height is going to be the bounds, the boundary, and the size is equal to 1 and then the height. Okay, and let's create the convolutional gradient parameters. So it's going to be w grad, np.zeros, and it's going to be the filter amount and the channel amount, and it's going to be the filter size and the filter size. And for the bias gradient, it's going to be np.zeros, and it's going to be the filter amount. Okay. Now we need to have so the fully connected layer initialization. So the first fully connected layer initialization. And it's going to be, so let's create I and then C, and then the width and the height, and it's going to be the output.shape. And for the width, we're basically doing everything that we've already right above here, but just putting it all together. And the width is going to be width multiplied by the height, and then multiplied by the C. Okay, and for the hidden neuron, is going to be the amount of images. Okay, so now let's initialize the weight and biases for now the hidden neuron should be 32, because we are going to use 32 image for every index, for not for every index, but for every batches. Okay, so we need for the first fully connected layer, which is, so it's going to be the bound of the fully connected one. It's going to be 1 divided by np dot square root of the width. And so for the w dot fully connected 1, it's going to be np dot random, oh my god, dot random dot uniform, and it's going to be the low part is going to be minus bound, oh my god, and the high part is going to be the bound, and the size is going to be hidden neuron, and the width bound, so it should be bound fully connected 1, and then bound of fully connected one. Okay, so for the bias for in the fully connected one, it's going to be np.random.uniform, and it's going to be the bound of fully connected one and the height of the bound, oh my god, the bound of the fully connected one, and the size is going to be the hidden neuron. Okay, now for the second, so this is the first fully connected layer, and we need to have the second fully connected layer. Okay, so the second fully connected layer is going to be, going to has 10 neurons, because we are going to classify the MNIST dataset, which is an image that's going from 0 through 9. So we are going to have 10 neurons for the each of the of the label, so that we can create the probability distributions out of those neurons. Okay, so the output neuron is going to be 10, okay, which is the amount of label, and the bound for the fully connected 2 basically, okay, it's going to be 1 divided by np dot square root of the hidden neuron. Okay, now for the W of the fully connected 2 is going to be np.random.uniform, and it's going to be the low of minus bound, and the high is going to be the bound, and then the size is going to be the output neuron and the hidden neuron. Okay, so for the bias in the fully connected layer number 2 is going to be np.random.uniform, and it's going to be low is equal to minus bound, and then the high, actually the bound and the size is going to be 1, and the output neurons. Okay, now I guess that's it, I don't know. So now we write the training part, which is the gradient descent for CNN. Okay, so it's going to be for I in the range of the iterations that we have. Oh my god, iterations, and it's going to be M, N, C, and then previously. Okay, so this is going to be the convolutional initialization. Okay, and C previously, and then N, H previously, and then N, W previously. So it's going to be the input shape. Okay, now for the new number of the channel is going to be the filter amount. Okay, now the new height is going to be the integer value of the n, h, previously plus 2 times the padding minus the filter size, oh my god, minus the filter size divided by the stride plus 1. And similarly with the new width is going to be the integer value of the n of the width of the previously plus 2 times the padding minus the filter size divided by the stride and plus 1. Okay, so the output of the convolutional is going to be np.zeros of the m, which is the amount of images, and then the new number of channel, which is the amount of filter that we are going to apply, and the new height and the new width, which is the pixel dimension. Okay, now further forward, convolutional, so it's going to be for every images in the range of the every image, which is the m, and for every channel in the range of the new channel number channel, and for the height in the range, oh my god, the range of the new height is going to be the height start, which is the height times the stride, and the height n is going to be the height start, the height start plus the filter size. Okay, now for the weight, for the width in the range of the new width, here is going to be the width start is equal to the width times the stride, and the width n is going to be the width start plus the filter size. Okay, and so we need to replace the convolutional width for every images, for every channel, for every height and width with the np dot sum of the input for the images across every dimension for the channel, and the height start until the height n, and then the width start, oh my god, until the width n, and then multiplied by the w, oh my god, and it's going to be for every channel across every dimension like this, plus the bias for every channel. Okay, I hope that's correct. Now So we need to get out of this for loop now, and I guess going to be here. So we get out of this for loop, and we are going to writing the activation for the convolutional output. So it's going to be out convolutional 10h. So let's use 10h because the numpy has the 10h command, the 10h. So it's going to be the out of the convolutional, like this. Now let's do the pooling layer, and we are going to use average pooling layer, and it's going to be the average pooling initialization session, and it's going to be the amount of images, the amount of channel of the previous one and the previously, the amount of the height previously, and the amount of the width previously, and it's going to be out of the convolutional dot shape. So we are going to take the shape. We can use the 10h actually, so that it's not confusing. So now we are going to get the new number channel is going to be the filter amount. So it's still going to be 6, and the new height is going to be the integer value of the n of the previous, oh my god, previously plus 2 times the padding minus the filter size divided by the stride plus 1, and for the new width is going to be the integer value for the n, the width previously plus 2 times the padding minus the filter size, okay, divided by the stride plus 1. And for the output, so it's going to be out the pooling layer, it's going to be np.zeros, it's going to be the amount of images, the amount of new number channel, and the new height and the new width. Okay, and so the forward propagation for the pooling layer, for the average pooling is going to be for images in the range of the m, which is the amount of images, and for every channel in the range of the new number channel, okay, and for, oh my god, and for the height in the range of the new height previously, the number of height previously. So it's going to be again the height start, the height, okay, start is equal to the height times the stride, oh my god, stride, then the height, and it's going to be the height start times the but the filter size. Okay, so the output layer, not the output yet, we need to have the for the width in the range of the number of the width previously, and it's going to be the width start is equal to the width multiplied by the stride, and the width n is going to be the width start plus the filter size. Okay, now for the output, the pool for the every images for every channel, for the height and the width, we are going to get the average value, which is we are going to use the np.min for the out of the convolutional of the 10H, and it's going to be images, the channel, and then the height start until the height n. Okay, and then the width start until the width n. I hope that makes sense. Now we are okay. I hope you see that. Okay, now we're done with the forward for the pooling layer. Now let's get into so we need to get out of the for loop for the forward average pooling, and we need to have now the fully connected layer. Okay, and the fully connected layer is going to be the out pool flat, and it's going to be the out pool dot reshape of the m and then -1. Okay, so m is going to be the size, which is 32, right? Oh my god. And a for the fully connected one is going to be np dot, which is the dot product between the output flat. Oh my god, what is this nonsense? So it's going to be output flat. Okay, and oh my god, what is this? So the w for the fully connected one dot transpose plus the b bias value for the fully connected one. Okay, now for the z value, we are going to get the fully connected one, fully connected, not the fully connected, not for the z. So the z of the fully connected one is going to be np dot, so we are using 10H again, and it's going to be a dot ar score fully connected one. Okay, and now we are going to have the a for the fully connected 2, and it's going to be np dot okay, what is this nonsense? np dot between the z of the fully connected one and the weight of the fully connected 2 dot transpose plus the p of the fully connected 2, the bias value. Okay, now we need to write the probability distributions, which is the softmax activation function. Okay, so the softmax is going to be the np.exp for the A fully connected to okay, so the fully connected to divided by the np.sum of the np.exp. Oh my god, and because we A underscore fully connected to, and I want to keep the dimension, so it's going to be the axis is equal to 1 and the keep dims is equal to true. Okay, now for the loss part, so okay, I need the patch size. So the patch size is equal to softmax dot shape the first index, and okay, so we write the delta L, which is the delta loss, and it's going to be softmax minus the 1 hot dot transpose. Okay, and we need to create the loss, so it's going to be the negative log likelihood, so we are going to have np.sum 1 hot and then we transpose multiply by the np of the, so it's going to be the log value of the softmax plus 1 e minus 8. Oh my god, I hate it. Divided by the patch size, if that makes sense. So okay, I'm adding the small constants, which is this 1 e minus 8 to avoid the log of 0 basically. Okay, and we can print the loss here, so using the f string is going to be the loss of the loss like this. Now we need to go back, so the back propagation through the second of the fully connected layer, which is the softmax part, is going to be, so we need to have the gradient weight of the fully connected to, and it's going to be 1 divided by the m, the amount of data, and multiply np dot of the delta L, which is just the delta loss, and we need to transpose and the C of the fully connected one. Okay, now for the bias for the fully connected 2, it's going to be 1 divided by the m times the np dot sum of the delta L, and less the axis of 0. Now okay, so this is the gradient for the fully connected layer 2, and so this is the gradient weight, and this is the gradient bias for the fully connected layer 2. Okay, does this make sense? Now we need to backpropagate. Okay, so backpropagate the error value to the first fully connected layer. Okay, so it's going to be the new delta L is going to be np dot product between the delta L oh my god, delta L and then of the fully connected layer 2, so multiplied by the 1 minus z or the fully connected one squared. So okay, so this part is the derivative of the 10H activation, which is this part. Okay, this part. Okay. After that, we need to backpropagate through the first fully connected layer, which is the 10H layer. So this is the softmax part, which is the second fully connected, and this is the 10H part, which is the first fully connected layer inside of the forward propagation. So again, we need to have the gradient for the weight of the fully connected one, and it's going to be the 1 divided by the m multiplied by the np dot the dot product between the new delta L. Oh my god, I hate it. Delta L dot transpose and the output flat. Okay, and so this is going to be the gradient weight for the fully connected layer 1, and so the gradient bias or the fully connected 2. Not the fully connected, no, it's going to be the 1. It's going to be 1 divided by the amount of data times the np dot the sum of the new delta L and with the axis of 0. Okay, we are doing that now. So oh god we need to get inside the average pool backpropagations. Okay, and it's going to be the new delta L. It's going to be np dot the dot product between the weight or the fully connected one transpose and then the new delta L. And so the delta out is going to be np dot the reshape. So okay, so this is going to be the one-dimensional no shape, because it is coming out, because it's coming from the fully connected layer. So we need to reshape it in an image kind of shape, because this is the pooling layer. So it's going to be the new delta L is going to be the amount of images, the amount of inside of every batch, and it's going to be 6. It's going to be 24 and 24. Okay. And for the M of the N of the C, and then the N of the H, and then the N of the W is going to be delta out dot shape. Now for the dx is going to be the np dot zeros, and it's going to be 32, and then 6, and then 26. Okay. Right. So now, so this is basically the output from the so this number is the output shape of the convolutional forward, right? And no, this is the output for the pooling, and so this is the output shape of convolutional forward. Okay. So now for every images in the range of the every images, the range is going to be for every channel in the range of the n amount of channel, and for the height in the range of the height, it's going to be the height start again, and it's going to be the height multiplied by stride, and the height, oh my god, height is this nonsense, the height n is going to be the height start minus filter size plus the filter size. So that is the height. So for the width itself in the range of the and the W, so it's going to be the width start, and it's going to be the width multiplied by the stride, and then the width n is going to be the width start plus the filter size. Okay. Now for the average part is going to be the delta out it's going to delta out. So so for every images inside every channel, for the height and the width, it's going to be divided by the by the filter size, and the filter size, which is going to be a 3x3 kind of shape size. Okay, filter. Okay, size and filter size should be like this. Okay, and for the filter average, it's going to be the np dot full of the filter size and the filter size. Okay, and the average, I don't know if you can see that, and the average here. Now for the dx of the image in the every channel, and so it's going to be the height start until the height end, and the width start until the width end, it's going to be the filter size. We are going to, not the filter but the filter average. So we need we are going to add all this value with the filter average value. Now we need to get out from this for loop, and now we get to the back propagation for the convolutional. Okay, and so first of all we are going to derive the 10H, and so it's going to be the dx, it's going to be like this, which is 1, this is 1, oh my god, 1, oh my god, so it's going to be 1 minus the np.10h, the out of the convolutional, and then take the square value of those. Now we need to have this variable, which is n, and then the nc, and then n height, and then the nw again, and it's going to be input.shape. Okay, so the input.shape is going to be well, I don't know actually, it's just going to be input.shape. Okay, I forgot. So basically, so it's going to be np.nc, and then the out, and the amount of n w m n w of the out, and the n of the so h first, and of the h of the out. I mean, this is basically the same thing. The out is going to be, so the delta out dot shape. So this is going to be the shape after 10H, right? So it's going to be I don't know, it should be 32 by 6 by 26 by 26 if I'm not mistaken. And so the dx is going to be np.zeros of the input shape. Okay, now we need to compute the dw. So for images in the range of m, and for channel in the range of n c of d out, and for height in the range of n the height of the d out is going to be the range is going to be the height start, and it's going to be the height multiplied by stride, and then the height n is going to be the height start plus the filter size. Now for the width in the range of the n, the width of the d out is going to be the width start, and so it's going to be the width multiplied by the stride, and it's going to be the width and it's going to be the width oh my god the width of the start plus the filter size. Okay, the width, so is the in why is it like this range, oh my god. Okay, now width and width start. So for the W, okay, I'm gonna do this. For the W gradient, it's going to be for channel across all of the dimension. It's going to be the delta out. Okay, for image, it's for every image and for every channel, for every height, and the width is going to be multiplied by the input of the image across all of the channel, dimensional channel, and then the height start until the height n, and then from the width start until the width n. Okay, and for the dx is going to be the image across all of the channel dimension, and it's going to be the height start until the height n, and the width start until the width n, oh my god, n, so it's gonna be the delta out of the image, and for every channel, for the height and the width multiplied by the W value, the weight value, as going to be the channel across all of the dimension. Okay, so that is the gradient for the W. Now we need to get out of this for loop and compute the dB, which is the bias value. So it's going to be yes, it's going to be dB. Compute like this. So it's going to be for filter in range of the filter amount. Okay, and it's going to be the B gradient. It's going to be the filter across all dimension. It's going to be np dot the sum of the delta out so delta out until, so for every images filter across all the dimension. Okay, I hope that makes sense. Now we need to get out of this for loop and update the parameters. So the W for the fully connected 2 is going to be the learning rate multiplied by the gradient W of the fully connected 2. Okay, and so the bias for the fully connected 2 is going to be the learning rate multiplied by the gradient of the bias for the fully connected 2. So for the W in the fully connected 1 is going to be the learning rate multiplied by the gradient of the W for the from the fully connected 1, and the bias of the fully connected 1 is going to be it's going to be the learning rate multiplied by the gradient bias value for FC1, which is fully connected 1, and it should be 2. Okay, now for the final, so it's going to be W is going to be the learning rate multiplied by the W gradient, and for the bias is going to be the learning rate multiplied by the B gradient. I'm not gonna lie, I'm not sure about the code. So okay, woo. So we read a lot of code, and let's see if it's worked. I'm not gonna lie, I'm very surprised if it's working in the first try. But if it's working in the first try, I'm going to reveal, I'm going to show you what do I mean by there's going to be a big problem at the end of this particular program. Okay. Start to learn. Okay, so as you can see, we are managed to reduce the amount of loss, but there's a big problem, and that is it is very slow. Even though we are using only 32 images for each batches, and it turns out it is very slow, and we are only using how many epoch? We are using 10 epoch or 10 iterations, right? But we are having such a slow computation, because it turns out, okay, so when we reduce the amount of data by using